Well, now that we have an IDE in place, let's talk a little bit about it and then get ready to do something with it. So the language in this course is C, most specifically the C11 version of C. What's so great about C that it's so important for so many people to learn about? So a snippet of history. Dennis Ritchie was at Bell Labs. He's the person who recently died, unfortunately, but he invented the C programming language in 1972. Or so you thought. Actually, C is a successor of a language called B, developed by Dennis Ritchie's colleague Ken Thompson, which in turn, you may guess it's a successor for another language or languages. There are many, many languages in use today, but there's something really special about C. Originally, C was developed for computer programmers. There are very few languages that have this mindset. If you're not a computer programmer by profession, or if you're just starting, you may not be aware of what the flavor and mindset other languages have, but as you get to know C better, you'll appreciate some of the things that C can do for you because it's so integrated with the Unix operating system and with the way programmers think. C was designed as a practical tool, not necessarily an academic tool like Pascal. Pascal is a language that was widely used in the 80s and late 70s. It was a simple language that was designed, among other things, to help teach freshmen and professional later on how to program first on mainframe and then on other computers. Unix was the operating system that was developed in part as an academic exercise. However, Unix didn't have good programming tools. This is where C was the language that was supposed to take the leading role in providing that set of tools that are both powerful and practical. C is not really a high-level language, like most people refer to. It is sort of a hybrid language. It has features of high-level languages, but it also has features of low-level languages, often referred to as assembly. C implements an approach to programming called functional. We will talk about this a lot, as opposed to, for example, object-oriented, a term you may have heard if you're interested in computer science and computer programming. C11 is the current standard for C. It started to be developed in the end of 2007, 2008, has been with us for quite a while, some time. What you need to know is that if you try to use an older book that refers, for example, to a standard like C99 or C98 or earlier, there are some minor changes that will cause your programs not to run today. However, for the purposes of this course, we are using the very, very standard version of C that withstood changes throughout probably about 30 years or so since people first started to talk about C. Other advanced topics like concurrency, threads, parallel programming, and security, those are the main issues that the new standard is dealing with. You shouldn't be concerned without those because they are irrelevant to the topics discussed in this particular course. One of the reasons we need standards is because we want a language to be available for programmers on multiple machines. We want to ensure that if you like to program on a Mac and your code is intended to run on Windows, then you don't have to switch every single tool, every single language. So once you learn a language, that language should work pretty much the same on every machine. Even though the tools may be machine-specific, the language itself should be the same. Another reason that the C11 standard is becoming more popular is because there is a cousin to C called C++, which is an object-oriented version of C, which is more modern and has some features that C priorly didn't have. So C11 now is becoming more compatible with C++ to the point where, in many respects, the language C has become a subset of C++. Therefore, should you like to learn more about programming in the C family of languages, it should be a fairly easy transition for you to go from C to C++ once you really mastered C. In this video, I'd like to refer to a concept that I like to call the engineering mindset, meaning C and other programming languages are fundamentally tools designed to solve problems. Whenever you're looking for a solution to a problem, you need to have a plan. You need to have something in mind before you start writing code. There is a reason why we're spending sometimes in the previous video and this one just talking about C, reflecting on some issues, and we're not jumping straight into writing code. The number one thing you have to take into consideration before writing a program is you really have to ask yourself, what do you want that program to do? Sometimes you write a program because you just feel like it. Sometimes you write a program that somebody else asks you to do. You have to make sure that you really know what this program will do and that the language you chose is the most appropriate for that task. Second, you need to have a plan. What are you going to do first? What will you do second? And so on. Writing code, it's not like playing a piano, just sit down and improvise and press some keys. You really need to have a plan. And before that, you need to have some grand idea that's the heart of your plan. Later on in this course, we will talk about formal ways to plan for writing code, namely about algorithms and flowcharts and other ideas and tools. For now, we'll just say you need to know what you want to do before you start doing it. After you know what the program wants to do, you can sit down and write your code using the IDE. In this class would be Eclipse. After the code is written, there's a process called compilation. The compiler is the heart of the IDE. The IDE has many components. Essentially, what the compiler does takes the piece of code that you write, which is essentially just plain text, uses another software that analyzes that code, makes sure that it follows the grammar's rules of C, and converts it into ultimately binary code that the computer can understand. What's great about C is that you can type C code in any editor and then take it onto any machine that has a C compiler and the code will run. This is what we refer to as portability that was really improved in C11. Once you run a program, the compiler will let you know whether it ran without errors or with errors. Just because a program runs without errors, it doesn't necessarily mean that it does what you intended it to do. So it requires further testing on your behalf. Keep in mind that fix an error, it's a daily activity in every programmer's life. In fact, it is guaranteed that you will spend more time debugging and fixing errors than actually planning your next great program. So if it's something that you really look forward to do, then programming is for you. If you dread being told that you're wrong every few seconds by a machine that's not really that friendly, then you have to do something to overcome that, because there's no greater reward and satisfactory feeling than fixing a problem and getting something to work. Then, right when you thought that everything is done and your program runs without error, guess what? You can do it better. The second most frequent activity you'll be engaging after fixing error is making everything better. Never be satisfied that the program you created is the final version of it. If you spend any amount of time on computers, you have noticed the frequent updates from various applications you have, whether it's a browser, a word processor, a spreadsheet, you receive almost daily notification of a better, newer version, which means programmers either spend their time fixing errors or spend their time doing something better, and so should you. By now, you're probably anxious to start coding, so we're not going to postpone this any further. Let's talk a little bit about our first C program. As we just recently showed you, before you get down to writing code, you need to have a plan. In this case, the plan is to show you how to write a very simple program that will ask the user to enter a number and then will print back that number. Let's switch now to the IDE and see how this program works, and we'll talk as we look at the program, at the code, what some of the things do and what would be the best approach for it. So this program is intended to do a very simple thing. It's ask the user to enter a number. We want the user then to type that number, and the program will then print the number back. As you can see on the right-hand side here, in green, there are comments. Comments are not part of the program. They are just text intended to explain certain lines of code. We will spend more time later on talking about what is a comment, Where should it go? What should it say? Let's focus on the code. Without getting to all the details, what every command does and why it is there, let's focus on the main things that we wanted this program to do. As we said, we had a plan. Our plan was to tell the computer to ask us a question. This line right here, please enter a number. It's a hint that probably this is where this will happen. You can infer, even if you don't know C, that the command like print probably prints something. It may not be intuitive to you that a command like scanf asks someone to enter a number. Scan comes from the word scan for an input. Finally, after the user receives the instruction to enter a number and types the number, the computer will again print, you enter that number. There are other things that go on here. As I said, we're not going to focus on them right now. So let's put this to test. First, we're going to build this project, if it's not already built. Build finish. We know that everything was smooth and no errors. And now we can run it. And as you see, the program is asking me to enter a number. So I will enter a number and hit enter. And the computer tells me that I entered 345. Everything works flawlessly. The program does exactly what I instructed it. But let's try something else. Let's run the program again. And what if I don't type a number? What if I type some letters? Let's see what happens now. Aha, didn't expect that. We'll talk about this later. I'll just mention one thing. Whatever you think it's a letter or a number, that's all in your head. To a computer, everything is number. Not just numbers, but binary numbers. We'll get into this much later. One thing to note right now. C assumes you know what you're doing. It will not tell you, other than illegal grammar usage, it will not tell you anything about your style or what you meant. It will not second guess you. Sometimes in computer science, we want to call this GIGO or GIGO, which stands for garbage in, garbage out. If you're going to write code that's garbage, it will create garbage. It's a term commonly used by most programmers and in other industries as well. Well, now you have your first C program that works as long as you give it exactly what it asks you. And if you try to be smart, he'll outsmart you. Preprocessor sounds like a scary word. In fact, it's a very helpful one. What C does, it enables programmers to create or work on projects that are very large in scope, distributed among multiple locations and multiple people. And the way this happens is using the command called include, which allows linking multiple files across systems, locations, and to multiple individuals. We will see shortly how this works in a C program. Include file, the second one with the double quotes, works in a similar way. So why do we need the two? The first one with the brackets, those are files that are already part of the standard libraries, which means just like you go to a library and borrow a book you don't already have, your program can link to a file from the library and use it. In fact, multiple people can link to the same file. The file in double quotes is a file that you created. Look at it as a custom document or a custom book that you placed in your own library for anyone else to use at will. One file can be included by multiple projects. And finally, there's a define command that allows you to substitute a number or a value that doesn't make much sense by itself with another one that does. For example, buffer size. Rather than referring to the number 1024 throughout your code, we can simply rename 1024 as buffer size. And from that point on, this is how it will be known to you throughout the code. The compiler at runtime will replace buffer size with 1024, and the program will run as intended. Let's see how this works in an actual program. You notice already the two include commands in every single example you've seen so far, but we never talked too much about it. Notice that the first two ones, the stdio or standard input-output, and stdlib, which is the standard library, are two programs or libraries that are included with every single default C project. The third one is more interesting. The third one is the one that we created for this project in order to illustrate how the linking works. Let's run this code and notice something. Obviously, the code works because somebody told it to print out the words it works. Let's see where in the code it works will come from. If you look throughout these lines, there's nothing here that says printf it works or any other printing command. We must infer, therefore, that it must reside somewhere else. In fact, if you look at line 14, include mylibrary.age, that's the clue the compiler looks for to find a resolution for commands otherwise not explicitly programmed. Let's look at mylibrary.age. Mylibrary.age, if you look at line 11 and 12, has definitions of two functions. In fact, function 1 is used in line 20, or called, as we say, but it's clearly part of mylibrary.age. Still, in mylibrary.age, we don't see any reference to the words it works. Therefore, we infer they might have to come from somewhere else. In fact, there is a mylibrary.c. Mylibrary.c is the file that actually has all the functions we need. We will talk about how this works in greater detail in further down the road. However, all we need to know right now to summarize this: if you want to extend the functionality of your main programs beyond what it has already built in and what C provides you, you can simply include a library.age, which then requires that you have a pair of files, library.age and library.c. .c has the actual code, .age has some linking code, which we'll explain later on. C program, like any other program, when done professionally, can very quickly grow out of hand. This means they can become very large in size and spread over multiple files. This is why we need to be able to use several tools that the C language gives us in order to make our code more manageable. One such tool, it's actually a process or a best practice called breaking up code into blocks. It's much easier to debug, to plan, to write, to review, and improve if the code is not all written in one big chunk. This is why we have a mechanism in C, as we do have in other languages, called functions. Those are blocks of code designed to perform a task. There are two main categories of functions in C. Ones that are built in, like getChar and printf, that are predetermined and predefined, and they're part of the standard libraries. And the others are completely at the discretion of the programmers. They can have any name you want. However, we'd like to note one notation called the camelback notation, especially useful when you have very large words. Calculate sum of two numbers. Notice that every word that makes up the function name starts with a capital letter. This is a function that does just what you'd expect it to do. Calculate the sum of two numbers. The numbers are a and b. Let's see how this is done in code. This is an example of a fairly large C program, definitely larger than the one you've looked at so far in the videos in this course. A quick scroll towards the bottom, you will see that there is a main program in line 21. There are task 1, 2, and 3 above it. There are calls to multiple tasks. There's even calls to special tasks, and so on. You can see how this can get out of hand very easily. Sometimes it's even hard to see where the program starts. We'd like to reinforce the fact that every C program requires a main function, and only one. You cannot have two mains. There has to be exactly one, and this is where execution starts. Some of the functions, like special tasks, are actually included in a separate file via the include special tasks in line 14. Let's quickly see what is in those files. As we saw earlier, it is possible to define multiple functions external to a current program using the include command to have access to them. In this case, there are more interesting things that can be done with functions. For example, in line 34, task 1 actually doesn't do anything except calling task 3. Task 3, it's a special task, which its name hints, is defined in the special task library. If you look at special task 3, it says special task 3 was called. The reason we did that is that we wanted to have unique functionality. So for example, if I want to make some changes just to special task 3, I only focus on lines 24 through 30 in the library special task. This is the beauty of breaking your code into blocks. Let's run and see what happens. When I run this code, you see that all the things that were in main and in various tasks were executed up to the point that I'm being asked a number. Let's quickly look at the main and see where would this have come from. See how hello world was printed, the multiple task was called, and some of those functions is calling task 3, which is entering a number. Let's enter a number, and now special task 2 was executed because after task 3 in main, special task 2 is being called. So using this approach, we were able to create a fairly complex web of links in which external libraries played an integral role in running this code. In order for programs to do anything useful, obviously they require data. Data is nothing but memory labeled by what we call variables. Data types and variable are strongly linked together. Data type describes what type of storage will be placed into that memory location, whether it's a number or a letter, and if it's a number, what type of number, and so on. In order for you to use a variable, you have to inform the compiler, C in this case, did you have an intention of using that variable? We call this declaration. Variables could be decimal numbers called floats in C. For example, that's a variable called height, which we want it to be of type float, or it can be a character and we want the variable to be called letter. Or we want it to refer to age as an integer number. How can you decide what's the most appropriate variable for a given instance? Let's look at the code. For example, if you want to look at the variable called the price of gas in California, and I know it's 99 cents, the most appropriate type would be float. Float is a decimal number that doesn't require too many digits, or in computerese, not too much higher precision. Another variable is y, which is clearly defined as an integer. For now, it has the value 0. If you look at line 19, later on, the same variable y gets a new value, 12. Over time, one variable can receive many values depending on what happens in the code. If you still like integers, but you don't need to use the full memory size that they require, there's another type of integer called short. In this case, line 17, the variable a is a short variable, meaning it's an integer but doesn't require that much space. As you improve your programming skills, you will be able to make a clear determination about the space requirement and the memory requirements and how much memory your entire program is using, and this will inform your decision about variable types to use. Line 18 is another type of a decimal point, which in C is called double. Double means it's a float, but twice the memory requirements. In this case, radio is 2.34567. Now that we define the variables, we can use them. In this case, all we do with those variables is just printing them. Look at the focus I place on the different formatting with a printf. Printf is a function that's already available in C, which allows you to format the printing for specific strings of words, of characters that are labeled for the variables and data that you print. If you look at line 21, because the price of gas in California is a float, we're going to use the designation f, which is the %, and f. On line 22 and 23, because y and a are integers, the designation in printf is d. Line 24, because our designation for radius is double, we're using the directive lf, which stands for long float, or double the float. Unless you put the exact matching designation in the printf, you may either not print a value at all, or you may print the wrong value. So it's really important that you match the type of variable with the type of directive inside the printf function. Let's see how this works. When the program runs, notice a few interesting things. The default for the price of California is 6 decimal points. Unless otherwise specified, the default format in printf is 6 digits of the decimal points. This is why 0.99 is 0.99 and 4 zeros. Integers are unchanged. The double float is printing the same thing as the float. That's why we have that extra 0. If we had the larger numbers, those digits would have been printed as well. Statements and expressions are some of the fundamental building blocks of every computer program. In fact, in C, a lot of those expressions relate to mathematical formulas, and it's not surprising given the deeply rooted foundation in math that C has. For example, anything that has to do with variable constants and operators, this is language directly borrowed from mathematics. Things like 25 plus 12, or x squared, or length times width. In fact, C, married to your computer, it's an awesome calculator. Everything you can do with one of those fancy graphic calculators, you can actually program in C and have your computer do the same. Statements are code elements that execute an action. Statements are actually expressions put together into a formula that calculates something. For example, age equals today's date minus birth date. Here's another little bit more complex expression. You have not learned yet in C, but try to read through the words. If age is bigger than 17, then can drive equals true. Those two are examples of statements and many more that you will see shortly. In this code, we see different ways in which you can type expressions and make statements with those expressions. For example, you can define on line 16 a variable days and immediately assign it a value that's a result of a computation. In line 17 and 18, you're creating just simple expressions in which you assign initial values to variables for later on to be used in a more complex statement. This may be simple, but it actually has a practical use, calculating the perimeter of an object. Assumed the formula to be 2 times width plus 2 times height, which I explicitly wrote as width plus height plus height. Since the width and height are given, we can now calculate the perimeter and print it. And let's see how this works. We build a project and we run. And lo and behold, the perimeter is 46.94. I could easily change these numbers to something else should I want to calculate another perimeter. And all I have to do is hit run, click yes, and here's my new perimeter. However, what happened here, it did not recalculate the new value because there's another step, which we will learn shortly, that requires an additional building of the project. So one of the things to keep paying attention to is that when you make a single change, not everything happens behind the scene as you would expect. So it requires a little bit further digging and investigation into learning how the IDE and the C language work. Let me ask you a question. Do you see yourself more as a math and science person or more of an English or humanities person? Sounds kind of strange since you are, after all, watching the C programming class, but actually, if you're going to be programming for a living, expect to write a lot and not just code. Comments in code are often overlooked. However, one of the marks of a good programmer are the ability to document the code thoroughly to the point where somebody that looks at the code and doesn't know anything about what the code does should be able to read the comments and tell exactly what that program is intended to do. Therefore, one of the main attributes of comment is that it should add some useful information about the code. Comments are often overlooked, and therefore, when you're going back to look at some program you wrote a while ago, if it's uncommented, you may not remember or not understand even if it's your own code. Here's an example of an unuseful comment, which is equally important to know. Int number, obviously, it's meant to be a number, that's integer. So adding a comment, the numbers in integer, it's not only useless, but annoying. Here's another way to write a comment. Float pi equals 3.14. Everybody knows what pi is, so there's no point in putting a comment that this is pi. Rather, explain what this is, ratio of circumference to diameter. Let's look at some code and see how one would use comments to further explain it. Let's start with the header of the program. Unlike in other videos, this section now is filled out completely. It's customary in computer projects to have a very complete header that identifies the programmer, the version, who owns the code, and so on. Comments start all the way at the top of any programming file. In this case, a header that is very formal and identifies the programmer, the version, the owner, and anything else you would like to include as part of the template of documentation in your company. Below, it's a description. Whenever you write some code, it should be very polite to other programmers and other people who may want to look at the code, not all necessarily programmers, and explain to them what this code is about. In this case, it solves a problem, it implements an idea, and so on. Even though you may know that those to include statements refer to access to external libraries, it is a good idea to know that those are indeed external libraries. This is not necessarily an obvious comment, as it does not repeat what's already written in the code itself. Then we move to the special constants section. It's customary and very useful if you use the define command to label numbers using a special word that's more meaningful to you, to group all those constants into one place and label that section, in this case, obviously special constants. Next to each one, I'm explaining what does upper boundary 100.12 mean. It is the highest permissible temperature in Celsius degrees, freezing point, lower boundaries, and so on. The more explanations you provide, especially if you're doing computational programming, it's very helpful. Further down, line 30, there is a counter that's initialized to 0. It is often a good idea to explain to the reader and the user or somebody that performs quality assurance on your code what is the purpose and the meaning of that variable. It's obviously an integer and it's obviously initialized to 0. So what do you need it to be more than that? Well, it's used to count the number of times certain tasks are performed, and so on. Let's scroll further down. Now we have a label of an entire section. Those are the custom function definitions. We have a function that reads data, another one that processes data, and another one that prints the report. In this case, these functions are not defined. They're just called function stubs. A stub of a function is a function that has yet to be implemented. Therefore, you can look at this comment as a note to self of what needs to be done later on in this function. Once your code is fully commented, it helps you analyze the logic in case things go wrong. For example, you may not remember why did you want to initialize the counter to 0, and if you know why, is this the proper place to do so? To this point, we have learned a lot about the structure of a C program. We looked at variables, we look at comments, we look at function, we look at blocks, loading external libraries, and others. This is a good point to stop and reflect. What have you learned? How do you feel about it as we're about to embark in the next phase of programming, where we look in depth into variables and other programming structures? You have seen already several data types in C. You have seen integers, you have seen floats and doubles, and so on. Now it's time to define the data type in a little bit more formal way as a mechanism for declaring variables or functions of different categories of data. What does it mean? It means that when you tell a computer that you want a particular label in memory to be used for floating point computations or decimals, it means that you are asking the computer to allocate you much more memory than, for example, would have been the case if all you had was an integer. It is important to recognize, as we'll see in the code right now, that C gives you a variety of choices for integers alone. Therefore, you have to be very knowledgeable about the requirements of your program, what to process, and match those data type with the problem at hand. For example, are you going to use a lot of very long, in this case, long means large, integers? You will have the long. Or your data is only managing very small numbers, in which case you will use short. Are you going to need very high precision calculators for long double? Or 6 decimal points is enough for you? All of these will come into place in the upcoming videos, where we will focus in depth on each one of those data types. Type of data it's supposed. Now that we covered some ground in terms of what types of variables to use in what instance, let's focus a little bit on integer types. As you've seen, there are a lot of them. One of the main things to know about integer types, other than there are lots of them, is how much memory do they take and what is their range. This way you can make a clear determination whether one type is more appropriate or another. For example, if all you care about is numbers between, for example, minus 128 to 127, then the sine car is the most appropriate option. However, if your range expands beyond that, you may want to go to a full int. By the way, car is not just short for character, it is actually an integer type. Another example are larger integers. For example, the short, which is larger than the car from the previous slide, it's 32,000 on the right side, all the way down to negative minus 32,000. The unsigned long goes from 0 to over 4 billion, and it's one of the larger available. If you know what type of problem you're going to solve, if you know what type of numbers your program is going to generate or need to handle, then you can match the memory requirement to that problem at hand. This way you can optimize memory usage, save time, and make your program run more efficiently and faster. Let's look at the code that will give even more information about what we can do when we talk about variables. This program shows you, in a very simple way, the ability of C to display the size of each variable using the function that's already built in the C language called sizeOf. All you have to do is simply use the output of the function and give it as an input the type you're looking for. What the program will do will tell you the exact amount of memory that this variable size or data type it's going to take. So let's run it. Okay. So as you saw in the previous table, this is now possible in code. For example, you can see the storage size for an int, the fourth line, is 4 bytes. The storage size for a long variable is 8 bytes. This means that your program may run unchanged if you use long or int as your integers. However, it will take twice as much memory. This is especially true if you have a lot of data, you save a lot of data, you store a lot of data, and you process a lot of data. In short, the wrong choice of a data type may cause your program to run up to 8 times as fast if you compare the unsigned long with a car, or even in the case of a short, which is 2 bytes, versus a long, which is 4 times more memory. So be very careful, use memory carefully, use memory efficiently. Older generations of programmers always complain that they don't have enough memory, the computers were too slow, but guess what? They were a little bit better than us today because they knew how to program with constraints. Today's programmers just assume that every generation of computers that's coming is going to have more memory, they're going to be faster, so why worry about saving and cutting corners? But that's not the case, because as memory gets cheaper and faster and there's more of it, programs get more sophisticated and people always want to do more. So there's never been a situation where you had too much resources. On the contrary, we're still complaining that we don't have enough memory. If you match the memory careful, you can mitigate the problem. You cannot eliminate it, but at least you can do the best you can. We just finished discussing integer points, how much memory they take, the range of usage, and so on. Let's have the same discussion on floating point and see some of the differences in size and requirements and capability once you move from the world of integers to the world of decimals. Let's start with a float. A float already starts at 4 bytes, and it only goes up to 8 and 10, whereas if you recall, the long int was the largest one at 8 bytes, and you had int as short as 2 and 1 byte. Let's just look at the store range. Notice that float is listed at output precision of 6 decimal places. This is only what you see on the screen. Internally, you see the range goes from 1.2 times 10 to the minus 38, or 3.4 times 10 to the 38. This means 38 digits past the decimal point. The long double is a staggering 4,900 digits past the decimal point. Let's take a look at the code and see how this transpires. When you write code involving floating point calculations, there's another thing you have to be mindful of. The precision, it's not just memory, but it's also a usability issue. Let's look at lines 27 through 29. I'm performing a very simple calculation. I'm dividing 2 by 3. So, it should be about 0.666, depending on what precision you want to. So let's see what is the difference between performing those operations in the case of using float, double, or long double numbers. Let's run this code. If you look at the size of the variables, the data type float, double, and long double are 4, 8, and 16 bytes respectively. We use the same size of function that we use to assess integers. Now let's look at the precision at 4 decimal points, and then I will show you how did I come up with this precision using the printf command. If all I'm interested in 4 decimal places, on one hand you could say it doesn't really matter if you use float, double, or long number. However, knowing that internally long doubles are stored with 4,900 digits beyond the decimal place, and knowing that 2 divided by 3 never ends, it's a sequence of 6s that never ends, there is no point in using a long double number if all you want is 4 decimal. There's no need to store 4,900 of them. Let's go further and look at what happens at the precision of 10 decimal points. Now we started to see something interesting. The numbers are no longer the same. Double and long are equal because they have a higher precision in calculation to floats. So you have to make a decision. It's not only about memory saving, but it's about how correct your results should be. If you are dealing with prices, stock information, trends in markets, and so on, you probably don't need that many decimal points anyway. 4s are plenty. But if you're doing computational biology, physics, science, trajectory of rockets, you really can use all the precision you can get. If you go further down, let's look at what happened with the precision at 30 decimal points. Well, a float number is not even capable of getting any kind of accuracy beyond 7 or 8 digits, where the double and long double keep going forever to some extent. You know that when you divide 2 by 3, in theory, they should be an infinite sequence of 6s. At the very end, when you finally choose to round it, it should be a 7. So how come those numbers are very, very different than those 6s? We'll get into this probably in a different course when we'll get into the mathematics behind those calculations. For now, it suffices to say that all you have to know is the memory size each float or integer requires and what type of memory requirements your solution in hand needs. We have talked a little bit about integer sizes, the variety of integer type available to you, so let's do the same for float. You already see, just looking at the size column, at 4 byte, 8 byte, and 16 bytes, floating type take a considerably more amount of memory than integers. If you look at the store range size, just look at the long double, a staggering number of decimal points, 4,932 digits past the decimal point. Unless you really need to calculate things that are extremely demanding in terms of their precision, you probably don't need to use long double. Why would you use a long double if you can use a float that still gives you 6 decimal places and stores internally 38 decimal points and only takes a quarter of the memory than a long double has? Let's talk about nothing. The void type is a type that has very different uses across different programming languages. It's not unique to C, but it's very important because it does a lot of things in the background and prevents a lot of problems from happening. First of all, it specifies that no value or no data is needed. It is a data type, but it's not in the same category as int or float or double. It doesn't really apply to variables, because why would you use a variable that has no data? But it does apply to functions, as you will see in a few seconds. Another reason why you would use a void type is add clarity. Sometimes you need something not to happen, or you want to specify that the function doesn't require any additional input. By specifying void, you're creating clarity and avoiding somebody thinking that you have simply forgotten to type something. You probably noticed, but didn't pay much attention to the fact that the main function in all the examples we've seen so far has a void in parentheses. What this means is that the main doesn't require any additional input for this program to run. If you look at line 14, that's a prototype definition of a function that says 2 things. First, it tells you that this function may be doing something internally. However, it doesn't require any additional values of variables. For example, like the function we saw that adds two numbers. It doesn't do anything to data, and it doesn't return any type of value. So that's the void. On line 19, there's the only time you would use a void as a type in a variable. This type of variable is one that is often used in C. We will gradually learn to use them. They are called pointers, hence the notation PTR. At this point, I just wanted you to see an instance where void might be used in the same way you use int or float before. Once you learn when to use void and how to use it correctly and how to avoid using it incorrectly, you will go one step further towards mastering everything there is to know about data types in C. If you like puzzles, you're probably using Boolean types without even knowing. If you ever hit a keyboard, if you ever do anything on a computer, you are instructing the electrical circuits inside the computer to switch a value from 0 to 1. Anytime you switch a value from 0 to 1, and those are the only type of value a variable can take, this is called a Boolean variable. The word Boolean comes from George Boole, who is the inventor of Boolean algebra, Boolean logic circuits, and so on. As I said, they simply denote a value of being true or false. For something so tiny, the entire computer industry is built on them. However, despite them being so important, Boolean types are not defined in standard C. But there are workarounds. Like with everything in programming, be prepared to find ways to do things that otherwise are not either explicitly defined or not possible at first glance. One is true, which hints that if we ever want to use the Boolean value true, we simply would use the number 1. Conversely, if we want to refer to false, we can simply use the number 0. In fact, the information in computers is stored as ones and zeros, and everything we do as computers is actually Boolean algebra. Let's see how this works in code. Notice a second or a third library called stdbool. This is a standard Boolean library that has been added to C99, which is the previous version of C before C11. It is not part of the original C. For the original C, you have to do something like in line 20 and 21, where we simply use the define processor directive to say that true is 1 and false is 0. Notice on line 19, there's a new command called typedef. We are defining a new type, bool. We're not really defining a new type. We're simply saying that bool is an int. This is mostly for clarity, so that if you want to define a variable later on and don't want to use int because you want to draw attention to the fact that this is a different type of variable, you can simply say typedef int bool, which means I'm redefining bool to simply be int. Once we did that, we can use on line 25 bool, a Boolean variable. This means that it's just an int, but we will be sure to assign it only values of 0s and 1. For example, we can say on line 26, a Boolean variable equals true, because on line 20 we defined true equals 1, and on line 25 we declared a Boolean variable to be of type bool, which is actually an int. So all we said that this is an integer who is assigned the value 1. But for clarity, this is the workaround that makes us feel as if we're working with explicitly restricted Boolean variables that can only accept 0 and 1. Let's print that by running the code and see what happens. Unsurprisingly, the value of a Boolean variable is 1 because we assign 1 to it. Once you get more comfortable with voids, with Booleans, with the sizes of integers and float, you will be able to make a very clear determination about which type of variable is most suitable to a given situation. Notice that there are workarounds that are not just computational, but mostly semantics. This should give you an idea of what's possible. Try to think out of the box. Maybe you can come up with your own types of variables, maybe with your own words for them. Maybe there are ways to define certain things that will help see a problem in a different way and make it easier to tackle. All of this is possible, and we will see in the next video how. Strings. You may have noticed that we discussed several types of data, integers, floats, and so on, but we haven't mentioned a type called strings, even though we did use strings and they're very prominent in any programming language, in particular in C. In C, strings are defined as a series of characters, such as this particular one. There is no string type per se in C. Rather, strings are just stored in arrays of type char. Like in the following definition, we are defining the type of an array to store, for example, 30 positions. Each one of those positions is a string. In a more formal definition, we're still not entirely covering the topic of arrays officially, but you can refer to them for now as a sequential collection of elements of similar type. In our case, that type is character. So let's look at an example of a string in C, which has 32 characters. As you can see, I'm labeling those starting from 0. It's very important to remember that each time we deal with an array and with strings, we start with the first character being labeled as 0 all the way to, in this case, to 32. Let's see how this is actually implemented in a C program. If you notice that this definition, the character on line 17, the character type of the address 30, is being assigned a string, can be anything of any length. However, notice that the number of characters in the string is larger than 30. We will see if there's an impact of that. So I'm allocating 30, I'm instructing the compiler to allocate a sequential collection of characters, which I am labeling address, and I'm storing something starting at position 0 that's labeled address. Then, in a second example, I'm defining another string called name, which has fewer than the number of characters I explicitly instructed the compiler to allocate. Let's run this code and see what happens. As you can see, there are two warning messages. One message is on line 17, and it says that string for char array is too long. So this is a warning. It's not necessarily an error. Remember, C assumes you know what you are doing, so it doesn't prevent the program from running. It doesn't do anything with the screen at this point. Nothing in the processing of the strings is affected. The second one still has a warning. However, this is a different type of warning. It just tells us that we declared that string and we haven't used it. So this string is perfectly fine to allocate more than you need, and often that's the case. This one gives you two errors, both for not using the string variable and for allocating it less than what it needs. So far, we have seen a simple example on how to use strings. In the subsequent videos, we are now going to get deeper into string manipulation. Now that we know what strings are and how they are stored, let's see additional uses for a string when it comes to interacting with a computer via the screen, what we call input-output. What is input? It's essentially a series of bytes of data that are entered via the screen, keyboard, or network. Each time you type something on a network, the information travels from computer to computer. You type something on a keyboard, the information is going from your keyboard onto the computer, and it's being stored somewhere in memory. The computer, the compiler, the language, that's a whole system that is tasked with processing the data that you are entering. Conversely, when the computer wants to present data to you, it sends a stream of bytes from memory to a device. Most likely, it's going to be a screen, but often can be a printer or some disk or another storage device. C provides a standard input-output library, which you already see included in your C program called stdio.h, and it has a function that allows you to input and read information to and from the screen. Let's look at some of the main functionalities of the input-output system in C. We have one command, which we have used already so far in this class, provides powerful formatting features to display multiple types of data on the screen. Please recall that we looked at doubles, floats, and ints by providing different directives to the printf command. Scanf is the counterpart to printf. It's the main vehicle, not the only one, that provides you the mechanism to read data from the screen into the computer memory. Both scanf and printf offer broad conversion capability across data types, which means you can read one type, format in a certain way, and then forward it for storage in a different way, as we will see in the upcoming videos. Let's look at this program. Notice in line 11, the include stdio.h. This instructs this particular program to use the external library that includes all the standard input-output features. Also notice on line 16, we have defined two characters arrays, which are name to hold 20 locations and address to hold 30 locations. Let's see what are we going to do with those. Lines 18 through 20 are the essential way to prepare the computer for communicating with the user. First, look at line 19. 19 prints a message to the user instructing the user to choose a number. Line 20 uses a new command called getChar, which, as its name implies, asks the user for a character. Recall from our discussion on various data types that character, it's actually an integer, despite its connotations to being a letter. The character that's being captured by the function getChar is simply stored in a variable C, which is defined in line 18 of type character. Line 19 provides the means for you to communicate to the computer a number. That number will be stored in the computer memory. Similarly, line 20 and 23 instructs the user to enter an additional string, except now in line 23, we're using a new command called scanf. Notice that the scanf directive %s and then the variable name. Line 16, we declared an array of size 20 called name. We are now using this array. However, recall that that array is a beginning of a string. When you're using scanf, we don't have to give it the entire 20 spaces. All we have to tell scanf is there is such a thing called name. It starts at a particular label, and the ampersand side preceding the letter N in name is another directive that the compiler understands that this name is actually an address. It's a labeled location in memory in which the string entered in response to the request in line 22 will be stored. Let's run this program and then we'll go back to the code and learn some more of what it's doing. As evident from line 19, now I'm required to type something, and I'm required to choose a number between 1 and 5. I'm going to choose 3. Now I'm expected to type in a string. I'm going to type my name, and I'm going to type my address. I'm just going to make something up. And the computer diligently replies back to me everything I typed. My name, the address. However, notice that it didn't put the entire address that I enter. Why is that? Notice that there is a space between 123 and some street. Whenever the scanf command encounters the space, it assumes I have finished entering my input, and therefore it ignored everything that comes after the space. Gradually, we will improve our understanding of how printf and scanf work, and we'll be able to create more powerful interactions between user and computer. Line 25 and 26 are similar to line 22 and 23 in the sense that they ask the user to enter a string value which will be stored in an array starting with the label as indicated. Finally, line 32 is the putchar command, which is the counterpart of getChar. Essentially, the value stored in the C variable is now being displayed back to the user. So far, this code presented a very simple, elegant way to ask the user to provide numeric, textual input, storing it in memory, whether it's a variable or an array of strings, array of characters, and then displaying it back to the user on the screen. At this point, we're going to advance our discussion on strings, and we'll look at some of the libraries that the language C provides us for string manipulation. There is a special external library we haven't seen yet called string.h. This library includes a series of functions that are very essential in the string handling. One of those functions is string compare. It allows us to compare the value of two strings and returns a number, which we will see shortly in the code, that would indicate whether the strings are similar or not. Another useful command is string copy, which is useful to copy a string onto another. Recall that if you want to copy the value of a variable onto another, you simply say, for example, x equals y, and then the value of y will be copied onto x. Since a string, it's not really a variable, but a collection of multiple memory locations, each one of them is a car, we need to process string copy a little bit different because a string is not just a simple variable. We are taking a source, shortcut here, src, taking all those positions that start at location source and copying them onto another location starting at the label called destination, or dest for short. Another interesting function allows us to copy a specific number of characters from source to destination, not the entire one. Finally, another useful function, string len, which simply gives us the number of characters in a string. There are many, many commands that'll help you manipulate strings in C. Those are just 4 out of about 24, which later on you can look up the string.h library and see which one is appropriate for your project at hand. Let's see now how this works in code. For the purpose of this assignment, we have now defined 2 character, string 1 and string 2. Those are character type that define 2 arrays, which we decide to call string 1 and string 2. Let's look at a few scenarios. Scenario number 1, we are going to copy the string anybody in C to a variable called string 1, which is defined as an array of 20 positions, each one being a car. The second one will copy anybody home into string 2. So we are now have initialized 2 string variables or arrays of characters, one having the value anybody on line 21, the other one anybody home on line 22. We will proceed now with calculating the length of each of those strings. Recall the string len is the function defined in the standard library as the number of characters in a string. If you were to count them, anybody has 7 characters and anybody has slightly more. The value computed by the built-in function strlen is an int, and it's being captured in a variable len1. Notice that I defined that variable len1 as being an int and assigned right away a value. In some instances, we do not have to define or declare the variable ahead of time. We could just declare it when we need it. Line 25 prints the length that has been returned by string len string 1, and we proceed with doing the same for string 2. We have 2 more scenarios. Notice that in scenario number 1, string 1 was shorter than string 2. Scenario number 2, string 1 is longer than string 2. And in scenario number 3, the strings are identical. We are in each scenario using another function called string compare, that's strcmp, for example, in line 52, that compares string 1 and string 2. Let's see how this works. Scenario number 1, string 1 was shorter. In case of a shorter string, obviously they are not equal. The return value is 32 negative. When string compares returns a negative number, a positive number, or a 0, these are the clues for us as the result of the comparison. When the first string is shorter, we get a negative result. When the first string is longer, we get a positive result. When the strings are identical, we get 0. It is not enough for the strings to be identical in length. They might be identical in their characters as well. So actually, string compare provides us with 2 pieces of information. One comparing the length of the string, the other is comparing their content. Those are just a few of the many string manipulation functions which are available in C. As we progress with our understanding of the C language and all the powerful things it can do, we will use an increasingly larger number of such strings, as we will see in other libraries that serve different purposes. We have talked about variables quite a lot in all the preceding videos. Let's pause and think a little bit deeper about variable names. One good tip for every programmer is to use names that mean something. For example, height, length, locus, rather than simply X, Y, L. Another convention, which is not a rule, it's simply a convention, is to use camelback notation. Take a look at max name length to the left versus max capital N name, capital length. Which one do you think is better? Obviously, the one on the right, which is called camelback notation, due to the humps created by the capital letters, it's immediately readable. There's nothing wrong with either one. It is simply a convention and will make your code easy to understand, easier to debug, and will help you identify potential errors later on. Let's see how it looks in a C program. This program doesn't produce any output. It's simply a placeholder for our discussion on variable names. Let's look at line 20, 21, and 22. We have defined three variables, x, y, z. Each one is an int. Do you think these names are appropriate? Well, maybe, maybe not. It depends, like with many things in programming. Hold that thought, and we'll finalize our answer in a few seconds. Let's look at line 25 and 26. We have defined two variables. They're both arrays of characters, my last known address and my last known address. One is not camelback, one is camelback. Are those variable names appropriate? One thing to note is that everything in C, as in most, not all, programming languages, is case sensitive. Therefore, the array in line 25 and the array in line 26 are two distinct arrays. They may sound as they have the same name when you pronounce it, but they're not. There's another reason why you would be required in any professional environment to adhere to that particular environment notation convention. Throughout these videos and this course, our convention will be camelback notation. This means line 26 is the preferred notation to line 25. If you adhere to the same convention consistently throughout your code, you are less likely to make mistakes. Let's go further down and examine two functions. In line 33, we have defined a function called cube dimension that has three internal variables called x, y, and z. And they are double. Well, recall that question we had at the upper portion of our code where we asked, is x, y, and z appropriate at that location versus line 35? It's not a simple answer. Obviously, when you talk about dimension of a cube, it makes a lot of sense to refer to those dimensions as x, y, and z because you will be dealing with coordinates and so on, and this is a typical language you would use in geometry or in algebra. Therefore, in such a situation, it is perfectly fine to use just x, y, z. Line 20 through 22, it is not clear what those variables are, and therefore they're subject to interpretation. The bottom line, when in doubt, add an explanation as to what those variables are intended to do, why are they labeled the way they are, to eliminate any possible confusion. Let's examine this further. Recall the my last known address in line 26, and look at line 38. We again use the word my last known address, spelled exactly as in line 26. Is this the name of this function appropriate? Well, again, it depends. Technically, you are allowed to name a function the same exact word as a variable. There is absolutely nothing in C to prevent you from doing so. But is it smart? Are you in danger of being confused? Is someone else likely to be confused when looking at your code and wonder, have you made an error? Or there is a reason behind you doing so? Just like with the previous example, make sure you explain your intent and you communicate it either via comments or simply use different notation. You may want to insert the word function next to my last known address or a comment to avoid further misunderstandings with other people or even with yourself later on when you come to re-examine this code. Finally, word of caution. Before you use variables in your code, especially if you're going to have a lot of them, think, have a plan, make sure you know what each variable is intended to do. It's often a good idea to list all your variables at the beginning of your code with a comment line next to them, so there's absolutely no doubt as to your intent and what are you planning to do with them. Let's continue our discussion on variables. So far we saw different ways in declaring variables. Now let's talk a little bit about when and where it makes the most sense. You already know that variables must be declared before use or the compiler will not understand the meaning of your code. Now you have a few choices. You could declare your variable all in one place. This will make, in some cases, the program more readable and will give you an opportunity to create a header at the beginning of your code detailing all the variables and listing their intended use. Additional option is you declare them as you need them. If you're only going to use a variable in one place, in one small portion of your code, it might make sense to declare the variable right there. Finally, you could declare all your variables in an external file and use include with a .h and .c pair of files, just as we saw with functions. Let's take a look at the code and illustrate this in action. This particular program uses, as you can see, multiple types of variables declared in multiple places. So let's take a look. We have an int x, int y, and int z. This is simply an example, as we saw in the previous video, that you could group together a few variables and have them all in one place. There's nothing particularly important that this program does. I just wanted to illustrate to you the fact that you could put them in one place or not. In line 20 is it where we use all three. Let's take a look at line 23 and line 24. In this particular program, the variable a is only used at that particular position. So it makes sense to define a right before I'm using it to get car and return a value. The same goes for b and the same goes for c. It would have been perfectly correct and perfectly fine to declare x, y, z, and a, b, c, all six of them at the beginning of our program and then use them as needed. Ultimately, it's up to your personal style, the conventions in place at your professional location, and other considerations such as style, who else you're working with, and so on. You will eventually develop your own preference, your own style, and you'll figure out what works best for you and it's most appropriate for the project at hand. Let's look at line 35. First of all, you would notice that it doesn't exactly fit on the screen, and it's not clear right away what this line is supposed to do. Careful reading reveals that we first declare a double xx 2.3, then a double yy 1.2, then a double zz 2.3, then we are printing the value of xx, then we have a comment, then we have another print, and so on. This is actually perfectly correct in C. If you're trying to deliberately make code harder to read, harder to debug, harder to understand, even to you, if you should come back to this later, then by all means, go ahead and write code like this. Let's test this code and see what it does when run. Notice that there is no prompt. This is because on line 24, getCar simply expects the user to enter something without any prompt. Knowing that, I'm going to type a number 1, enter, and the second one. And now I'm getting to the output of the program. As you can see, this particular program, variables were declared in a very, very messy way. They're hard to read, and they probably impacted the programmer's ability to think efficiently about displaying the results. The output, as you can see, it's also very hard to read. Note, there is no relationship between how you write your code and how your output is presented. You can write code that is very messy, very hard to read, and yet the output could be very easy. For example, if I were simply going to reformat the printf, we can get a better outcome. However, it is not necessary for this example, as we will have plenty of opportunity to practice in the upcoming videos how we can improve the formatting of text on the screen. To recap, our discussion in this video is you can declare variables in multiple ways, in multiple locations. You can make your code easy to read or hard to read. You are the master of your code. Whatever you put in there, this is what other people will see. This is what you will see later on when you come back to look at it. It's ultimately up to you to write the best, most clear code you can. So far, we have discussed multiple topics related to variables, where to declare them, when, how to name them. Let's see how they're actually used in expressions and simple assignment statements. What is a simple assignment statement? It's a statement that, first and foremost, changes the value of a variable. We have to do that following certain rules. Most instances will be dictated by the mathematical nature of an assignment statement, which is the case with C because a lot of programming in C is meant to provide solutions in areas that are mathematics related. For example, size equals 12. We simply say that the variable size will be assigned the value 12. Or time equals time plus 1. Notice that the right-hand side of this equation and the left-hand side both use the variable time. This is perfectly fine. We simply say, take the original value of time on the right side, add 1 to it, and store it back as a new value for time, which is now incremented by 1. There is a simpler way to accomplish the same thing in C, which is a shortcut notation, simply states time plus equal 1. You may as well write time plus equals 5, time minus equals, and so on. Finally, a more complex formula, for example, would be final price equals original value plus tax minus discount. This is still a simple assignment statement, and we will gradually ease our way into building more complex ones. Let's see how this is done in code. We are first declaring several variables and initialize them. Notice one other thing. C is actually running on a very powerful laptop, personal computer, Mac, or Windows. They are much more powerful than the pocket calculator. In fact, if you have some experience with math and improve your knowledge in programming, you can duplicate and even expand beyond anything a simple calculator and even the most advanced graphic calculators can do. So this is a simple illustration of that. Let's look at an example from the financial area. We are declaring 4 variables: original price, tax, and discount. And the plan for this example is to show how can you calculate the amount of tax and discount and a final price to a customer. First, we're going to ask the customer to enter the original price. Then we'll ask the customer to enter the percentage of tax, discount percentage, and based on that, we will calculate the final price. In this particular example, I chose to simply say, let's first calculate the after-tax price, which is a simple mathematical formula some of you may have known. If not, here's a quick refresher. You simply multiply the original price by 1 plus the percentage of the tax you entered. Then, to get the discount, in this particular example, I decided that the discount is applied to the original price. So I'm using the original price as my base, both for the tax and for the discount. When all this is computed, on line 36, I am now able to calculate the special price, which is simply the price after tax minus the discount. Finally, in line 38, I am printing out the rules for the user to know how exactly I calculated that, not the formula, just the main idea. And then I proceed with formatting. Notice a few new things about the printf command. Look at line 40. First of all, I am printing a $sign right before the number because, after all, I'm dealing with monetary values. Second, notice after the percent, there's a dot, and then 2, and then LF. The LF you have seen before is simply denote that original price is a double. The dot and 2, it's another indicator to the printf command that I'm only interested in displaying 2 decimal points. After all, we're dealing with money, and money have their own characteristics when being displayed. We expect to see a dollar sign, and typically we expect to see 2 decimal digits. Let's run this program and see what it does. First, I'm being asked to enter a price. I will enter 100, so it's easy for us to track. The sell percentage, in my case, I decided that the sell percentage would be 8. And the discount, let's say I'm going for a modest discount of 5. The program indeed prints the rules. The tax are applied first. The discount is applied to the original price. And notice that I'm displaying the price after tax is 8%, which is $8 out of 100. So we know the calculation is correct. The discount amount is $5 because 5% out of 100 is 5. Therefore, 108 minus 5 yields the final special price of 103. Let's run this one more time with different values. I'm still going to put 100. I'm going to add a ridiculous tax, 400%, and an equally ridiculous discount. The computer doesn't know that those numbers are ridiculous. Only you know that. So the computer will simply take your numbers, put them in the formula, and give you the result. The original price is 100. The price after tax is 500, and so on. Let's do one more test. This time, I will type something that I know for sure is wrong. I'm going to type a sales tax percentage of 20, but a ridiculous discount of 1,000%. Let's see what happens. Well, as expected, remember the term earlier, garbage in, garbage out? Well, now my special price is negative. If you enter a negative number, this means that you are actually expected to be paid money back. Again, the computer doesn't know any of that. The computer simply takes the numbers you give it, plugs them into the formulas that you coded, perform the assignment statement, and display the result. It is up to you to ensure that the input is valid, the values make sense, and there are obviously mechanisms in C that will let you do just that, as we will see in our next videos. We just finished looking at basic assignment statements, so now it's the right step forward to look at arithmetic operators and see how we can create more sophisticated mathematical calculations in C. C defines a series of operators as follows: addition, subtraction, multiplication, division, modulus, and then 2 special ones, increment integer by 1 and decrement integer by 1. Those operators work exactly as you would expect coming from algebra or calculus. The increment and decrement are not commonly found in a typical mathematics class, so we'll see how useful they are in a C program. This is an example of usage of multiple operators, and we'll see how they can be used to perform some calculations, simple at first and increasingly complex later. We are defining 2 simple ints, 5 and 7 in line 22 and 23, and a series of variables, sum, difference, product, etc., that will store the results of those calculations. We have already seen in a previous example how to calculate percentages and do a simple multiplication. We'll just take this one step further and point some things that are particular to C, and there are very important details to consider when you create more complex programs. We are simply going to take each one of those operators, perform it separately, just so you can have an idea what they do and how they work. And this is pretty simple. Line 26, we simply add x plus y. Line 30, we're adding x minus y. And then we are printing the result, and so on. Line 33, we are multiplying. The star is the symbol used in C for a product, division, and the modulus. This simply gives you the remainder if you divide x by y. Those are simple. They work exactly how you would have expected with basic knowledge of algebra. It's more important to focus on line 42 and line 45. It is very important to notice the position of the plus plus sign and the x. If you place the plus plus before the x, this means that you are incrementing and then you are using the value. 45 means you're decrementing and then you are using the value. And we will note those differences shortly. We will look at some code in line 50 that will illustrate how the increment works and what is the meaning of increment first, use after, or first use the variable and then increment it. The best way to understand this is simply run the program and then look at the code. Let's scroll all the way up, and I will look at the code in parallel with its output. We have initially assigned in line 22 x to be equal 5, y to be equal 7, and indeed our output shows that. Then we're displaying the sum, the difference, the product, the division. Notice that the division is 0. Why is 5 divided by 7 0? The reason is we define those as integer numbers. When you are defining all variables as integers, their value is rounded up to the nearest integers. Since 5 divided by 7 is a fraction that starts with 0 point something, when this is truncated, then the division result is 0. Everything else works as expected, so let's focus on the increments. If you look at the increment in line 42, this is the result displayed here at the increment value of x equals 6. Originally, x equaled 5. I incremented x, therefore its new value is 6, it is displayed. Then I decremented x by 1, and now its new value is back to 5. So far, so good. Let's take this one notch higher. In line 51, which corresponds to this output here, line 51, I am assigning 1 to x. And notice that the plus plus symbols are to the left of x. When I'm now printing the value of x in line 53, the result is 2. In line 54, I'm printing again the value of x, but note that the plus plus signs are to the right of x. This tells the C compiler, use x and increment its value by 1. Therefore, when I print x at 54, I'm still printing its original value of 2. When I print x again in line 55, x is now 3. So line 54 did two things. It printed the current value of x and incremented it, but that increment was not reflected in the print. It's only in the subsequent use of x that you saw the results of it. We will now do the same thing with the decrement operator. Again, in line 59, I will assign 1 to x. I will decrement it by 1, and then print it, and as expected, it's 0. Then in line 62, I'm going to decrement it again and print it. However, the decrement is after the x, which means use the value, which is currently 0, print it out, decrement it. In line 63, I'm now displaying the new value of x, which is decremented by 1, and now x is -1. To recap this concept, all you have to remember is if the symbols of addition or subtraction are before the variables, they're executed first, and then the variable is assigned the new value in whatever formula is being used. If the symbols are written to the right of the variable, this means that the variable is used in its current value, and then it is incremented or decremented based on what the symbol is. We are now proceeding with learning about a different type of operator, which are called relational operators. They are not very different than what you are used to in algebra, but in C, they take an additional meaning, as we will now see. A relational operator It's also called the logical operator because it enables you to make a logical inference. For example, when you look at group 2, you are asking, is a value bigger than another value? Smaller, bigger, or equal? This is a result of a logical inference. Those are the obvious ones, and they should be known to you from algebra. A slightly different type of operators, still in the same category of relational ones, are in group 1. The exclamation mark simply reverses the logical value of an operator, meaning if it was true, it is now false. If it was false, it is now true. The logical equal simply asks, are two values identical? Conversely, if you combine the not with the equal sign, you're asking, are those values not equal? Finally, group 3 is the one that's most different than what you are used to in algebra. This one is called logical and logical or. You're essentially saying this: if two conditions are both true at the same time, the outcome is true. The logical and requires that both items compared would be true. The logical or will simply say, if one of those conditions is true, then the result is true. The best way to understand is this, to put it to work in a C program, as we will now see. In this program, we will take an in-depth look at each one of the relational and logical operators. First, let's recall that 1 is logical true and 0 is logical false. Now we can proceed. We are going to use two numbers. They could be any numbers, and they will suffice for us to understand how this operator works. Let's look at line 32. X is 3, y is 12. We are now asking the compiler to evaluate the truth value of the expression x equals y. We are actually asking, is it true that x equals y? This is what line 32 does. It does actually more than that. It looks at the expression x equals y as being evaluated for a true or false value, and then it displays the result. We could have done it in a separate step. We could have collected that result into another Boolean variable and display the value of that Boolean variable. This is an illustration of a shortcut and how C can help you simplify the way you treat relationships and expressions. Line 33 does the same thing, except now we are evaluating the truth value of the expression x does not equal y. We are expecting that the result of that to be true or 1. We can continue now. In line 34, we are evaluating whether x is bigger than y, then whether x is less than y, bigger than, less than, and so on. Let us run the program, and we will look at specific outcome of each one of those lines. The first line is comparing x and y, and the result is 0 because it is false to say that x equals y. So the expression in parentheses, x equals y, is evaluated as one result, one numeric result, in this case Boolean, and the outcome of it is 0. We do not have to specify anywhere that we are dealing with a Boolean or a logical inference. The built-in logical inference mechanism in C displays a 0 or a 1 to reflect whether an expression is true or false. Let's continue. For x equals 3 and y equals 12, it is true to say that they are not equal. Therefore, x does not equal y yields the logical result 1. 3 is definitely not bigger than 12. Therefore, on the next line, it is false to say that x is bigger than y, but it is true to say that x is less than y, as finally, x is true to say that it is less or equal to y. This concludes the first portion of this exercise, in which we are comparing the logical value of operators that you have maybe become familiar with in a previous algebra course. Let's look at different ones and the one that may seem a little bit different when processed in C. Line 42, we are asking to evaluate the expression x and y. What this means is, if x and y are both true, then the result is true. For this particular section, I used different values of x and y, 1 and 0. 1 denotes true, 0 denotes false. Therefore, true and false cannot yield a true result because both of them need to be true in order for the total outcome to be true. And indeed, when we ask C to evaluate x and y, the result is false. When we ask to evaluate x or y, the result is true, because OR simply requires that one of the evaluated x or y to be true for the final result to be also true. And finally, we apply NOT to x. Since x is 1, the inverse of x, or the NOT value of x, is 0. This is not algebra, this is Boolean algebra, and it reflects the fact that C is a low-level language that also handles assembly-level bit operations, as we will see shortly. Recall that 0 and 1s are not just their arithmetical values that you are accustomed to, but also denote a logical meaning. A bit of 1 is true, and a bit of 0 is 1. We will see more on the discussion of bits and bytes as we progress, and you will be exposed to even more powerful language constructs and ability to calculate even more complex relationships by mixing together arithmetic operations, logical operators, and create very sophisticated inference engines. Let's look at an application of logical operations. Namely, let's build a simple decision-making support system using those logical operators. Recall that the logical operators we covered so far in C are AND and OR. Logical operators can be used to make decisions. We are going to leverage the fact that 1 equals true, 0 equals false, and we'll create a set of data that, when placed into a formula, will apply some logical operations into them, such that the end result of that formula calculation would be either true or false. And based on that, we'll make a decision. What this will enable us to do is to build a query system to assess outcome given a set of conditions. In other words, we will ask the user a few questions, we'll put the answers in a formula, and we'll produce a result. Let's see how this works in C. We have several variables that would be the ones that we're asking the user to enter values for: weather, readiness, supermarket, minivan, wagon, mood, and decisions. If we haven't guessed yet, we are going to ask the user to enter some questions regarding the possibility of going onto a picnic. The picnic, readiness, and supermarket are two variables that go hand in hand. The idea is that you're either ready for the picnic or you'll buy stuff at the supermarket. The minivan and wagon also go hand in hand. You will either use a minivan or a wagon. The weather, it's another major factor. So is the mood. Our idea is as follows. All the conditions must be true. This is the logic. In human speak, all the conditions must be good in order for the picnic to take place. In other words, we need the weather to be good, then we need either readiness of supermarket and either minivan or wagon, and the mood. The following set of statements, line 25 through 37, are simply the ones that are asking the user to enter some input to a survey. For example, we will ask the user, what is the weather outlook? 1 is good, 0 is bad. If the user enters 0, it invalidates the entire logic, which means we will not be able to go on with our picnic. We will capture that in a variable called weather. Then we'll ask about readiness and the supermarket. If both of them are 1, that's fine. However, we only need one of them to be 1. So goes for minivan and station wagon and the mood. Let's take a look at the formula, which is at the heart of this system. We have a variable called decision, which is an int that will store the result of the calculation based on Boolean logic. For example, we have the weather, which is either 1 or 0, and now the next expression is readiness or supermarket. If one of them is 1, meaning true, then the value of the entire expression, readiness of supermarket, is true, or 1. The next expression is minivan and wagon. If either one of them is 1, then the entire expression is 1. And finally, the mood. Therefore, we created a formula that requires certain factors to be 1, and other factors give us more than one option, and it's enough that one of those options is 1. Let's see how this works. The first question I'm asked is the weather outlook. So let's say the weather is good. Picnic readiness. Let's say I really don't feel ready for the picnic, so I'm going to enter 0. Is there a supermarket? Just in case. Luckily, there is one. What is the minivan condition? Not that great. I'm going to put it bad, 0. What is the station wagon condition? Just in case. Well, it happens to be good, so I'm going to put a 1. Finally, the mood is 1. Now the verdict. Under this condition, the decision is 1. Because in each of the pairs that has an OR, at least one of them was 1, and in all the others, I had to put a 1. Let's run this one more time with slightly different conditions. Weather outlook, great. Picnic readiness, great. There's even a supermarket as a backup. The minivan condition, really not that good. Station wagon condition, no station wagon either. The mood is great. Let's see the verdict. Is 0. Notice that the minivan and station wagon was both 0. At least one of them needed to be 1 in order for that pair to yield the result of 1. Therefore, the entire decision formula yielded 0. In this case, no picnic. In this video, we are going to talk about binary numbers and operations on binary numbers, because this is one of the unique characteristics of C, and it's not often discussed in other programming languages. We are calling those bit-level calculations because at their core, inside a computer, data is represented as binary digits, or bits for short. Some of the bit-level operators are AND, OR, and XOR, which is short for exclusive OR. Those operations should be familiar to you if you had some background with base 10 calculations, which are assumed to be part of your readiness for this video. In this particular course, we are not going to focus too deep on bit-level operations because this is an essential C. It's only brought in as an overview of the capability, and you are welcome to explore other courses that treat this in a deeper manner. The second group of bit-level operators are ones complement, which means we're going to switch all the zeros to ones and all the ones to 0 in a given number. And the other one is right shift and left shift, on which we'll talk a little bit at greater length shortly. First, let's have a refresher of the meaning of a truth table, and in particular case, the AND bit-level operator. What is a truth table? If you're not familiar with it by now, a truth table simply tells you what is the outcome of applying the operator to two values that can be either true or false, depending on the circumstance. For example, if both values are true, then the AND operator is also true. In some ways, there are parallels between the bit level AND and a product of two digits. For example, if you multiply 1 times 1, the result is 1. If you multiply 1 times 0, the result is 0. The same goes for bit level AND. True and false yield false. Only true and true yield true. In a similar manner, we can look at the truth table for OR. This means what would be the outcome when two operands are put together in an OR expression. You can again make analogies between the addition operation, although it's not the same as addition. True or true yield true. True or false yields true, and so on, as you can see in the table. Finally, there is a more interesting operation called exclusive OR, in which when both values are the same, either true or both false, the result is false. Exclusive OR yields true only if the two values are different. Let's put this to action in code. For that purpose, we don't have to do anything special other than defining certain variables. In this case, int is 1, 0, and y is 1. And let's see how we use them and what will be the result. Line 30 depicts the usage of a bit level AND. It takes the binary representation of x and y, perform a bit level operation, and displays the results as int. And so do the other following ones. If you look at line 36, this is the symbol for the XOR operator. Let's look at the outcome of those before we continue with the right and left shift. We'll run the program. The first three represent the outcomes of AND, OR, and logical XOR. If you look at the values being 1, 0, and 1, you can easily see the outcome of those operations if you know the rules of AND, OR, and XOR. It is more interesting to look at the right shift and the left shift. If you recall from your knowledge of basic algebra, in base 10, if you add a 0 at the end of a number, it's the same as multiplying that number by 10. For example, if you have the number 12 and you add a 0, it will be 120. If you remove the 0, it's as if you divided the number by 10. Well, in binary arithmetic, where we only have zeros and ones, the equivalent of multiplying by 10 or dividing by 10 in a base 2 is multiplying or dividing by 2. Therefore, when you right shift a variable by 1 bit, it's the same thing as dividing by 2. This is the same as saying in base 10, you have 120, you shift it to the right, you drop the 0, and now you just have 12, which would be the same as dividing by 10. Conversely, when you left shift, you take the value of y, shift it 1 bit to the left, it's the same as multiplying by 2. In base 10, you would say, I have the number 12, I'm going to shift it to the left 1 position, which will be then filled by a 0. If I add a 0 at the end of 12, it's as if I multiply it by 10. So now it's 120. In base 2, this is multiplying or dividing by 2, and then the result is converted back into decimal numbers. Again, the purpose of this video is obviously not to teach everything there is to know about binary operators, but just to give you an overview of what C can do in the area of logical bit level operators. Should you need to do this further, there will be other opportunity a little bit later in this course, but primarily in other courses that go deeper into processing data in binary using the C language. At this point, we're going to continue our discussions of operators, expressions, and statements in C, and we'll see increasingly more complex and more useful ways to calculate things. Let us recall what are complex statements. They're simply those that involve the use of multiple expressions. That's the only thing that makes them complex. Sometimes they represent a very complicated process of thinking that's being reflected in the complexity of a formula or a statement. Let's look at an example. We are defining 4 variables: init value, weight, k, and a flag, which will then be used in the complex statement at the bottom of the screen. Init value, it's very simple, an initial value of a variable, which we decided to be 0. Weight of 5 and k of 1 are meant to add to that variable a repeated number of weights based on the value of k. For example, if k equals 1, we are just adding 5. If k was to equal 2, we will be adding 2 times 5. And if you look at your expression at the bottom, you will see that weight is being multiplied by k. There are additional variables that are multiplying weight to the right and to the left. Let's continue our discussion on the left side. We are multiplying weight by k and incremented k by 1. So should we repeat that operation, k will now be 2, and so on. A flag does something very interesting in this case, and it's an example of combining both arithmetic and logical expressions. If you look at the declaration of flag, it receives the value after evaluating whether k is less than 10. If k is less than 10, the value of this expression will be true, thus flag would equal 1. If k is more than 10, the value of this expression will be 0, and thus flag will be 0. Let's look again at the complex statement. Flag multiplies weight and k. It can have only values of 1 or 0. Therefore, if k is equal or larger than 10, flag will be 0. Thus, we are preventing from adding to the initial value more than 10 times the weight. This is an interesting way of putting a top boundary on a value by simply defining a flag. Problems like this are easily solvable if you understand the meaning of truth tables, the meaning of logical inferences, and how to combine the two. Let's see how this is done in code. In our code, we are going to do several things to exemplify how this operation works. At first, we are going to define several variables, a, b, and c, with respective value of 5, -3, and 12, and then 3 floating point variables, r, s, and t. Let's start with simple calculations to illustrate complex expressions, and we will call this part 1. In part 1, we are multiplying a times r. It's a simple expression as a refresher. You can simply store the result in a float. Now we're doing something that we saw in our previous screen. We are multiplying a greater than b times c. In other words, we are calculating the value of a greater than b. In this case, if you scroll up, you will notice that 5 is greater than -3. Therefore, the C compiler evaluates a greater than b as 1. Therefore, the expression on line 35 becomes 1 times c, and then the value of c is being displayed. In the same manner, we can do a different calculation by using a less than b, which in this case would be 0, since we define a to have a lower value. In part 2, we are going to again play with the notion of incrementing a variable and then using it. In part 3, we will be using the variable and then increment it. Let's follow the execution of this code in parallel to looking at it. It will make things easier to understand. But first, in part 1, we simply printed the outcomes of simple expressions that make up a somewhat complex statement. The complexity is due to the fact mainly that we're combining arithmetic and logical operator. So the integer result is 7 because A is larger than B in this case. Let's continue. In part 2, we have a few things to look at. First is we have the variable A, which we printed value to be 5. And now we are incrementing A to be 6, multiplying by B, which is negative 3, to give us the result of negative 18. Now we are printing A, and A is now 6, because in line 44, we incremented A by 1, used it in a calculation, but after that, it stayed 6. In part 3, we are going to reset A to its original value of 5. We again printing the value of A to be 5. We are using A in a multiplication times B. However, in this case, because the plus sign is to the left, we are using the original value of A, which is 5 times negative 3, it's negative 15. Now, if we are printing the A after this operation, A is now also being incremented by 1, so in 6. So in both part 2, A has been incremented by 1. The first time, it was incremented prior to its use on line 44, whereas in line 52, it has incremented after its use. In part 4, and final part of this example, we are going to reinitialize some of the values, and we're going to use the same complex statement that we saw in our previous screen. We are going to exemplify how if we multiply the counter times an increment and then add it to the initial value, it will use different values of that counter. So in line 60, we are incrementing the counter by 1, but only after we are multiplying it by the increment. So in line 62, the counter is now 3 times the increment plus the initial value, and so on. In line 64, we are first incrementing the counter, and then we are multiplying it. With additional exercise and reading and trial and experimentation, you will be able to figure out on your own what is the best way of using and combining expressions, operators, increments, and many others as you will continue to increase your knowledge about what's available in C. We'll now continue our discussion of expressions and statements in C and focus a little bit more on mathematical ones. Math is the root of computer science, so it is no wonder that a lot of the material covered in a computer language class is about math. Let's take, for example, the area of a circle. It's a simple formula which you probably learned sometimes in geometry in middle school. Pi times the radius of the circle square, or the roots of a quadratic equation. The quadratic equation is typically noted as a times x squared plus bx plus c equals 0, and then there are two positive roots given by minus b plus or minus the discriminant, which is the expression under the square root, divided by 2a. This will give you two values based on whether you're using plus or minus. And then the volume of a cylinder, which is the area of the base, which is a circle, pi r squared times the height. Let's implement those formulas in C and see how we can compute that. In order to do that, we're going to introduce a new library, math.age, which we're not fully taking advantage of in this particular one, but as we move along, you will see different uses of math.age. For now, we're going to explicitly define pi as 3.14159, and we will use it throughout. We're also going to define the radius of a circle and the variable area, which obviously does not have an initial value. In a comment, that's a little bit of a creative way to write radius square. We are going to calculate the area of a circle. Rather than using a function for radius square, we simply multiply radius times itself. Then we're displaying it. Then for the quadratic equation, I'm arbitrarily defining a, b's, and c as 2, 7, and 4. I am then calculating the discriminant using the square root in line 40, which is a use of the math.h library. That's b squared minus 4 times a times c. And now I'm calculating the two real roots of the quadratic equation. One root is negative b plus the discriminant divided by 4a. The other one is negative b minus the discriminant divided by 4a. I'm printing the two roots as floats. And now we're on to our last calculation, which is the volume of a cylinder. Pi times r squared times h. Calculation here is a little bit simpler. We're simply multiplying the value of pi times r times h in line 56. Let's see how all this works. We're going to run the code, and as we can see, a circle with radius 5 has an area of 78.539, and so on. The solutions of the quadratic equations are the first root is negative 0.35, and so on, and the second root is negative 1.39, and so on, and the volume of a cylinder. We have just created a calculator in C. You can imagine that should you have a need to use very specific calculation in any area of science, you could simply create a C program that has as many formulas built in, and all you'll have to do is plug in those numbers. You would note, however, that this particular example is not very useful in the sense that it has hard-coded values, meaning it only calculates the areas and the volumes and the roots for those particular equations whose values are included into that file. We will now see a better approach to this. We will allow the user to enter those values. In this particular one, we'll allow the user to enter the values for a, b, and c and calculate values of the roots for any quadratic equation. First, we're going to ask the user to enter those values. So if you look at lines 24 through 31, we are using a combination of printf and scanf to ask the user to enter a, b, and c respectively and capture those as floats at their respective value positions, a, b, and c. Notice the ampersand sign preceding a, b's, and c's in scanf because scanf requires a memory address to place the value of the variable. This is a syntax that makes scanf a little bit different than the way you use to treat variables with other functions. Further down, we are calculating the discriminant, just like before, which is the square root of b squared minus 4ac, and the root 1 and 2, just like the previous example. So the only thing that's different now is that we have not hard-coded anymore the numbers inside the code, but we are asking the user to enter his or her own value. Let's put this to work. I first enter the number for A. Let's pick a 1. I'm going to enter now a number for B, let's say 10, and a number for C. And here are my two roots of this quadratic equation. If you want to test that, you are welcome to plug those values back into the quadratic equation for x using the a, b's, and c's you defined, and you should get a 0. Let's try something else. I'm going to use a different value for a small value for b, and a large value for c. Notice that we did not get this time a numeric result. Nan is C's way to say not a number. In other words, something erroneous happened, and this was expected. If you look at line 33, there's a square root. As you recall from algebra, the square root can only be applied to a positive number. Therefore, if the expression b squared minus negative 4ac is a negative number, you will get an error. You will get an error simply because in the realm of real numbers, we do not handle square root of negatives. That's another area of mathematics called complex numbers, which are handled separately and with different libraries, sometimes custom libraries, to handle that. This is beyond the scope of this video. In this video, we will continue our discussion on the relationship between statements and expressions, just to make sure that you get a little bit more exposure to the differences and how to approach the process of building them. An expression represents a single data item, whereas a statement carries out some definite action. It is not always wise to create very complex statements. When possible, it's better to break the statements into smaller substatements and build custom statements this way. A simple expression statement is a equals 6, or c equals a plus b, or increment j by 1. Compound statements are those that require multiple steps of calculations which result in a very specific action. Let's go back to our code and see how this works. Here again, we included the math.h library, and we start with simple statements without output, lines 20 through 24. We are then following with a block of code, line 25, all the way through line 34, which is in green, and if you notice, line 25 and 34 are comment lines, which means the entire block of code is being ignored. Let's run this program and see what happens. Well, not much. Everything below line 24 is commented out, so there's really nothing that this program does other than printing a statement. These are simple statements without output. Why would you want to do that? When you have programs that deal with multiple logical challenges, building expressions, and any other compound issue, it is a good practice to comment out portions of the code while you run the other. This will give you an opportunity to ensure that every piece of code runs correctly before you put everything together. Now we're going to proceed and remove the comments, save the file, and run this again. This time, the calculations have been performed. We calculated the area and the circumference of the circle. Let's look at one more detail. We included the math.h, and notice that I am no longer needing to define pi at 3.14 and so on. Instead, on line 30, there is a reference to m underscore pi, as well as in line 31. This is the constant that's predefined at the maximum available precision in the math.h library. This concludes our discussion so far on expressions, statements, and mathematical calculations and formulas in C. You are now ready to do a little bit more advanced exercises and maybe even challenge yourself. Here's the challenge to make your study of C a little bit more interesting. The objective of this challenge are for you to demonstrate an ability to solve computational problems in C, as we have seen in the past several videos. In addition, I will be asking you to translate some mathematical formulas into expressions and statements in C. Specifically, here's what you have to do. Write a program in C that receives as input a height in centimeters. The program will then calculate and display the following: the height in feet and inches. All you have to do is figure out what is the conversion between inches, feet, and centimeters. Be a little bit creative with the way you would develop the math, and use everything you learned so far about calculations, variables, expressions, math, and statements, and write a very short and simple program in C. I estimate that this exercise should take you about 20 minutes. So hopefully by now you have figured out how to convert from centimeters to feet and inches. And if not, here's a simple way, definitely not the only way to do that. In order to help with this solution, we are defining three variables: double centimeters, double inches, and int feet. And there's a special reason to do that. The reason being that we typically refer to feet when it's about height as one integer number. For example, you would say that my height is 5 feet and 10 inches. We will then ask in line 20 the user to enter the height in centimeters, and we'll use the scanf command to capture that in a variable centimeters. And notice the LF directive for scanf because we're dealing with doubles. Then we are going to convert our entire centimeters value into inches by dividing by 2.54, given that 1 inch equals 2.54 centimeters. Next, in line 23, we are going to calculate the feet. We're going to take the inches that we calculated previously, divide that by 12, because we know that there are 12 inches in a foot, and since the feet was defined as an int variable, everything will be truncated. That's part of the decimal piece of this number. And all we'll have is the integer value of the height. Typically, we will now going to have a remainder, and we need to figure out what the remainder is. There are multiple ways to do that. One way, which I brought here, is we're going to take the inches that we calculate in line 22, and we'll subtract from that the actual value in inches if the height is known. So the height is already known in feet, the integer part there is of the height. We multiply that by 12, subtract that from the total number of inches, and this is what it's left. Let's put this into action. Enter the height in centimeters, for example, 180, and the program tells me that my estimated height is 5 feet and 10.9 inches. This was a straightforward exercise. The only real little bit of a challenge was in line 24, and after you look at the code, maybe once or twice, I'm sure you will find it quite easy to understand. One last thing to note is that in line 25, when we printf the inches, I requested that only one decimal digit is printed. Therefore, 10.9 and not the entire range of precision values that that variable holds. Here's another challenge. As before, we are focusing still on demonstrating an ability to solve computational problems in C. In addition, I would like you to translate mathematical formulas that will be given to you into expressions and statements in C. Specifically for this challenge, we are going to convert degrees from Celsius to Fahrenheit and Kelvin. It is known that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Write a program in C that will calculate the freezing and boiling temperature of water in Fahrenheit and Kelvin degrees. For this exercise, use the following formulas. Degree Fahrenheit equal degrees Celsius times 9/5 plus 32, and Kelvin equals degrees in Celsius plus 273. We estimate that this exercise should take you considerably less time than the previous one, only 10 minutes, given the fact that you have the formulas. This is a solution to the second challenge. It may seem a little bit simpler than the first one, however, it's very useful. In computer science and computer programming, often you will find out that the best solution to a challenge or a problem is typically simple. You don't necessarily need to require a lot of complicated computer science algorithms. So here it is. We know that the boiling Celsius and freezing Celsius temperatures are given at 100 and 0 respectively in line 15 and 16. And we're introducing here a slightly new concept called constant. In line 19, we're going to calculate the boiling temperature in Fahrenheit by taking the boiling temperature in Celsius times 9/5 plus 32. We are going to then repeat the calculation for freezing, and then we'll use the formula for boiling and freezing in Kelvin by simply adding 273. This exercise was not only meant to demonstrate how difficult or easy it is to solve a problem using C, but the ability to take a problem defined in plain English and a set of formulas that help its solution and translate that precisely into computer language. This is a very important skill to have as a computer programmer. If you are able to translate accurately the requirements of a problem into a computer language, you have already accomplished a major step towards solving it. Now that we have covered the subject of functions a little bit, mathematical expressions, and a few other topics, we are ready to integrate all of them and create even more interesting and useful things in C. On the topic of functional programming, it's worth recalling some of the things we mentioned earlier. Functions are blocks of code that perform specific tasks. For example, calculate a mathematical expression, evaluate the outcome of a series of statements, or print results in a specific format. Some of the advantages are obvious. Enables reusability of portions of code, enables breaking complex solutions into simpler steps, and simplifies the debugging process. And finally, it eases the process of code update and improvement. Let's see all of this to work right now in an actual program. Let's imagine the following scenario: a program that assesses the number of empty seats in each one of 3 rooms in a building, in a museum, or whatever your context may be. It then asks the user to enter the numbers of waiting visitors for each room. It assesses each room is still vacant seats, the overall capacity, and the average number of visitors waiting per room. Let's look at the 4 functions that are defined for this program. One is assess room capacities, the other is estimate waiting visitors, process data, and generate reports. Sort of the 4 functions that it's very obvious, or at least legible and plausible, what those functions may do by just reading their names. That's another feature of C. You can use names that make sense. It enables you to write functions with those names. And then if you look at the main is very short, and it simply lists the steps that you are about to perform when this program runs. You simply assess the room capacity, you estimate the visitor, you process data, and generate some report. In order to do that, we define in line 27 through 29 multiple global variables that are known throughout the program, like room 1, 2, and 3, which will tell us how many seats are empty in each room. Visitors 1, 2, and 3, how many visitors are waiting. Then we'll be able to calculate total available seats and total waiting visitors. Now let's look at each one of those functions. As you can see already, I was able to think about this problem without worrying about how will I implement each one of them. I simply created the skeleton for the main program. I typed the names of all the functions that represent functionalities that I want this program to do. All I have to do now is start implementing them one by one. For example, the functions called assess room capacities simply ask the users for each one of the room to enter the number of vacant seats. The second function that estimates the number of waiting visitors asks the user to enter for each room how many visitors are still waiting. Finally, there's a function to process data and to generate the report. The function that processes data does 2 things. One, it adds the total number of seats available in each room, and then the total number of waiting visitors for further processing. The generate report then combines a few things you already seen in a previous video. First, it assesses for each room the number of visitors compared to the number of seats available and uses a Boolean logic operator. If room 1 is bigger than visitor 1, for example, the result would be true or 1. and so on for each room. It also calculates the total available seats in comparison to the total number of waiting visitors, and also displays a 1 or a 0 based on whether there are available seats. Finally, it calculates the average number of visitors per room by simply adding all the visitors and dividing that by 3. Let's see what happens when we run this program. First, we're going to enter the number of seats left in room 1, let's say 30. Number of seats left in room 2, let's say 20. Room 3, let's say 10. Visitors waiting for room 1, 12. Waiting for room 2, 5. For room 10, 9. Here's our results. Overall, there are still seats available, yes or no. 1 means yes, there are still seats available. Room 1 can accept more visitors, yes. So is room 2, and so is room 3. On average, there are 8.67 visitors waiting per room. As you can see, this program allowed us to take a task, breaking into smaller, simpler ones, develop them individually, and now we can easily update each one of those functions without much interaction and effect on the others as needed. This is the beauty of functional programming. As we continue our discussion of functions, we are now going to talk about passing variables to functions. What does it mean? It means that the function can work and do its magic using values it receives externally. Functions are just mini programs which may or may not use external data. Parameters are those variables that are defined to accept external data. And arguments are the data passed onto the function. We'll see an example shortly. Here's an example of a function without parameters. In this case, the function parameter section simply states void. Everything the function needs is contained within the functions. Everything it does, it's calculated internally and it prints a result. The way to call this function is simply use its name and parentheses. The second example, it's a function that does use parameters. In this case, there's two of them defined as float x and float y. The function performs a calculation with those two values, and then it prints out the result. Note that the function is being called with two numbers, 2.6 and 4.2. Those numbers are passed accordingly and mapped onto the two variables that are the parameters of the functions. When the function is called, the 2.6 and 4.2 are called the arguments. When the function is defined, the float x and float y are called the parameters of the function. We are going to look at a C program and see an implementation of those functions with and without parameters. This is a scenario in which the user interacts with an ATM-like program and has an opportunity to either debit or credit an account, and a few other things would happen during those transactions, which we'll see right now. Let's take a look at the main program first, and then we'll see what we needed to define for that. The first thing that program does is to initialize an account and print the balance. This is performed in lines 30 and 31, calling a function getBalance. Then the customer will perform a transaction, update the account, get the balance, perform a second transaction, update the account again, and on line 39, there's even a gift added. What I would like you to notice in this example is the fact that we are repeatedly calling the same functions. For example, ask customer, line 33, line 37, and line 42. Get balance, line 31, line 35, line 40, and line 45. This is possible due to our approach to programming, which we called earlier functional programming. By defining a set of functions as short blocks of code tasked with a very particular item that they have to calculate or a particular action that they have to perform, it enables us to keep reusing that block of code by simply calling its name. For example, ask customer. It simply displays the message, next transaction, enter the amount, credit, debit, positive, or negative, then ask the user the amount. Each time we need to ask the customer to enter this amount, we simply call the function askCustomer. Let's look at the function addGift. This function is using a parameter, which is a float, and it's the gift amount. When the function receives an argument, for example, $5, as you have seen in the main, it's being translated into gift amount. The gift amount is now an internal variable whose value is only known inside the function. It's being added to account balance in line 54, and the message is being displayed to the user. Another function that is using a parameter is on line 67, the function updateAccount. The account is updated with the amount that the user has entered in another function, askCustomer. There are different ways to interact with functions via passing a variable. As we go along, we will keep learning more and more interesting ways and ways that gives you a lot of flexibility in the way you write your code and write your functions. Let's run this program and see how it works. First, the program tells us that the current balance is 0, and we are supposed to enter a first transaction, either positive or negative. I'm going to enter 100. The account was updated with $100, and the current balance in the account is 100. Let's see where this comes from. We just performed the first transaction. I was asked how much money I want to debit or credit. The account was updated, and the balance was printed. Let's proceed. The current balance is 100. Next transaction. This time I would like to debit my account. It has been debited by $23, and as you can see in the code, a gift in line 39 has been added in the amount of $5, and indeed, the addGift function also includes a note, congratulations, a gift of $5 has been added to your account. The current balance now, aggregating my debit and the gift, is $82. I am being asked to perform one more transaction. I will debit yet another amount, let's say $89. Actually, I'm going to put it negative. A gift has been added of $2. The balance in my account is now negative $5, and I have no more transactions. To recap, you can see that our program are starting to get longer and longer and more complex, even more making the case for using functions as much as possible, because if we didn't have functions, each time you see a call to this function, I would have had to copy this code again and again. This program might have become even longer. Furthermore, should I want to change the message that I'm asking the customer to do, the instruction to the customer, a congratulatory note, anything in any functions, the moment I change it into that function, it's being updated each time the function is being used. Again, this is the beauty of functional programming, and it's enhanced by the use of parameters. In the upcoming videos, we will do even more complex and interesting things with passing parameters. In this video, we're going to continue our discussion on functions, and we will learn even more powerful features and many ways in which that can make our coding experience more fun, more efficient, and more powerful. Let's look at one feature of the functions called return value. It is possible for a function to either return a value or not return one. What does it mean? It means that if we want to specify a specific type of value, we will assign the data type to the function, and then we will put that function in such a way that it returns a very specific data type to match the one that's been declared in the function header. If no result needs to be returned, then the function data type is void. For example, if no result is returned, the data type of the function is void add numbers. In this case, the function simply computes something inside its body and then prints the result. In this example, a result is returned, in addition to receiving arguments for its two parameters. In this case, the function returns a float, and The float is then captured into an external variable called the result equals add numbers. This line means that whatever the function computes, it's going to be forwarded to a variable outside the function and then being used in the rest of the program. Let's see how this works in code. To demonstrate this, I created a fairly lengthy scenario in which we will look at the ability to calculate statistical data in a basketball game, or more correctly said, an imaginary basketball game. This program describes a very simplistic approach to gathering statistics. We are going to ask the user to enter the number of shots in each quarter, the number of three-point shots, and the number of two-point shots in every quarter. And we are now going through a lengthy printf and scanf pairs of commands so that we can capture all this data from the user. We're going to scroll down now to the actual execution. As you can see, there are numerous functions called starting with line 68 all the way through 76. Let's look at line 68, for example. I'm declaring a variable total points, which is going to be storing the result returned by a function calculate total points made, to which I'm going to pass 4 variables as arguments: total shots in Q1, in Q2, Q3, and Q4. Notice that in the subsequent two lines, lines 69 and 70, I'm capturing data for 2 additional types of statistics: the total 2 points made and the total 3 points. However, I'm using the same exact function. Why? Let's see. Calculate total points made is a function that receives 4 values as arguments because it has been defined with 4 parameters in line 83, int Q1, int Q2, Q3, and Q4, and returns a value that is also an integer. Now, notice something interesting which I did on purpose. Inside the function, there is a variable called sum that's defined as double. Even though the numbers that are added are int, the function is expected to return an int value even though sum is double. In the process of returning that value, the C compiler is automatically converting the value of sum from double into an int. I did that deliberately so you can see that that's possible. Sometimes it will be incorrect to do so, but again, as I said before, the C compiler assumes you know what you're doing. If the result in this case, because it's double, would be, let's say, 20.0, the int version of it will be 20. However, if the result would have been 20.5, we would have lost that 0.5. Let's continue with assessing what this program does. Line 72 through 74 calculates various averages and performances. For example, line 72 calculates the average performance per quarter. It's a function that receives 4 arguments, adds them, divides them by 4, and produces an average calculation. Let's see what happens now when we calculate performance. There's another interesting notation. If you look at line 94, float performance equal shots made divided by total shots times 100. Notice float type in parentheses to the left of shots made and to the left of total shots. The reason for this is shots made and total shots are integers. We need to ensure that when we are dividing 2 integers, the result is float. This operation is called typecasting. We are forcing shots made to become a float, even though it's an int. So internally, we can look at it as just adding a .0. It doesn't change the value, but it now becomes a float. If you don't do that, your performance will be 0 because all those variables will become integers, and you're welcome to try this and see what happens. Now that we have all this in place, let's just test the program and see what it does. And after the video is over, please download the file and experiment on your own and see if you can find ways to make this better. Let's enter the shots for the first quarter. Let's say 20 shots. 2-point shots made, 5. 3-point shots made, 2. Second quarter, I'm going to enter 18, 4, 4, 12 shots, 5, 2, and 16 shots, then 8, and then 2. And here are our statistics. Total attempts made, 66. Total 2-point shots made, 22. 3 points, 10, and so on. Success for 2, for 3, and average points per quarter. Again, this is not the most accurate, the best basketball statistics out there by all means. However, its purpose was to illustrate a few things. First, the convenience of using functional programming, the convenience of having return values, and the ability to repeat calls to one function. In the upcoming videos, we will continue our discussions with functions, functional programming, parameters, and so on, and you will be learning how you can make C work for you in a much, much more efficient way. In this video, we're going to discuss one of the most exciting, dangerous, and most controversial topics in computer programming, recursion. So let's talk a little bit about the math part of recursion, because its name comes from a mathematical concept called recurrence relationship. In a nutshell, recursion is a process in which a function calls itself. It is based on a recurrence relationship in mathematics as follows. This is an example of a recurrence relationship because in order to generate a series of numbers using this formula, you are using the numbers themselves in order to bootstrap the process. Here's a specific example. an, meaning the nth number in the series, equals the previous number in the series plus the one previous to that. So in order for me to kickstart the process, I must know the first two values, namely A0 and A1. Once I know those two, A2 can be computed by adding A0 and A1. So 1 plus 0 is 1. A3 is A2 plus A1, which is 0 plus 1, which is 1. A4 is 2 because it's the sum of the preceding two, and so on. This is a series of numbers generated by a recurrence relationship. Let's see what does this mean when we translate the concept in C. A recursive function, simpler than the recurrence relationship before, looks like this. The header function is just like a typical function. In this case, it returns no value, it's void, and needs one argument for its int parameter num. Inside the body of the function, called func, we are calling the function again. This time, I'm adding 1 to num. In essence, I'm passing to the function the value of its parameter plus 1, and then I'm printing the function. In order to kickstart the process, I'm going to have to start with some initial value. In this case, I decided to start it with func1. This means I'm first sending 1 to the function, num becomes 1, then the function calls itself with num plus 1, meaning 2, and so on. Until the process, what do you think? It never ends. There is nothing here from preventing this to go on and on forever, and has the controversy. Recursion does something very dangerous to computers. Each time a function calls itself, it creates a copy of itself in the computer memory. If there's nothing to stop this process, functions will be continued to duplicate themselves until either the computer memory is exhausted and your computer will crash, or if you're lucky, you're using a modern operating system in which there is a safety feature that recognizes that a function calls itself so many times that the operating system intervenes and halts that function. Let's see what happens in the actual C code. I created 4 functions so we can experiment and see what are the effects of stopping and non-stopping recursion. First, there is a function called number series, which is a very, very simple function. All it does, just like the one from the previous example, it has an argument called k. It prints k, it's the first step on line 33, and line 34, it calls itself with k plus 1. There is a warning in line 31. Do not do this. I'm only doing this to illustrate the process and so you can see what happens. I'm going to run the project and notice that this goes, and for no apparent reason, it stops at k of a value of 262,000. So without noticing, within a few milliseconds, this function calls itself 262,000 times. It's such a large amount of memory wasted that the console of Eclipse can't even display because it's very limited in the amount of memory it can handle. Hence, my warning, do not do this. I'm going to comment this function out, so it is being ignored, and I'm going to uncomment another function, also recursive, that does something very different. It also has a variable k, which is int, that's being printed each time the function calls itself. In addition, it has another variable called val. At each recursive call of the function sends to itself the value of val divided by 2. Let's see what this does. It is hard to notice, again, because it was so fast. This time, it stopped at 174,669 recursive calls, but you can imagine that any number that you divide by 2 174,000 times, eventually it's going to be very close to 0. So it is not very helpful to use a recursive function that doesn't stop. So let me introduce a new concept, which is actually also the concept covered in the next video. But this concept is absolutely essential to the use of recursion, and I'm going to use this explanation as a bridge between this video and the next. This concept is called an if statement, a logical decision. And it's very simple. Line 47, I am telling the function, if k is less than 20, then call the function with the next increased value of k. And that's it. The moment k reaches the value of 20, the recursive call stops. Let's do that. I'm going to uncomment the function number series stops and run the program. As you can see, the program started with k equals 1. At every step of the recursion, k was added 1 in line 34. The function went back to its beginning to line 32, printed k, and so on. The function calls itself, but I told it to stop. The only way to use recursion is if you can stop it. Let's see one more time what happens with the recursive half. We'll do the same exact thing. And now you can see we started with 1,000. And then at every recursive call, that's 1,000 get chopped in 2, 500, 250, and so on. And you can see it's very quickly getting close to 0. I stopped it after 20 steps. In the upcoming video, we'll talk much more about if statements, and we'll see how it can be used to make decisions of all kinds. In this challenge, you will be able to demonstrate your understanding of the concepts of linking external libraries. Specifically, you will demonstrate the ability to improve your manageability of code and files through the use of external libraries. Take a look at the exercise file 0702 in Chapter 7 and modify it in the following way. Create a pair of external files with extensions .h and .c, as you saw earlier. Identify all the code in the original exercise that can be placed into such external files. Then, use the include preprocessor directive to link the external files that contain the code that you have moved from the original file into those external files. Run your project and ensure that it does exactly the same thing. We estimate the time for completing this exercise about 15 minutes or so. Good luck. Let's take a quick look at the original exercise file in Chapter 7, 0702.c. That file, as you recall, includes a lengthy prototype section, a lengthier main section, and lots of functions that it calls. The solution in this case, it's quite simple. We're going to move everything except what is in main. In transactions.age and transaction.c, which is the file names I chose for this project, you can choose any other files, I moved all the prototype functions, and in addition to that, the include stdio and stdlib, and I defined the global variables as well. In transaction.c, we still need to include the two libraries because they are used by this function in this file. That's all there is to it. Now, if we examine the original file, all there is, it's an include to transactions.age, which also has inside it the include to the standard libraries, so we don't even need those in here, and the main. We created now a solution in which we have three files. They are much more manageable, they're much shorter, it's easier to find information, and they can be actually shared with other projects should you choose to do so. If you look at transactions.age, it is very clear in a very short file what functions are available for someone to use. A different person may not even care about how these functions have been implemented. All that person needs to know is the name of the function and what type of variable. If someone wants to know all the details, they are available in transactions.c. This is the second challenge for this chapter, and it's quite simple, but it will demonstrate your understanding of the concept of recursion. You will simply be asked to implement a recursive function according to the following rules. Write a program in C that asks the user to enter two integer values. Then, write a recursive function that uses the two values as lower and upper bounds of a series. Recursively print all the numbers from small to large. Display the recursive call counter. Just to repeat and make sure you understand the challenge, let's say you enter the numbers 10 and 50. Your recursive function will print all the numbers starting with 10 and stop at 50. Here's the solution to the challenge number 2 in this chapter. You were asked to write a simple recursive function that, given two numbers, small and large, will recursively print all the numbers in between. Let's take a look. First, straightforward printf commands to ask the user to enter a small number, then a large number. We are storing those values in two int variable, small num and large num. Let's look at the recursive function and then why we call it the way we do. The recursive function is called listNumbers and has three parameters: small, large, and k. Let's focus on line 32. The function recursively calls itself with small plus 1 because at each call of the recursion, I want to increase the number by 1 so that I print in line 30 the current number. So if I start with small equals 10, line 32 will add 1 and will make it 11, which will be printed in line 30, and so on. Large is the upper bound that's used in line 31. Keep in mind that at every recursive call, small increments by 1. Eventually, it will reach the value of large. However, line 31 has a little if statement that guarantees that the function only calls itself as long as small is less than large. Eventually, as we keep adding ones to small, small will equal large. When that happens, the program no longer calls itself and it simply halts. The last parameter of the recursive function is k. K is simply used as a counter as it was required in the challenge definition so that we can print what is the current recursive call. So if you look at line 25, the initial call to list numbers uses small num, large num, and 1. K is being initialized to 1. In line 32, when list numbers calls itself, K is incremented by 1, and therefore it counts the step. In line 30, I'm printing both the current step, K, and the current value of the number. Let's put this to test and see what this program outputs. First, I'm going to enter a small number, let's say 27. Then I'm going to enter a large number, let's say 76. Enter, and here it is. At the first step, I'm printing 27, which is step 1. The step increases due to K, and it stops with the last one, which is 76, after 50 steps. In this video, we're going to start a series of discussions about if statements and see how they can allow us to make decisions, change the course of action, and do very sophisticated logic things in our programs. Let's recall the definition introduced earlier for a simple if statement. It is simply a way to instruct the program to do different things outside the order that the code is serially written. Unless otherwise told, a C program, like any other program, will execute all the command lines in the order entered. The simplest form of an if is if, condition, then do something. The word then is unnecessary. The condition can be a simple expression or a very complex one, or even a call to a function, as we will see soon. Let's look at a simple statement. If x is less than 0, meaning x is negative, we would like to make it positive by multiplying it by -1. Very simple use of if. Let's go to the code and do a little bit more interesting things. This program will ask the user to enter a number, and then based on the number entered, a decision will be made and feedback will be sent to the screen. For example, the number the user is asked to enter is between 0 and 100. There is a function in line 21 that will take care of asking the user the number and processing the data, return the result into a variable called num. Let's see how this function works. It's a simple printf question, a scanf to get the number, and then we return the value, which is int, to agree with the data type of the function getNumber. Once num has been given a value, it can be tested. Line 23 tests if the number is less than 0, in which case we would like to call a function toSmall. Line 26 tests whether the number is larger than 100. Line 29 checks whether the number is exactly within range. In each one of those cases, we are calling a function that in turn provides the adequate message. You may ask yourself, isn't this redundant a little bit? In some ways it is. However, the purpose of this video is not to create the best logic implementation, but to show you different things you can do with an if statement. In particular, line 29, in which we are combining two expressions and a logical AND to make a more complex decision. We will see in the upcoming videos as we can improve the if, the logic which they are part of, the expressions they process, and so on. Let's run the program and see how this all works. I'm going to enter a number between 0 and 100. I'm going to start with a small one. The number is too small. I'm going to run it again. This time I'm going to give it a very large number. The number is too large. And now I'm going to type 1, which is just within range. And the program works as planned. In this video, we will introduce a new element into the if statement. It's a variation of the simple if called if-else. Let's see how this works. Just like the simple if, condition, do something, we now are adding a different option. Else, do something else. If the condition is false, the if block will try to perform an alternative function. It could be a simple assignment statement or a call to a whole different function. Let's see a more concrete example. For example, if sorted equals true, let's assume we have some data and we have an indicator to tell us that it was sorted. So if it is true, then print results. Else, starts a whole new series of commands or function calls. So if the data is not sorted, sort data and then print results. So this is very different than just a limited version of an if. We have now a more efficient way to say, test one thing. If this is not true, then do another thing. Let's see a little bit more complex example in code, and you'll be able to understand even more the benefits of the if-else construct. In this example, I am taking the same exercise you saw in the previous video, 0801, but we'll make it a little bit better and a little bit more complex. Notice that I don't have the same number of ifs in the main as before, but here I just have one if using the complex expression where I'm simply asking whether the number is within the right range, 0 and 100, and this is facilitated by the logical AND. So essentially, I'm distinguishing between two alternatives. Either the number is within the right range or it isn't, in which case I want to display an error. So it's either just right or else call the check error function, to which I am passing the value of the number that the user entered using the same method, getNumber. Let's see what check error does. Inside check error, I have another if-else construct, because again, there are two options. The error could be either that the number is too small or that too large, in which case I'm calling the same functions that I used in the previous exercise, too small and too large. So this was an example of using the same mechanical tools for displaying messages, but slightly changing the logic in order to take advantage of the if-else capability. In this video, we're going to keep discussing the if-else statements. Now we're going to make them even more complex by using nested if. What do we mean by that? Logic can become, at times, very complex, demanding very intricate if-based decisions. For example, if current speed is less than max speed, then I want to display the message, you are driving at legal speed. Else, now I have another decision to make. If current speed equals max speed, then print be careful, slow down. Else, that's yet another choice, slow down now. So what is the logic of this? First, the speed is less than a maximum speed, which is fine. Now I have an alternative. It is not less than maximum speed. In that case, it could be either equal to the maximum speed, or if it's neither less than and it's not equal, the third choice has to be that it's bigger than, in which case I'm displaying the message slow down now. I don't need to test another if because it's the only available option. Let's see a similar example in code, and we'll see how this all works in C. We're going to stay within the same framework of mind of traffic and speed, and let's write a little program that checks the color of a light at a traffic stop. We will ask the user to enter R for red, Y for yellow, and G for green, and we will do that in a function called checkTrafficLight called from main. Note that this is the only function that is called from main. This function, in turn, calls another function, processColor, that's the one that would enter by the user. Let's look at processColor that implements most of the logic of this program. First, I'm testing whether the user has entered R. If the user has entered R, I'm interpreting this as the traffic light is red. Else, meaning it was not R, so let's see what other options do I have. If C equals Y, I'm interpreting this as being yellow. Else, I'm continue to test. If it was an R and it wasn't Y, maybe it's a G. So if C equals G, then I'm printing the traffic light is green. Else, meaning it was not R, it was not Y, it was not G, it must be something that is an illegal input to this program, in which case I'm displaying the message unrecognized color. I hinted to the user to enter only those three options, red, yellow, and green. Otherwise, we will display an error message. Notice one more thing. One of the advantages of the nested ifs approach is that as soon as a correct option or choice has been made or identified, there is no need to check the other options. For example, in the beginning, if the user typed R, the entire block of code starting in line 39 through 46 is ignored. There's no need to go through it. However, if it is not R, we will only test then line 40. If the line 40 is resolved, meaning the user has typed Y, there is no reason to perform the other sections in line 42 and so on. So only in the worst case scenario where the user has typed a wrong choice, the program has to go through all the options to finally detect that the user had made a wrong or an unrecognized option as this program is written. Let's now test this program and see how this all if block works. Okay, so first I'm asked to enter a color R, yellow, or green. Let's type Y for yellow. The traffic light is yellow. Great. Let's run it again. I'm going to type G for green. Traffic light is green. Now I'm going to type some unrecognized letter, D. Got the message, unrecognized color, which means the logic works as planned. You will see in the upcoming videos how we can make this even more sophisticated, more efficient, and what programmers like to call a more elegant solution. In this video, we're going to learn a new command called switch, which is a more elegant way to replace nested if, else, if statements. Let's see how this works. Rather than asking, as we saw in the previous videos, is the color R, else is the color Y, else is the color G, and so on, this is a more elegant construct. We're simply using a command called switch, and then we have a list of tests, as you can see, case R, case Y, case G, and so on. There is no limit to the number of cases we can have, and you can see that if you're going to have 20 or 30 levels of nested ifs, your program logic would become quickly unreadable, undebuggable, and guaranteed to have errors. This way, it's much easier to see what the program is intended to do, easier to organize. In each one of the cases, I'm calling a different function to process that option. At the end, notice the last case is not a case, it's actually default, which means if none of those cases above were received as input to the switch statement, perform the default operation. In this case, if the user hasn't typed R, Y, or G, the default action is something I called traffic light malfunction. Let's see how this works in code. This is an improvement of the previous file in exercise 0803, where we were handling traffic light color choices by a user using nested ifs. Rather than using process color with nested ifs, we are taking an approach now using the switch statement and different cases. We are asking the user just as before to enter a color, except now we are using the switch to decide what to do in each case. So whether the color is R, Y, or G, we have a function, stop driving, get ready, start driving, respectively, to handle each one of those options. The default is traffic light malfunction. Let's see what some of those functions do. For example, stop driving, it's still printing the same messages. Get ready, shift into gear, and so on. We are simply calling different functions that display different messages to the user. Those functions can do anything you want them to do. They could be complex lines of code, they can in turn call other functions, and so on. In this video, we're just focusing on the mechanics of the switch statement. We edited our arsenal. It doesn't mean that it is always better to use switch than if, or it is better to use a nested if than a simple if. What you have to realize right now is that C gives you option. You, the programmer, must decide in every instance which type of command, which type of language construct is more appropriate for the situation at hand. Sometimes it will be better to use an if, sometimes it will be better to use case, and in time and with experience, you will be able to make the determination on your own. Let's see how this program runs. The menu choices are slightly improved from before. I'm still asked to enter R, Y, or G, and I'm going to make my choice. Let's say Y. It still works. I see the message. I'm going to run it again. I'm going to put red this time. I stop this car, and one more time. This time I'm going to give it an illegal choice. M, unrecognized color is the malfunction. So the program runs just like before, and you saw that we can either use nested ifs or we can use the case. To recap, it's a choice you have to make. If you only have a few options, it is arguable which one is easier. If you have a lot of options to process, obviously case would be a better situation, will give you more options, more flexibility in coding, and it's more readable and easier to debug. In this challenge, you will be asked to demonstrate your knowledge of using decisions and if statements and switch statements in C. More specifically, here's what I'm asking you to do. Build a stock purchase decision advisor. Pretty simple. You will ask the user to enter the current value of the stock. Then you will check the decision parameters. Your program should have preset values for sell and buy that will inform your decision. Then you will advise to either purchase, sell, or hold. You will write a function that will check your input or the user input against the preset values. Based on whether the value entered by the user is less than the selling point or higher than the buyer point, or whatever result your comparison may yield, you will then call another function that will implement a switch construct to handle the purchase, selling, or hold decisions. You do not have to implement any actual transactions. Simply print out a message to the user that informs about the decision. I estimate that the total time for this exercise should be about 20 minutes, given the fact that you have the exercises in the other files. Let's see how we can implement a simple buying or selling stock advisor using if statements and switch statements. We will start this code by defining two constants in line 14 and 15. Those are the sell price point and buy price point. Obviously, those are arbitrary and you can change those numbers at will. Then we will define prototypes for three functions: ask stock value, make decision, and handle transaction. So let's see how this works. If you look at the main, we have two main statements in line 23 and line 24. The first one is asking for a stock value by calling the appropriate function. And the second one is using the value returned by the askStockValue function and passes it onto the makeDecision function to evaluate it. The askStockValue, it's a simple printf scanf pair, and the decision is where the first if is being implemented. And notice two things. When we're asking to make a decision, we are not checking a specific value, but we're checking a range. Therefore, it is more appropriate to use the if. For example, in line 42, if the value is less or equal than the buy price point. If you scroll down, handle transaction checks for very specific matching to a predefined value. For example, handle transaction with a parameter s or age. In this case, the switch statement is more appropriate. So let's recap. We are first processing the value and making a decision using the make decision function. If the value is less than the buy price point, then we're going to handle buy. Then, if that's not the case, we will handle a sell. Finally, if it's neither a buy nor a sell, we handle a hold. Now we are moving to the handle transaction where we implemented a switch action based on the value received in the action variable passed by the make decision function. Here we are simply displaying the appropriate message to the user. Let's see how this works. What is the current stock value? Let's say 100. In this case, we suggest to sell the stock. Let's run this again. I'm going to put a value of 20. In this case, suggest we might buy more of the stock. One more time. Let's type 35. Let's wait and see. So the advisor is working as planned. In this video, we are going to learn a new structured command sequence in C called loops. Loops are very useful when we need to repeat a block of code more than once. For example, on different data sets, same data set but with different parameters, or we need to repeat execution until some condition is met. Can you think of an additional instance? Let's examine one such construct in C called the for loop. There are many types of loops in C. This is just one of them. The for loop is very helpful when you know a precise number of times a set of commands or function calls must be executed. The syntax for is quite simple. You have to give it three parameters. One is the start value, the max value, when to stop, and the increment. For example, if we would like to execute something 10 times, the start value could be 1, the max value could be 11, and the increment would be 1. Then the k, which is the counter in the loop, will perform this from 1 to 10. The way this works is k is initially assigned the start value, for example 1. It checks whether that value is less than the maximum value. In our case, it would have been 10, so it hasn't reached the maximum yet. So we are ready to perform, do something and do another thing. Then k is being incremented, and again it is checked against the max value. Since now k equals 2, which is still less than 10, the loop continues, and k equals 3, and so on. Once k equals 10, it's the last time it will be executed if we set the max value to 11. Next time k is 11, it is no longer less than 11, and therefore the loop stops and the rest of the program continues. Let's see how this is implemented in C. For this particular exercise, I set up a very simple example to print a list of all the even and all the odd numbers between 0 and 100. Let's take a look at the function that lists even numbers on line 25. I'm just printing a title first, and then in line 28, I am declaring an index or a counter for a loop, which is then being used in line 29. In my case, the start value is 0, the max value is 100, and the increment is 2, because I want to start from 0 and then print 2, 4, 6, 8, and so on until the last one is less or equal to 100, in which case I will stop. Let's see how this works. At first, I equals 0, and on line 30, I'm printing I. I am then testing whether I is less than 100, which it is. I'm incrementing I by 2, so now I equals 2, and I perform the operation again. Since 2 is less than 100, I continue, I increment I to 4, I check against 100, it's still less than 100, and so on. In a similar manner, I'm using a function list odd numbers, which is identical to list even numbers, with one difference. I starts at 1 instead of 0, because 1 is the first odd number, If I start at 1 and keep adding 2, I'm going to print eventually all the odd numbers between 0 and 100. Notice another small difference. In line 28, I am declaring I outside the for loop. In line 37, I am declaring I right where I need it. It is perfectly fine in C to declare a variable and use it right away. This is not just used for, but it's being used in other instances as well. Either way, it is up to you which option you prefer. Let's run this program and confirm that it indeed works the way we planned. We have to scroll back to the beginning, and we can see already all even numbers between 0 and 100, 0, 2, 4, and so on, and the last one is 100. And then all the odd numbers, 1, 3, 5, and so on, all the way to 99, because 100 is the upper boundary and 100 is an even number. It is worth pausing at this point and reflect a little bit about for loops and a different way to simulate the execution of a for loop. As we saw earlier, the for loop is most appropriate when you know the exact number of repetitions needed and there are no other conditions. The for loop is not the best choice when the halting conditions are dynamic or when waiting for an event to occur. Let's recall our previous discussion on recursion when we first introduced the concept of if as a means to stop a recursive process. Let's examine the following function. We are still printing the even numbers from any number k up to 100. However, we're doing this recursively. A recursive call, it's essentially mimicking the behavior of a for loop, is just not explicit about it. We are starting the function with a given value. We are repeating the call to the function until the value of k reaches 100, in which case the function stops and the rest of the program, if there is one, continues execution. This is not the best choice to loop. It works, it's elegant, doesn't require an explicit loop. However, please recall that each time you are using recursion, for every recursive call, the function creates another copy of itself. Eventually, it drains the computer resources, particularly memory. Let's proceed to an actual C example and compare the for and the recursive calls. Let's look at an example that again prints the even numbers between 0 to 100, and this time we'll compare side by side the use of a for loop versus the use of a recursive function. Just like before, we are listing the even numbers using the same for loop unchanged. We are not going to repeat that. It works just like the previous example. In line 40, there is a recursive function that again starts with a value of k that being received by the function externally in main, except now we don't have an explicit loop. We are simply calling the function recursively in line 47, passing it the value of k plus 2. K plus 2, if we start at 0, would now be 2. In line 47, will be updated to 4, 6, 8, and so on. It will be printed in line 46, and if in line 45 the value reaches 100, the recursion stops. Let's see how this works, and then we'll compare this a little bit further. As you can see, the results are identical. All even numbers between 0 and 100, and then all even numbers between 0 and 100 recursively. While recursion takes much more memory, for such a small number, you haven't noticed any difference, so you might be tempted to think that it really doesn't matter. Actually, it does, because if you were to use a larger number of recursive calls, you might risk into running out of computer memory, your computer might crash, might lock up, and you might necessitate a reboot. While recursion is elegant and it works, use it with caution. In this video, we're going to look at a different type of loop, namely the while loop. The while is a little bit different than the for loop because it doesn't assume a preset or predetermined number of iterations. Rather, while depends on a condition to start and continue the loop. The syntax is very simple. While the condition is true, do something. Let's look at an example. We're setting a variable flag to false, assumed to have been defined previously as an int. While not flag, in other words, while flag is still false, read the next page. That's a function defined elsewhere. Then we have an if. If characters to read equals 0, we print to finish the book, and we're setting the flag to true. Once the flag is set to true, the execution goes back to the while because we reached the end of the while structure. And again we test, is flag false or true? If the flag is true, meaning the condition is no longer valid to continue the loop, the while loop stops. If, however, the characters to read is not 0, then the flag is not set to true, it continues to be false, and the while loop continues. One of the things to pay attention to when using while loop is to ensure that a condition for halting eventually occurs. Otherwise, we may get into a situation of an infinite loop. This might probably happen, especially to beginning programmers, and it's a common error when you write code. So just a word of caution here, whenever you implement a while loop or any other loop, ensure that the conditions for halting the loop eventually will occur. Let's switch to C and see how this works. In this little program, I created two functions to illustrate how the while loop works. The first one, it's called while loop 1, simply prints numbers until a value reaches the number 10. I'm initiating the while loop with a certain value of n received externally. In this case, in line 22, the while loop is initiated with a value of 1, which is passed as an argument to the int parameter n in line 27. I'm initializing a flag to false, and then I'm starting the loop. While not flag, in other words, while flag is still false, print the value of n, in this case will be 1, increment n by 1, and then test, is n bigger or equal to 10? In this case not, because n is currently 2. So the if condition doesn't set the flag, the execution returns to line 29, and we continue to print n, increment n, it's now 3, and so on. When n reaches the value 10, flag is switched to true, and when the execution turns back to line 29, the condition no longer holds, which means flag is now true, the loop stops, and the program ends. Let's test this, and then we'll look at the other function. Indeed, you see the numbers 1 through 9 have printed, and the while loop have stopped. You could say that in this example, we could have used a for loop to print the numbers 1 to 9. I just wanted to show you that you have always options. Think creatively. It is possible in many cases to use one loop to emulate the behavior of another loop structure. In this case, indeed, it might have been more appropriate to use a for loop if you knew exactly how many times you need to iterate and all the conditions were fixed. So this is a slightly different situation in which a flag and a condition for an if were working together. I just wanted you to get the idea that you have now an arsenal of tools. Pick and choose the most appropriate tools to make decisions to create loops as you see fit, and it's more appropriate for a situation at hand. I'm now going to comment this function, and instead, we're going to look at another function called getInputData. The input data, that's something slightly different. We're going to ask a user to enter a letter. We will print the letter back to the user, and as long as the letter does not equal x in line 39, the loop will continue. The loop will only stop if the user enters x. Let's see how this works. I'm going to type A, you entered A, I'm going to type D, G. The loop continues. I can type all kinds of letters. There's absolutely nothing to stop it, short of shutting down the computer. the program or typing X. So this was a great instance where a for loop clearly would not be appropriate because I don't know in advance the number of times I need to repeat the commands. Therefore, a condition was the proper way to go forward. As a finer detail, in case you haven't noticed, the use of the flag equal true or false was allowed because in line 14 and 15, I defined true or false to be equal 1 and 0, as we have seen in previous videos. In this video, we are going to look at a slightly different form of while called the do-while loop. Let's see what the difference is. As you can see, this is also a repeat until some conditions are met with a major difference. In the regular while, we tested the condition in the beginning and prevented execution if the condition was false. In the do-while, we execute the code at least once, and then we determine whether the condition holds or not. So that's the major difference. Let's look at a specific example, which is the same example as before in the previous video with the read page. However, now we are going to read the next page at least once because at the beginning of the do, there's nothing to prevent the loop from starting. Only after the cycle of the loop was completed once and the flag was or was not set to true, only then we are testing the condition. This is a very small distinction, but in some cases, you may want to perform something once. Sometimes you will want to prevent it, and it's up to you to decide which one is most appropriate. Let's look at the code, and we'll look at both of those types of loops side by side and be able to compare. In this code, we are looking at the same exact loop as in the previous video, with one exception. I added a test variable in line 30. The test variable is initialized to 0, and then in line 32 is being assigned a new value of 999. And I'm doing this two ways. First, I have a function called getInputData1, which is a regular while loop, and then getInputData2, which is the same exact function, except in line 46 through line 52, I'm using a do-while. So in the do-while loop, line 46 doesn't test for any condition, so line 47 will be executed regardless of the value of C, which is the character I need to test. Furthermore, I am forcing in line 44 C to equal X, which is the value that I want to use as stopping the loop in line 52. Notice that the condition in line 52 is only tested after the loop has executed one cycle, lines 47 through line 51. In the original while loop, the condition was tested at the beginning in line 31 and execution was prevented. So I'm not interested here in repeating again the cycle of entering letters. I want specifically to focus on the notion that the while loop prevents execution from being carried on. The do while only prevents it once. Let's put this to test. And first, we're only going to enable getInputData1 so we can see what happens. Notice I wasn't even given a chance to enter any type of input. Let's look at the code. I explicitly assign to C in line 29 the value of X, which is my condition to start the loop. In line 31, I'm testing whether C is equal or not to X, and I'm starting the loop only when C does not equal to X. Since C does equal to X, my test variable remains 0 as it's been initialized in line 30 as a proof that the while loop has not even started. At the end of the while loop, I'm displaying the same error message or feedback to the user. You enter X and the loop exited. And the test variable is still 0 because the loop hasn't been started. Let's do the same thing, clear the output. I'm going to comment the getInputData1 and activate get input data 2, and see what happens. Now, I am being asked to enter a letter because I am already in line 48. This is the first time. So that's already a clue that my loop has started. Let's see what happens if I start typing some different letter. I type a D. So my loop has started, and only if I type again X, the loop ended, and the test variable is obviously 999. So even though I explicitly set C to equal X in line 44, the do loop still started and was executed. Therefore, you have to be very careful when you use one loop or the other, as the program will only execute what the programmer is asking it to do. In this video, we're going to talk about one small details, but often it can mean the difference between a working program and a non-working one, meaning the need to break out of loops. Sometimes, either deliberately or due to a programming error, a loop may not end, causing an infinite cycle that drains the computer resources, in addition to the fact that it prevents the program from working properly. There is a command in C called break that lets you break out of a loop or halt the loop regardless of what else is happening. Here's one example. There is a loop, a while loop, that reads a character one by one until the end of line, unless that character is X. If the character read is X, the while loop stops. So if that while loop continues to read characters other than X, it will absolutely never stop. And we want to make sure that there is some condition that will make this loop stop. Let's look at another example in code and see how this works. In this example, I created a simple function called test break. Notice line 25, while 1. This is a typical type of while when we are interested purposely to create an infinite loop. While 1 is always true, which means there's absolutely nothing to stop this loop. Sometimes you will want to have a while 1, an infinite loop, because you have other constructs that will cause some events that eventually will cause the loop to halt. In our case, we have a loop counter and we have a number n that's being entered by the user. The loop counter simply counts the number of cycles the while loop executes, and this entering of the number in line 27, the scanf, is the only real action that this loop is performing. So unless otherwise told, this loop keeps asking the user to enter a number, the user enter a number, and so on and on and on and on, seemingly to infinity, because while 1 is always true. However, here's the little trick to prevent you from doing things that will drain computer resources and help you prevent inadvertent errors. Line 28 has two safety measures. We could have said, let's just say, if n equals 0, then stop the loop. This would mean if the number typed equals 0, the loop will stop. Well, if all we wanted is that, we could have said, while n does not equal 0, do the cycle. However, we want to do something a little more than that. We want to have an infinite loop, so we want an additional safety. Therefore, we have the loop counter. The loop counter is set to 0 initially, incremented at every cycle of the loop, hence the term loop counter. But in line 28, I'm testing whether this value is equal or larger than 10. If yes, then we break in line 29. So because this is an infinite loop, and I want to ensure that there are some conditions under which I can actually stop this loop, I put those two safeties. So in case my prescribed input of 0 for some reason doesn't happen, I have the second safety that I am not allowing this loop to go over 10. Naturally, For a 10, it's not a real drain of any kind on a computer, so I'm using 10 as an illustration because I want to create an example that will run within the time allocated for this video. But imagine you have a very complex program and you want to make sure that the program performs the number of cycles required, but just in case, let's say you don't want this to go over 1,000 or over 10,000 or whatever you decide the limit would be. In this case, no matter what you do, this particular while loop will stop after 9. So let's put this to test. First, let's test the 0 stop measure. I'm going to type a number and another number and a 0, and the loop stops. There's nothing else for me. I'm hitting the keyboard and nothing happened. And we see the word here terminated, which is what the application under Eclipse tells you. Okay, let's run this again. This time, I'm not going to enter zeros. I'm just going to enter just 1. You can see the cycles keep increasing. Cycle 8, cycle 9, cycle 10, and nothing. I'm typing, and you see the note here, terminated. So we used the break command together with a safety lock to prevent infinite loops. There are other reasons why you may want to break, and you will be more experienced and be able to make the choice as you write more code. In this challenge, you will show that you understood how to use loops, which type of loops are most appropriate, and solve a little problem that would require you to use loops. The challenge is pretty simple. You are required to display a bar chart. What is a bar chart? It's a set of dots printed horizontally that represent one bar. If you print several of them, one below the other, eventually they will form a bar chart. You will create one function whose role is to print a single bar. You have to figure out how to do that. Then you'll create another function that calls the first function multiple times, each time sending it a different parameter that represents the length of the bar. It is up to you how many bars you want to print. 5, 10, or anywhere in between would be a good number. But that's totally up to you. Good luck. And by the way, we think it should take you maybe about 20 minutes to figure this out. Let's look at the solution to the challenge of printing a bar chart. It is pretty straightforward. Let's see. We have one function that will call a show one bar function multiple times. The function show bar chart is simply there to be a placeholder for all the bars that will be printed. It's not a very efficient one, as we will learn later on that it is possible. For now, we're just calling the function that prints one bar 5 times with multiple length, as you can see in line 24 through 28, 10, 12, 5, 6, and 8. The most interesting function is the show one bar. Here, we're doing a few things. At the core of this function is the loop in line 33 through 35. It is a for loop that prints a number of dots. By the way, to print this dot, you can use the option 8 key. Bar length is the parameter of the function that decides how many of those dots should be printed. So if I pass it 8, then from 0 to I equals less than 8, which is 7. So from 0 to 7, it's actually 8 dots. So in a for loop, I'm printing the precise number of dots since I know what this is. The only one other touch is before I print the bar, I'm actually displaying the number of dots, the bar length. And if you notice, in the printf, there is a % and then 3D. Because I want to ensure that all the bars will start at the same location, I am forcing the bar length number to be displayed over 3 spaces. For example, the number 20 takes 2 spaces, the number 1 takes 1 space, the number 100 takes 3 spaces. So I assume I will not need more than that because we're not going to write a program that prints very, very, very long bars. So 3 spaces should be enough. Therefore, I am ensuring that every bar starts at the same place on the left side. All I need to do now is, from main, to call show bar chart, which in turn calls show one bar 5 times with different values, and the bar will be printed. Let's test this. Here it is, a bar chart with 5. I can always add more bars as needed. For example, save and run this again. And as you can see, I have another bar chart. So lo and behold, we saw that C can be a calculator. C can give you statistics, financial calculation. Now it can also print graphs. In this video, I am introducing a new concept called array. It is a unique concept to computer programming. All programming languages use it. However, there are slight differences in implementation. Let's see how C is making use of an array, and we'll start with defining what it is. It is simply a collection of elements. For example, 20 numbers, 50 letters, 60 records, financial data. As long as the data are of the same type, they can be stored in an array. Actually, an array is a series of memory locations, each one labeled in a particular way, and all grouped under the name of the array, as we will see shortly. When do we use arrays? Whenever we need to store a temporary list. Temporary reflects the fact that the list disappears once the program ends. For example, while you are playing a game, you may need to store multiple data points related to levels of a game. Data generated by functions for plotting later. You could have any kind of numeric information that needs to be sorted. If we place it in a list, we can write a program that then will traverse the list and sort the data. Vectors in linear algebra that have multiple dimensions, or in physics. We don't know in advance how many numbers we are going to have, so we cannot define variables x, y, z, and so on because we just don't know how many. We will see how arrays allow us to declare lists of data points without knowing exactly how many of them we are going to need. Finally, matrices of data. If you have any kind of experience with algebra, you have learned about matrices, determinants, and any other types of data that requires numerical tables for processing in very mathematical exercises, problems, and so on. Let's switch to code and see how do we declare an array. Very simple. Lines 16, 17, and 18 show a few examples of arrays. The one on line 17 should already be familiar to you because we actually used it in some instances when we refer to a string as an array of character. Now we can see a bigger picture where an array can be an int or a double or any other data type available in C. Line 16 shows an array of, for example, 20 slots in which you can store integer numbers. Line 18, you can only store double precision numbers and up to 50 of them. Another way to visualize an array is a hotel, where at the floor of the hotel, there are multiple rooms. They're all of the same type in the sense that they are all rooms. And we can refer to room number 1, room number 2, room number 3, and so on. In each one of those rooms, we can store any type of data. We will see how this works in the upcoming videos. Now that you saw how we can declare an array, let's look at a slightly different, not necessarily better, just different way to declare an array. So we saw one way, which is an explicit stating the size of the array. For example, int numbers 100, which means I'm declaring an array of type int called numbers that can store up to 100 integer numbers. An alternative way is using a predefined constant. Let's assume somewhere I have defined a constant named max items. I can then use max items rather than 100. Suppose I use that array or that array declaration or that number in multiple places in my program. If I write 100 everywhere, and then I need to change it to say 200, I will have to make those changes everywhere, and I might risk not changing all of them and therefore causing an error. It is sometimes safer to use a predefined constant. Again, if all you have is a very small program with one instant, it's arguable which one is better. I defer to your personal preference and style. Let's look at the code and take another look at this from a slightly different angle. Look at lines 17, 18, and 19. Those are the same three arrays from the previous videos, except now I'm using max scores, max letters, and max data points. I'm actually doing two things here. First, I'm using a predefined constant. Second, I'm using a number that sounds more meaningful. For example, if I would say int scores 20 or 30, it is not clear what that 20 or 30 means. However, if I write the word max scores or max letter, it implies there's some thought or some rules that have been placed onto that program, and it adds another layer of information to whoever reads the program, whether it's the programmer itself later on or another person. However, if you look in this file, there's nowhere a mentioning of max scores, max letters, or max data points. So I did an additional thing. Notice line 13, there's an include constants.age. This is a more elegant way to declare those constants. Let's see what is in this file. As you can see, lines 11 through 13 define those exact data points as max scores, max letters, and max data points as 50. The reason to do that is, first of all, the constant.age is a file separate from the main code. Should I need to modify this, I don't even have to open or touch the main code at all. Second, I may want to share constant.age with other programmers. Many others on my team or on other teams can have access to constants.age, for example, if it is placed on a server. And this can be a common repository of all agreed standard constants for a particular project. We could have a team of game programmers in which, for example, we define a constant max levels. All those programmers will then access the same number in the constants.age. There is no danger that one programmer will work on level 8 if the maximum level allowed is 7. Furthermore, we can create loops and conditions that don't check against a specific number, but check against a concept, max levels, which is then predefined externally. We will see in the upcoming videos more aspects of interacting with arrays, using them in lots of different ways. In this video, we will see how to initialize an array with data once we declared it. We have essentially two choices. Either stating the size of the array, for example, number of classrooms being 5, we declare an array of int that can hold a maximum of 5 elements, all integers. Notice the use of curly brackets on the right-hand side of the array declaration. A second alternative, without an explicit size. For example, we want to have an array of heights that is float, and we're not committing to a particular size of that array or length of that array, meaning the number of elements. The number of elements is going to be preset depending on the number of data points we are entering. We will see the applications of that later on in code when we'll be looking at different problems that necessitate the use of an array. For now, let's switch to code and see those alternatives in the context of a program. Just as before, I am defining 3 arrays, and it's very similar to what you saw in the example. It is perfectly normal to have different types of arrays and different types of initialization. Whether you are using a predefined constant in line 19, like max letters, or an explicit number 5 in line 17 for int classrooms, it is all up to you and what the particular needs of your particular problem at hand are. One thing to note is that whatever you do, you have to ensure that you always allocate the necessary number of elements for an array so you don't run out of space. For example, it is okay to go a little bit over. Let's say you think you might need 50 or 60 data points. It is perfectly fine to go a little bit over and declare an array of length 80 or even 100. It is much more memory efficient to commit yourself in advance to a specific length of the array because it instructs the program to allocate that much memory to it, and it prevents potential problems later on should you have very large arrays for which you didn't request a specific size right in the beginning. One last thing to notice is that the array on line 19, max letters for last name, has been allocated 20, but Mr. Johnson clearly is less than 20 letters. So this is an example where we could allocate more than we needed, but we don't use all of them. And since this is actually a string, the initialization of an array of strings, it's a little bit different than the initialization of the array of numbers. In the upcoming videos, we will start using arrays in computations and solving problems. Now that we learn how to declare and initialize an array, let's take some steps into learning how to access the individual elements of the arrays. One of the most important concepts about arrays is that the elements are indexed, and indexes always start at 0. For example, in our classrooms array of size 5, the first element, 15, is at position 0. Or, in other words, we can say the index of the first element is 0. The index of the second element is 1, and so on. So an array of size 5 uses indexes 0 through 4. For example, classroom 3 refers to the fourth element in this array, which happens to be 23. Okay, so note, the fourth element has the index 3. I am now adding 2 to the fourth element of the array, which used to be 23, and now it is 25. So this is how I can change the value of a data item stored in an array. Finally, if I wanted to print the value of a particular element of the array, I would say, for example, the fifth element is classroom 4, and the value to be printed would be 15. There are more interesting things that we can do with the array. Let's proceed to an example in C code where we'll learn how to pass an array to a function and do things that are a little bit different than what we did so far. In this example, we're going to use the same array for classrooms. So I have defined a constant number of classrooms to be 20, and in line 19, I am initializing the array with the same 5 numbers, even though I have allocated 20. The same line 21 as in the previous video section. Classroom 3 has now been updated to no longer equal 23, but we added 2 to it, so it is now 25. We are printing, as an example, in line 22 the fifth element, just so you can see an illustration of how do we access an element of the array. The more interesting part, though, is the ability to print an array using a loop and passing that array to a function. Even though this is a very short function, a lot of things are going on. So let's start with line 29, and let's look at the parameters of this function. The first parameter is the data name. I would like to have a generic print array to which I can pass the name of the array to be printed. In this case, the name of the array is classrooms. If you look at line 24, I am passing the string classroom onto the print array. However, a string is in itself an array of characters. Hence, in line 29, I'm using char data name, an array with an unspecified initial length that can accommodate strings of any size. Therefore, the argument classrooms in line 24 will be mapped onto the parameter data name in line 29. Second, line 24, the second argument, classrooms, the one without the double quotes. Classrooms is the actual array. Even though when we declare an array, we use the brackets in order to access the elements or to specify its size, when you pass it onto a function, we just need to pass its name. If you look at line 29, int dataset, this is the name of the parameter of the function print array, that is an array itself. In line 24, we are passing the array classroom, the second parameter, into int dataset. So internally to print array, classrooms now becomes dataset. Finally, in line 24, the third argument is number of classrooms. This is simply an int, which is defined in the function in line 29 as int data length. To summarize, when we call the function printArray in line 24, we use 3 arguments. Each one of those arguments is mapped in order to one of the 3 parameters that are defined in printArray in line 29. Let's go further into that function. You have already learned that you can use a for loop to perform an action if you know the exact number of times you want that action to be repeated, which is exactly this case. We know the length of the array, and we know that we want to execute this the exact number of times as the length of the array. In this case, we are using, in line 30, a for loop that runs from 0 to the number of classrooms. Another reason why it is a good idea to have a predefined constant. Inside the loop, I would like to print 3 things: the name of the array, the content of the array, and the index itself. Therefore, we start with the data name. The data name is now a string that equals classrooms, because this is what has been passed from line 24 as an argument to line 29 as the data name, to line 31 as the name of the array. So note here that when you want to refer to an array as a parameter to a function or to do something with it, you simply use its name. When you want to access a specific element of the array or to populate it, you have to use the bracket notation with the appropriate index. Since in printf, data name is a string, we're using the directive %s, followed by square brackets because this is the format I want to display when I print. I want to display the actual position of the element currently printed in brackets, followed by the last %d, which is the actual value of the element at that position, which is dataset bracket I at the end of line 31. So the printf prints the name of the array, the current position being printed, and the content of that position. This way, I have created a generic print array function that is capable of receiving as parameters any array name, any array length, and it will print it. Let's see how this works. Since this doesn't expect any input from the user, I simply hit run, and now we can see several things. First of all, the printf in line 22 simply printed the content of element at position 4, which is actually the 5th element in the array. Then we are printing the entire array. Please recall that the array was set at the maximum length of number of classrooms, which was 20, even though we only initialized 5 of those positions. Therefore, positions 0 through 4 have the numbers that I have entered in line 19, except position 3, which has been updated in line 21. It used to be 23 initially, but then we increased that by 2, and it's now 25 in line 21. So if you look at the printout, classroom 3 shows 25. Another interesting thing to note is that when we initialized the array, the C compiler decided to place zeros in every position of this array. So when you initialize an array in C, it is automatically assigned zeros. This thing is important to notice because sometimes you might involve computations and you may want to do some mathematical calculation that would involve dividing, and if you are dividing something by 0, you might get an error. Therefore, it is advisable before you use arrays, ask yourself if it is okay to have the array pre-initialized to 0, or you may want to initialize it using a loop to something else. And because we haven't specified any other limitation but just printing the entire array is being printed from 0 to 19, which has 20 positions. Let's look at a different type of array. This time, it's what we call a two-dimensional arrays, and let's see what this means. Two-dimensional arrays are essentially tables or matrices that have any number of columns and rows. For example, this is a table that has 2 rows and 3 columns. Hence, the definition of the array is table brackets 2 brackets 3. We initialize the array following the same principle as a one-dimensional array, except we have to provide 2 sets of numbers within curly brackets. Because we have 2 rows and 3 columns, this means there's going to be 2 sets of numbers in curly brackets. In each set, there's going to be 3 numbers. Other than that, the principle is the same. The other thing to notice is when we refer to a specific element of the array, we have to provide 2 indexes, one for the rows and one for the column. In this example, if I want to refer to row 1, column 2, I would have to type table 1, 2. Since we have 2 rows, row number 1 is actually row 0, because if you recall, the indexes in the array always start at 0. So we have 2 rows, row 0 and row 1, and we have 3 columns, column 0, column 1, and column 2. Therefore, position 1, 2 in the array is row 1, column 2. Row 1, it's actually the second row, and column 2, it's the third column, which means the number 872. Let's switch to code and learn a few more things about this. The same array as we just saw is now being initialized in line 22 with the same exact numbers, and we are going to print in line 28 the same location 1, 2. There's nothing new here. What's new is in the way we are printing the array to look like a table. I'm going to run this first so we can have a visual of how this works, and then I'm going to explain a few things because some of those are not trivial. So as we said already, row 1, column 2 contains the number 872. If you look at line 24, this is row 1, column 2. Below is the output of the printable function, which indeed looks like the array. Let's take a look at how this happened. First, my print table requires 1 argument because it has 1 parameter. Look at an interesting thing. Recall that when we had a one-dimensional array, we simply said the array name and then brackets. When you have a two-dimensional array, in this case in line 35, we're using int table. For the rows, it's open brackets, but for the columns, this is not. This is not a peculiar thing. It's the way memory is being allocated by the C compiler when you want to use an array. We will discuss the reasons why is this way in the upcoming video when we talk about pointers and memory management. For now, let's just accept that if you want to refer into a function parameter to a two-dimensional array, you have to specify the row component of the array in open brackets, with no value inside, and the columns, you have to specify a number. Moving on, line 36 is just a label, so we know that we're printing the table. Now we're starting loops. You already know that in order to print an array, you have to use a for loops. Well, if we have 2 dimensions, we are going to use what is being called as a nested loop. We need one loop to print all the rows, and for each one of those rows, we need another loop to print all the columns. That's why we have the inner loop in line 38 through 40 that prints the columns, and the outer loop on line 37 that ends in line 42 that prints the rows. So we have the outer loop runs number of rows time, the inner loop runs number of columns time, and eventually when we print table ij, because those are the indexes for rows and columns respectively, we are ended up with a table. Finally, 2 more things. Line 39, printf %4d. Because I happen to know that the maximum element in the array has 3 digits, I'm going to allocate 4 spaces to each element of the array in order to have the array displayed correctly and all the numbers aligned. Second thing to note is line 41, printf. The reason we need that is still inside the loop for rows, each time I finish printing a row, I have to advance to the next line so that the rows are printed one below each other. And that's it. It is now the time to discuss some rules for using an array which will save you a lot of time and headaches later. The number 1 rule about arrays is to watch the index. It's the pitfall in so many instances that you really have to be very careful and instill this into any practice. There's a very simple rule actually. The index must be within the range of the array. It always starts at 0 and it ends at the length of the array -1. So if you have an array of 5 elements, the index runs from 0 to 4. Let's look at an array that's initialized with those numbers for a length of 5. And let's set up a number to 0. I want to update list k, which is 0, and add 2 to it. This means the first element in the array at position 0, 23, has now become 25. So far, so good. Now I'm going to set k to 5. Now, recall there's only 5 elements in the array, which means the last position is 4. I am now attempting to add 1 to the value stored at position 5. What do you think might happen? You have to remember a second thing about C. The compiler assumes you know what you're doing. When you are manipulating the array, you have to be extremely careful because you may do things that are incorrect, but the compiler will not tell you. And let's see this in action. I copied the same exact code from the previous screen into the C program here. Very simple program, which is going to print 3 things. The 3rd element, the 6th element, and the 20th element of an array that only has 5 positions. First of all, let's compile this. I'm going to build a project to compile it, and notice there are no error messages. So the fact that I am attempting in line 23 to print a number that doesn't exist, as well as in line 22, which lists 5's position in the array, it doesn't generate an error. Compiler assumes you know what you're doing. Let's see what happens when I'm running this program. It tells me the 3rd element is 15, which is correct. 0, 1, 2, which means elements 1, 2, and 3. That is correct. The 6th element is 1. There is no 6th element defined in the array. There's only 5 of them. Where does this 1 come from? The 20th element is 32,767. If you inadvertently access or try to access a location in an array that doesn't exist, the results are unpredictable It may range between getting an erroneous result in a calculation to crashing something to coming up with completely ridiculous outcome in a program. And this is all because there are no errors, so you may assume that everything is okay. There is one thing that the compiler might do for you. Sometimes it might issue some warnings. In this case, there are no warning issues, so you are completely on your own. Again, remember to always use an index within the range of the array. It is up to you to manage the values of those indexes correctly to avoid situations like that. We will wrap our discussion of arrays in C with two main functions that are very likely to appear in lots of your projects: searching and sorting. Let's start with search. Searching for data is enabled by you using an index to run through the entire length of the array. Obviously, there are lots of algorithms out there for different ways for efficiently finding data, and this is beyond the scope of this course. In this class, we will just talk about a very simple approach for finding a data element in an array. The principle would be that we will run an index throughout the entire array, and then we'll test against a criteria that's of interest to us. In this particular case, let's assume we have a data set of MPG ratings, miles per gallon, of 10 imaginary cars. And we are interested in those cars whose MPG is larger than 32 or larger than 30, for example, any number. I'm going to run an index I from 0 to 9 because the array is of length 10. And at every cycle of that for loop, I will ask, is the current element of the array I larger than 30? If yes, I will print it. I will print its index and value. Pretty simple. We will see all this in action in the code shortly. The next item is sorting. To sort an array, it's not an easy task. There are lots of algorithms out there. Some are more efficient, some are less efficient. Today, we will focus on just the heart of an algorithm called bubble sort. However, this technique applies to other algorithms as well. At the heart of bubble sort is the ability to swap two elements of an array. You need a three-step set of statements in order to swap two elements. We want to swap the element at location I with the one at location j. We do that in three steps. Step number one, we're going to move y into some temporary location called temp. Then we'll move j into y. Remember, we didn't lost the yth element because we stored it in temp. And now we are overwriting the j's position with whatever we stored in temp. So at the end of the three steps, we swapped the elements. We're now going to look in code at two implementations of a searching method and a bubble sort method to sort an array of 10 elements. Let's take a look at an exercise that demonstrates how can we search and sort data in an array of 10 elements. The array is defined in line 24 as containing 10 floating point numbers. We're going to search some data in the array, and we're going to do that in two separate steps. For now, I disabled the bubble sort function that sorts the array, which allows us to focus on line 26, which is search high MPG, all those data points that are larger than 30. Let's run the program, and we'll see how this works. So listed here are all the cars that exceed 30, because if you look at the data, we have a 32, a 40, a 31, and a 35. Okay, those are the four ones. Now, let's see how this works. First, I am printing a message that verifies that I'm now calling this function, and I'm using a helper function, print array, which is the one you saw in the previous video, so we're not going to go over this right now. It's simply a loop that prints the elements of the array. Now we're going to look at the heart, which is right here. All this is, just like we saw in the previous part of the video, we traverse the entire array and we ask, is the data set I, which is the way the array is referred to inside this function, larger than the value that was passed as a parameter? If yes, then this is now going to be printed. If not, it's being ignored. It is not the most efficient way, but it works, and for such a small data set, that's fine. Let's focus on the bubble sort, which is a little bit more difficult to comprehend the very first time you tackle this in C. First, let's explain what bubble sort does. It simply traverses the array once and swaps every pair where the pair consists of a larger and a smaller element. So if I compare position 1 with position 2, if position 2 is smaller than 1, then 1 advances. Then I'm comparing 1 with 3. If 1 and 3 needs to be swapped to be sorted, then 1 advances further. So by the end of the first traversal of the array, I have the larger data point where it's supposed to be. Then I repeat the procedure again, and I'm sorting the remaining data points. And I continue as long as the array is not entirely sorted. This is not a very efficient way to sort, but for the purpose of this video, it illustrates two things. That you can sort an array, you can apply a method that's systematic, and eventually the array will be sorted. Plus, you get to practice swapping data in array, for loops in the context of the array, and other manipulations of indexes that are essential for the understanding of how arrays work. At the heart of this, there is an outer loop. It's a do-while loop that continues while a flag named swapped is true. To help you understand how this works, I inserted in line 50 a printf command that will help you see each time a do-while loop cycle starts. And I also inserted one inside the for loop, so you can tell each time you are inside a for loop cycle. We are performing the do-while as long as the swapped flag is true. Initially, it's being set to false so that I can test the comparisons. The swap does exactly what I showed in the earlier part of this video, meaning you are using a temp or a temporary location to aid in the swapping of elements at position I-1 and I. Since I is a running index, we are traversing the entire array, and we keep checking if two elements that are adjacent to each other, naming position I-1 and I, need to be swapped. If they need to be swapped, we're swapping them all the way to the end of the array. So each time we traverse the array, we swap as needed, and with several traverses like this, the entire array is being sorted. Let's run this and see how this works. It is enabled, so all we have to do is save the file and run. Array received by bubble sort is the initial array. You can see it's unsorted, and now we started the do-while loop cycle 0. Inside the do-while loop, we have one for cycle, and as you can take a look at 40 keeps being swapped. The first 4 happens to be sorted already, so the next time we're going to sort is 40 and 24. We keep moving. 40 now has been swapped to 24. 40 now has been swapped to 31. 40 now has been swapped further with 16. And when we're done with the cycle, 40 is now in position 9. We are done with one traversal. Now we're starting another do-while loop and find the next largest element of the array that is not yet in a position. We keep traversing, and we don't find one until all the way cycle 9, and now 35 is in place. Now we start in do-while loop cycle 2, and so on. If you follow this data, which I suggest you print out and go line by line, compare it with the code, you will in no time be able to understand and then even improve. In this challenge, your objective is to improve on the previous challenge you worked on with the bar charts. The main objective at the higher level is to continue to learn how to solve problems using loops and arrays and creatively integrate multiple concepts we cover so far in this course. Specifically for this problem, look at the same challenge as in Chapter 0906. Revisit the bar chart program, and if you haven't been able to look at it yet, please do. Generate a random data set. That's an improvement over the previous program. The data set should consist of integer numbers in a given range, for example, between 0 and 50. I will show you how to generate random data numbers in a minute. Then you will store the data generated into an array called dataset. You should have a function that generates the dataset and populates the array. Then, in the function that creates the bar chart, read the data stored in the dataset, meaning in the array, and print it in the same manner you did it for the previous challenge. Let's see how we generate random numbers in C. First of all, place the following include in the header. I will explain in a minute why. Second, call this function sRandom from the function that you use to generate the data to populate the array. Finally, in the loop in which you assign a data value to each dataset element of the dataset array, insert this line. This will create a random number between 0 and 49. How does this work? The C compiler has a built-in random number generator. It's not really a random number, but is using a mathematical formula to generate a series that has all the attributes of random numbers. In order for those numbers to be different each time, we need to initialize the series with a unique number. That unique number is the current time in milliseconds. Since the clock moves continuously and time never repeats itself, by accessing the current time in milliseconds, we are able to ensure that each time you run the program, the random generated sequence will start at a different place and therefore will be different. There is much more to that, but this is sufficient for the purpose of this exercise and for the scope of this particular introductory level course in C. The random function, rand, it's another built-in function in C that together with the modulo function, 50, allows you to generate integer numbers between 0 and 49. We estimate that the total time for completion of this exercise is about 30 minutes. Good luck. Let's look at the implementation of the solution to the challenge of drawing a bar chart using functions, arrays, and loops. First, as I explained in the challenge description, in line 15, I am including an external library called time.age that allows us to receive information about the current time. Second, I am defining a data size of 10 in case I would like to change that later across multiple places and do it all from one place. Then I will have 3 functions. The only one that's different from the previous implementation of the bar chart program is in line 24, set data values. Let's take a look at this function. This function is supposed to generate a set of random integers and populate an array called dataset, which has been defined in line 26 as a global int values dataset of size data size currently set to 10. The way we generate the datasets are as follows. In line 40, I'm calling a function called sRand. S stands for seed the random generator, which uses the current time in milliseconds to kickstart a process of generating a unique sequence of random numbers. Then, inside the loop that starts at line 41, there is a call to another randomly generated number, meaning the rand modulo 50. The rand function generates a random number. The modulo 50 ensures that that number is between 0 and 49. Finally, I am assigning that randomly generated data point into the appropriate location in the array. And because this is part of a for loop that goes from 0 to data size -1, because I is less than data size, I am ensuring that the entire array is being populated with random values between 0 and 49. Finally, the show bar chart is an improvement from last time. If you recall, in the previous exercise, we had multiple calls explicit to show one bar with a different number. Now, because we know loops, we have placed the same call to show one bar, except now we're doing it in a for loop, again, from 0 to the data size -1, because the arrays are being of the same length regardless of what function we're using. It's the same array and the same data length. The only thing that's unchanged from last time, it is the show one bar. It's exactly the same. It is a loop that prints dots based on the bar length that's being passed to it. In this case, line 52 calls show one bar with the argument dataset I. Dataset I is the ith element of the dataset that currently holds a random number that was populated by the function setDatasetValues. Let's run this program and see what happens. As you can see, this is a very nice bar chart. Furthermore, I can repeatedly click and rerun the program again, and each time I'm generating a new set of data. We have just created a general purpose random data generator and are able to plot it in a bar chart. In some respects, a pointer is just a type of variable. However, it's a very different type of variable. For starters, it is a variable used to store an address in memory. It reminds us that C is not just a high-level language, as it's evident from working with it so far, but also allows us to manage memory directly in ways that are very, very sophisticated, and you really need to be careful because you can access things that could cause damage if inappropriately used, or may cause a program to work incorrectly. Let's look at some declarations that are possible for a pointer. Because a pointer stores an address, it has to point to a particular type of data. This is an example of a pointer that can store an address of an int. This pointer, letter, stores an address of a char, and this one, the address of a double. Note the star that precedes the pointer. This star is always an indicator that the variable is actually a pointer. Let's see how this looks in a C program, which is identical to that. In this program, we have the same exact variables, pointer, int, letter, and price. The same rules that you use to name your variables, the same location you use to place your variables and declare them still hold for pointers. The only difference is the star in front of the pointer definition and the fact that you have to remember that every pointer can only point to the address that was used when it was defined. We will now gradually learn more about pointers and see what are they good for and why they're so important. In this video, we are continuing our discussion on pointers, in particular, how to declare and initialize a pointer variable. When you declare a variable, you typically say, for example, int size, and we assign the value 15. To declare an int pointer, we simply put a star in front of the pointer variable. Now we have two types of declaration, one for the regular variable of type int, and the other of a pointer, meaning a variable that stores an address of size int. That pointer doesn't store anything yet, it's simply capable of storing an address of type int. Now we can actually assign a value to the pointer int, and we assign the value of the address of size. Size is an integer whose value is 15. Now the pointer stores the actual location in memory of that variable size. To do so, we use the ampersand sign just to the left of the variable name. So we have three things going on here. Let's see the same thing in code. The same exact thing, line 20, we have now assigned the address of the variable size to the pointer named pointerInt. If you recall, all memory in the computer is labeled by hex numbers or binary, depending on what mechanism you use to access them. When you store a value in a variable, essentially you are picking one of those hexadecimal labels of memory locations and store some data in it. The pointer gives you a mechanism to refer directly to that address in memory. However, you don't have to know the hex value, although you could, but it simplifies the memory management by using the variable and its address through the ampersand. One thing to notice is not to be confused by the semantics. When you use the pointer itself, you use the star. When you use the address, you use the ampersand. We will see more how we can use pointers and addresses they point to in the upcoming videos. Let's continue our discussion of pointers. In this video, we will look at how to use a pointer variable. Again, we are going to compare variables versus pointer variables. When we declare them, we declare a size equals 15 as an integer variable. We're now going to declare a pointer also to an int. So far, these two are unrelated. One is a variable, one is a pointer that is capable of pointing to an address of type int. Now we're actually going to assign a particular address, that of that previously declared variable size. Now, pointer size is a pair. Pointer stores the address of the variable size at which 15 is being stored. To confirm that, we're going to use a simple printf command to print the value at the address the pointer points to. Let's see how this works in code. We have the same exact declaration. We declare int size equals 15 in line 16. Then we have a pointer of type int. And finally, we assign the address of that number 15 to the pointer ptr. Now we're going to instruct the compiler to fetch from memory the label of the address where the number 15 is being stored. We refer to that address in our program as the variable size. However, there is a hexadecimal number that's internally represented by the modules of the operating systems that manage memory. Let's run this code first, and then we'll take a look at line 21 and explain in details what happens there. As you can see, the address 54DE1C88 contains 15. The number 54DE1C88, it's a hexadecimal number that represents some memory location. We do not control necessarily where numbers are stored, but we can definitely know where they are. Let's look at line 21. Notice the directive %x. Whenever we want to refer to a pointer, we are using x and int in that case. This particular pointer is a pointer to int, which means itself is just like an int variable. Therefore, we are using the directive d for the star ptr. If you look at line 18, ptr without the star is a variable that stores the address of another int. Therefore, when we write in the printf statement %x, we use that in conjunction with a pointer, and this extracts from the ptr variable its content, which in this case is the address. To recap, star ptr is the pointer. ptr is the variable associated with the pointer definition that stores the actual memory address. And as you can see, it's a hexadecimal number. And at that address in memory, we have the number 15. Without pointers, we would refer to that location as the integer variable size. We have no idea where in memory it is located, and until now, we did not need to know. Now that we have the power to manage memory directly and read, and we'll see soon, place values at specific location, this allows for all kinds of interesting things that we can do in C. They are as interesting as they are dangerous. So I'm going to caution you to be very careful when you use pointers, because the results are not always predictable for the novice programmer. And as you have seen before, the computer and the compiler assumes you know what you're doing and will not always issue an error message if something goes wrong. Something may still be right from a syntax standpoint, but be wrong from a logical of the program standpoint. Now we're starting to get to the fun part about pointer arithmetic. Let's see what this is about. One of the most important features of pointers is that they are closely related to arrays. If you recall, an array, it's essentially a collection of elements grouped together as long as they have the same data type. An array is actually a closed depiction of the memory of a computer. When you are storing numbers into an integer array, for example, sizes, essentially you are grouping a set of memory locations under the label sizes, and then you refer to them as sizes 0, sizes 1, and sizes 2 to correspond to the 3 elements stored in that array. We can now use a pointer to point to the beginning of that array. This is a pointer of type int because the array is also of type int. And the pointer needs to be able to point to addresses of the same type as the array. Notice that the variable sizes without the brackets is the storage place for the first address at which the array starts. Now we have a hook. We have a PTR variable, a pointer, the one with a star in front of it, that tells us exactly where the array begins. If we are incrementing the PTR or pointer variable, we are not adding anything to the array. What we're doing instead, we are telling the pointer to advance to the next value of the array. Whether that value is a contiguous part of memory or jumps to a totally different location, it's inconsequential at this point. We are treating the group of 3 numbers as 3 values stored in memory, and we can move from one to another using, in a sense, the pointer as an index to the array. We can then move back to the first value of the array because we are now using the minus minus. And this is now a mechanism that lets us point to specific items in the array, referring to them using the pointer. Let's look into the code and see what actually is being stored at the pointer address. I am declaring again an array sizes and storing inside it 3 numbers, 15, 20, and 30. On line 17, we are declaring a pointer and are initializing it with the beginning of the array by assigning the value sizes without the brackets. We are telling the pointer that this is where the array starts. We now have a hook at the start of the array. On line 20, we are incrementing the pointer. On line 23, we are incrementing it again. And I will show you that incrementing the pointer allows us to point at various elements of the array. Let's run the program and look at the code in parallel. The first printf statement, that's the address of the beginning of the array. And indeed, we see that at address 58CA5C78 stores the value 15, which is also the first element of the array. We are now moving to the next address, which is the value 20, and we move there in line 20, where we incremented the pointer by 1. Incrementing the pointer is equivalent to moving to the next element of the array. I am repeating that procedure again in line 23, so we can move to the third value of the array. And if you notice, 15, 20, and 30, the values that are outputted by this program, are exactly the numbers stored in the array. Finally, I want to go back to the beginning of the array. Since in line 20 and in line 23, I incremented the pointer twice, I have to decrement the pointer twice as well. Line 26 and line 27 decrements the pointer twice, and when you print it in line 28, you can see that it again points at the value 15, which is stored at the beginning of the array. We can now better understand the relationship between pointer and arrays by looking at ways in which we can move across the array and point at the addresses that the array stores. Let's look at a few characteristics of that relationship. For example, the arrays store data in a sequential block, which is very helpful if you are going to refer to them starting with one particular location and then advance one position at a time. Pointers are variables that point to the beginning address of an array and retrieve the value stored at that address. An array notation is essentially a pointer notation. Let's see how pointers enable powerful access to memory, and the easiest way to do that is in code. I defined an array named data. It's an array of int that has 6 values and a pointer who is being assigned the location of data. So now the variable pointer, ptr with a star, points to the beginning of the array. Now I'm going to use an interesting property of the array. I would like to know what is the length of this array. And I'm going to do this in the following way in line 21. I am dividing the size of the entire array using size of data. It's a function we encountered in one of the earlier videos when we discussed the sizes of various data types. So I am dividing the size of the entire array by the size of int, which is the data type of the array. Because each one of the elements of the array has exactly the same data type, and the factor that distinguishes one data type from another is its size, if I have the sum of sizes, I divide that by one of the sizes. The result is the number of elements in that array. We will verify that when we look at the code that prints in line 22 the number of elements. Finally, now that I know how many elements are in the array, I can use it in line 24 to write a for loop that will traverse the array and then use the pointer in line 26 to point to each element of the array at every cycle of the for loop and print the content that's being stored at that location. So this way, I'm able to point to the specific elements in the array without using the array name, without using an index to the array, and essentially I am showing that array notation is pointer notation. I can either refer to that notation as data with an index, or I can refer to a pointer and whatever the pointer points to. Essentially, we have two labeling systems for the same exact data structure. Let's run the program and see what happens. If you look at line 18, print data starts at address and so on. If you look at the first line of the output, it tells us that data starts at address so-and-so 5761160 with a value 15, which is the beginning of the array. And there are a total of 6 elements in the array. We computed that in line 21 by dividing the entire size of the array by the size of one element, and it has indeed been confirmed that the array has 6 elements. I am now able to use that number 6 in line 24, where I am performing a for loop starting with location 0 all the way to num elements minus 1, because I is less the num elements. That's the boundary to finish the loop. And I am incrementing the pointer. First, I can print the value of the pointer, which is the address, and what it points to. That's the star PTR, because I already have a pointer to the beginning of the array. Then in line 26, I increment the pointer and continue the loop and keep printing all the elements of the array and their respective addresses. We're going to wrap our discussion on pointers by learning yet one more very powerful feature related to managing memory and the function malloc. Let's recap the relationship between pointers and arrays. Static arrays waste memory because you have to allocate, for example, in this case, 20 positions just in case you might need them later. When you declare an int array 20, that memory block, whether you use it or not, is being set aside for this array and nothing else, no other program, no other function within your own program can use it. There is a better way to declare arrays using pointers. The function malloc, which is short for memory allocation, will set aside also initially 20 times the size of int, which is essentially the same thing that we did the line above with an int array, except now we are simply pointing the array named pointer array with a star in front of it to point to a location that could potentially be used by up to 20 integers. We don't have to use all of it. When we are done working with the array, we are going to call another function called freeArray. This is a library function built into the C language that in conjunction with the operating system, it frees up any unused memory of the array to be returned to the pool of memory or the memory heap so that other applications can use it. Let's look at the code and let's get some more insights into this. Just for illustration purposes, I declared an array called int static array. That array is not used in this code. It's just there as a reminder that once you declare that static array of size 20 ints, it doesn't even matter if you use it, it is being allocated and the memory now has been wasted. The better way to do that would be in line 21 is to allocate an int, which I call dynamic array, using the same malloc function of 20 times the size of int. This means that I need an array of size 20, pretty much the same one as the static one, except now you will see that this is a much more efficient way. How do I store something in this array, even though I didn't call it an array? Line 22, I store at the beginning of the array the value 10. Please recall that from a previous video, we showed that a pointer to an int can be assigned the value of the beginning of an array. In other words, if the pointer can point to the beginning of an array, I don't need the array itself because I'm just going to manage memory directly using the pointer. I am assigning now the number 10 or the value 10 at wherever dynamic array points to, and de facto, this is now the beginning of an array. We are going to print the value and convince ourselves that this works. Line 25, notice that I am treating dynamic array as if it was already declared as an array, which it hasn't. Only static array in line 17 has been declared in the traditional way of an array. Line 25, dynamic array, there is no such declaration. This is again a further illustration that arrays and pointers are essentially the same notation. I'm going to assign the value 20 to position 1 in the array. Let's print this and see what happens. Address 75C038A0 stores value 10. This comes from this line right here, line 23, because I have just assigned 10 to the beginning of what I refer to as an array. Then in line 25, I'm placing 20 at position 1, and I'm using the same type of printout as if it was an already pre-declared array. Finally, I'm calculating the size of this dynamic array, and it's 8 because each one of the cells of the array or the elements of the array is an int, which is 4 bytes, a total of 8 bytes. Now, recall that I have allocated 20 ints for this array, but I only used 2. Therefore, the command in line 30, or the function free dynamic array, returns to the memory heap 18 positions that are unused since I only used 2 of them. This is a much better way of using an array. It allows later on a pointer to continue to point to different elements and add them to the array, thus using only the amount of memory needed without the waste associated with pre-assigning a static block without any knowledge whether it will be used in its entirety or not. In this video, we will discuss a new concept in the C programming language, structures. Let's see what they are. Structures are an entity that allows us to combine multiple types of variables into a single one. For example, chars, integers, and floats. We can define a complex type beyond the standard built ones. For example, we may want to have a vector that has 3 floats designating its 3 dimensions x, y, z. And we can create those complex variables and manipulate them as if they were just one variable. Let's see how this looks in C. This program shows a very simple definition of a struct using 3 variables that are packed into a struct in line 23 called book. A book is typically associated with a title, an author, and a publisher. But we want to refer at the book as one entity. Therefore, we are going to define 3 arrays, one for title name, one for author, and one for publisher. Those are arrays of characters, also known sometimes as strings. In order for be as generic as possible, I defined 3 admissible maximum length, one for title, one for author, and one for publisher in line 14, 15, and 16, respectively. I have now created a new type called book, which for all intents and purposes, it's now added to my list of available types, including those built in. So now I have int, float, double, and book. We will see in the upcoming videos how we can put that to use. In this video, we will further our understanding of how structure works by declaring them and accessing them. Let's look at an example of a structure that could be used to designate the characteristics of a person. We will call this struct person, and we will assign 5 fields, 2 of them being first name, last name, followed by age, eye color, and height. Notice that we have 3 character arrays, 1 integer, and 1 float, yet all these 5 fields are packed into one type. For all intents and purposes, they are treated in the same manner as we would treat any regular type that we had seen so far that are built into the language. This is how we would refer to a struct. First, we're going to declare a variable of the same type as the struct. So struct person citizen means that citizen is now a variable of type struct person. We can now refer to the fields of citizen using dot notation. Citizen.age refers to the age field or the age characteristic of the struct and is being initialized to 38. Those are, for all intents and purposes, regular variables, except they are part of a more complex variable called citizen. Let's see how this works in code. First, we're going to declare 2 constants that will help us with arrays which are going to be part of this struct. And since we're going to use string manipulation, we're also including the external library string.age. This is the array first name, the array last name, the array eye color. Those are the 3 arrays that are using the defined constants in line 16 and 17. First name, last name, age, eye color, and height, together are packed into one type, person. We are also defining a function print structure to allow us to print a complex variable. First, let's initialize the struct with some data using a variable citizen. So citizen is now a variable of type struct person, and we can populate its fields, age, height, last name, first name, eye color. Notice that while 35 and 36 are regular variables that can be populated through a simple assignment statement, last name, first name, and eye color are strings. To populate the string, we are using the strcopy command, which we already saw in the video dedicated to strings. We are assigning Johnson, Sasha, and Green, respectively, to the three corresponding arrays of characters or string, and we are now ready to call a print structure function, which I defined specifically to be able to print this structure. Notice that I am passing the citizen argument to the print structure function as if it was a simple variable. The function is defined as having one parameter, which is named individual, and it's of type struct person. Inside that function, we have 5 printf statements, each one corresponding to the type it's printing. For example, first name and last names are strings. Therefore, we are using the directive %s in printf. Age is an integer, and we're using the directive d. Height is a float, and we wanted to only have one decimal point in line 51. And eye color, again, is a string or an array of characters. Let's run this program and see how this looks. As you can see, the values with which I populated the array are now printed. So if you want to print a single value or several discrete values, you use the regular printf. Now, this program gave you an example of how to define a custom type, initialize a variable of that custom type, and then create a printing function for that particular type. We are going to advance our knowledge of structures, and we'll see how we can manipulate them, treating them as the complex variables that they are. In this example, I am defining an array teams of size 10, in which each element is a struct person. So the type of the array is struct person. In order to access or assign a particular value to one of the elements of the array, I have to use the regular array notation, in this case, teams 0, the first element of the array, dot the field of the struct that I wish to change. So team0 dot first name equals Bob. This means the first name of the first person in the array is Bob. Team5 dot age equals 30. The age of the sixth element of the array, which is in the position 5, is now 30. I can also use the for loop in order, for example, to print the array. I can run a loop with an index from 0 to 9 because I is less than 10, and there are 10 elements in the array from 0 to 9, and then print all the last names and ages of the elements of this array. In a way, I can treat this array as a mini database, and we can see now how a lot of these concepts are coming together. Arrays and variables and loops and structs and types and so on. Let's see how we do that in C, and we can do even more interesting things with it. In this example, we will see how can we access arrays of structs and treat them as if they were a mini database. First, I am defining a struct named person similar to the one we used in the previous examples, line 24 through 30. Then, I am creating a bank of names. Those are 3 two-dimensional arrays of characters because they are arrays of string. Please recall that a string is itself an array of characters. So in a sense, what we have here is an array of arrays. Hence, in line 33 through 35, we are using the two-dimensional array notation. So the bank of first name has one dimension, max names, which is defined above here as 14, and a second dimension of max name length. This is the maximum allowed string length in that array. The same goes for the bank of last names and the bank of iColors. Now I'm going to use two functions. One is to print a structure, we have seen that before, and one is to populate array of structs. Let's look at the populate array of structs. Essentially what I'm doing here, I am choosing random entries from the bank of data and populating an array of structs, which I define as a global variable. That array is called teams. First, in line 53, I'm seeding the random generator with the current time. You may have seen that function before if you looked at the challenge from the previous chapter. Then I am starting a loop that starts at 0 and runs through the entire length of the array teams using max teams predefined as the upper boundary of that array. Now I have to choose a random number in line 57 that has a value within the range of the bank of first names. Line 58, a random number within the range of max names. Then in line 59, a random number for a position within the range of the array colors. Therefore, I can now use those random numbers as index positions in their respective bank of data, and then assign that to the team in the I position because I'm now in the for loop. So at every cycle of the loop, I am selecting random positions from my bank of names, iColors, and so on, and I'm assigning them to the teams array. So for example, line 61, I am choosing a random number from bank of last names using RL, which is the randomly computed index for that array, and I'm assigning it to teams I dot last name. Finally, line 63 and 64, it's a straightforward assignment, teams I dot age, teams I dot height. I'm choosing a random number for age because I am defining above max age to be 120, so any age up to 119 would be okay in this program. And then line 64, it's a little bit of a calculation because I'm trying to pick a random height. Because I want to display the height as inches and feet, I'm going to pick a random number for inches and a random number for feet. The random number for feet is 4 plus a random number less than 3, so 0, 1, and 2, which means the feet could be either 4 plus 0, 4 plus 1, and 4 plus 2. So I'm allowing to a maximum of 6 feet, plus a random number between 0 and 9 in inches. Finally, the print structure is the same as in the previous example. Let's print this and see what it looks like. Notice that the array is nicely formatted because I allocated spaces according to the size of each data type. For example, like 71, I allocated 8 spaces for first name, like 72, 9 spaces for last name. In this video, we are going to look at a related topic to structures, namely unions. Unions are similar in many ways to structures, but they enable storage of different data types in the same exact location. For example, the declaration looks very familiar. Union symbol, it has an int field number and a char field letter. Very similar to a struct, except we're using the word union instead of struct. Here's an example of how we would refer to one. We are declaring a value variable of type union symbol. Just like with structs, I can assign a numeric value and a character to letter and number, except Now letter will be stored in the same place as number. So letter has replaced number. This is useful when I want to have a variable that has changing types. This is an example of defining a union. The advantage, we want to make sure we all understand, of using unions rather than structure is that int and char can be interchangeable based on the last operations I am performing. So, for example, if I am defining a union that could have an int and a char as fields, only one of them would be used at a time. So in line 24, when I write value.number equals 25 and then value.letter equals m, m has replaced the 25. So now if I was to type the value, it will say m. Before we do that, let's look at another interesting way of interacting with union in line 27. I'm defining a pointer ptr to point to a union, and I'm storing in that pointer the address of value. I am now assigning the field ptr letter. Notice that I'm using the arrow notation because it's a pointer and no longer the dot notation as I used with the struct. But it's the same principle. I'm accessing the letter field, which is now m. I'm placing that into my letter. Let's confirm that through printing. And indeed, the letter field is m. Let's add another print statement. This time, it's going to be for the variable ptr and number. Notice how Eclipse automatically gives you the valid options to choose from. In this case, would be number. And let's see what this prints. Notice now that the letter field is 109. I printed that twice. We should also change that to number field. Still the same output. But notice that the number field is 109, which is the ASCII code of m. If I was to change that to C, they're both m. So even though I never explicitly change the value of number anywhere from the original 25, the meaning of a union is that the int and the char takes the same exact spot, which gives us tremendous flexibility. I could have the same exact location, sometimes storing an int and sometimes storing a number. We will see more applications to that in upcoming videos. A lot of the other handling is similar to structs, so there's no need to repeat that here, but there will be cases where we really want to be able to store multiple types of value at the same location, and this saves us a lot of space, and it's part of this whole notion of low-level management of memory that the C language enables. In this video, we'll discuss data management using sequential files. But first, let's start with defining what a file is. It is simply a named portion of storage area. In the same manner that you label a sequential set of memory locations and call it an array, you can do so and call them a file. A file is a slightly different structure than an array. It is a more complex type of data storage, and we should be accessing it in a different manner, as we will see shortly. Files are of two types. They are random access and sequential. A sequential file means that, for example, if you want to read the 20th character, you must first read all the first 19th to get to the 20th. You cannot jump directly. You have to open the file in one of several modes. You can open it for reading, for writing, for example. You can close the file so that it is no longer accessible to the program. You can read from the file until a desired location is reached, or you can read the entire file. And you can write to a file when arrived at the desired location. We are now going to see how this is done in practice. In this example, we are going to look at three functions. One, line 15, reads the entire file. The second one reads until a pre-designated marker. And the third one is going to show how we write to a sequential file. I commented out line 22 through 24 because I want to focus for now just on read the entire file. For this exercise, I created a text file and I placed it in the project folder. Let's open it first. The file contains, this is a message. I'm going to close the file right now and we'll see how we can read it with this function, read entire file. First of all, let's focus on line 31. Line 31, I'm defining a pointer to a data type file. We need this pointer because this is the way we will refer from now on to that file. In this particular instance, line 32 shows how we can open that file and establish a link between the pointer and that particular area in storage. For example, fopen, the full path to the file, and at the end, an R. This designates this file as being open for reading only. I now proceed, line 33, to read one character from the file. If you recall, we had the ability to read from the screen using the getChar command. The counterpart of that, when it comes to file, is the getC command. It's actually a function that requires a parameter, and that parameter is fp, the pointer to the file. A program could have multiple files opened, so we have to tell it to which one are we referring to. In this case, the int defined in line 30, ch, short for character, is the one that will hold the output returned by the function getC that reads from the file message. We shall now start a loop in line 34 while ch does not equal end of file. End of file, it's a predefined constant. It is actually -1. If you hover over it in Eclipse, it'll tell you it is actually a macro. But for readability, we call it end of file. We are first printing on the screen the first character which was read outside the loop. We read the next character and continue looping through the file until we reach the end of it. If the file was empty, nothing would have been printed because the loop would not have started. Then we close the file. It is a good practice to close the file to avoid any system hangup. Let's run this program and see what happens. Indeed, the file was read. This is a message as intended. Let's move on, and now I'm going to do both things. I'm also going to read until a marker. This is essentially the same function, except I'm passing it a value of a marker, which is, in this case, the letter M. The only change is line 46. Instead of reading until end of file, I'm reading until the first occurrence of the letter M, which is the value of marker. So let's run this. As you can see, everything was read until M. Finally, we no longer need those. Instead, I'm going to write to file. But let's see first, to which file am I writing? I'm actually creating a new file because if you look at line 55, I am writing to a file named message2. If you look at my project on the left-hand side, there is no file message2. When this program executes, if there isn't such a file, it is automatically being created. In addition to that, I'm going to use another type of command. If you recall, in line 57, we use printf to print on the screen. fprintf, it's short for file printf, which is formatted file printing. It works the same as the regular printf, except we have to provide it a pointer so it knows to which file to write. In this case, fp is pointing to the file message2, and you notice at the end of line 55, this time I'm opening the file with a W for writing. I'm going to run the program. Nothing happens on the screen. We don't see a file yet. So I'm going to right-click and refresh. And here's my message 2. And this is the message for Roger. Why does it say message for Roger? Because I printed this is the message, and then a name, which in line 56 is an array that contains Roger. In this video, we will take a look at the second type of files, namely random access. Random access files are different than sequential files because they only allow access to the data at the point at which it should be read or written. You can look at it as being able to go directly to a location, skip everything else, as long as you know how many units to skip. Typical operations with these files are open the file in one of several modes, just like sequential. You can open it for reading, for writing, or for both. You can obviously close the file. You can advance to a specific location and read from file. If we can make an analogy of sequential files to the old tape decks, those of you who remembers the tapes, in order to get to the third song on the tape, you had to fast forward all the song, the entire material, until the beginning of the third song. With dynamic, this is a little bit along those lines. You can instruct the reader, the pointer, to advance directly to that position. And this is because of how memory is being managed internally using pointers. We can go to a specific location and either read or write. In this file, we are going to look at two examples. One is a function called read and verify that will write some content to a file. And the second one is add text to location, where we will first write some content and then we will overwrite it with additional content. The first one, read and verify, is defined in a very similar manner to the one that we used in the example with sequential files, except we have a slightly different set of functions that are at our disposal in C. First, the fopen command is similar as it was with sequential file. We're simply opening a file. In line 34, we are calling a file in a similar manner, and the directive this time is W+, meaning we are opening this file to read and write. We are going to put a message into the file using the command fwrite for file write. The message in line 35, it's message to write, which is a string or an array of characters defined in line 28 that says this message will be written to a file. We are writing the message in the following manner. We are telling the fwrite function three things. One is what is the message, the other is what is the length of the message, and finally, to which file to write it, that's the FP. The length of the message is given to us by the function strlen, which is available because we included the string.age library. Finally, we are using a new command which is specifically for random access files. It's called fseek. Fseek essentially tells the pointer where to point in the file. In this case, we want the pointer to go to location 0. So we're telling fseek, take the file fp, seek set the reading head or the pointer head to location 0, which is the very beginning of the file. So we wrote a message to the file in line 35, we moved back to the beginning of the file, and now we're going to read into a text buffer, which is actually another array of characters, the message that was placed in the file for verification. Since we know which message was written, we can easily verify that the message is the same. And since we know that this message has been stored in line 28 in an array, All we need is to take the same length as we used in 35, line 35 that says string len message to write. We have to take the same length of characters, and this will be our verification. Let's run this code and see what happens. First of all, let's convince ourselves that the message file which we open is empty. Because it is empty, whatever will be written, we know it's a result of this code. I'm going to close the file and run our code. This message will be written to the file. This is the message that was printed by line 44. Because on line 42, fread read the message or the content of the file from the beginning of it, placed it into text buffer. We then took the content of text buffer and printed it on the screen. For further verification, let's open the file message and recall that it was empty a few seconds ago. Now we have the content in the file. So we created a mechanism to read and write data to a file using random access. I'm going to clear the console, and now we're ready to proceed to the next function. I'm going to now comment, read and verify, and I'm going to enable add text to location. Let's look at this function first. This function is going to write a message to the file using a slightly different method this time. We are opening the file in the same manner and using now the command fputs. It will going to print not much to say today to a file using the pointer fp. Then we will go to location 8. So if you look at here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, we'll skip 8 location. Again, we seek set, and we'll replace from that point and on the existing text with the text in line 55 to talk about. So the original text would be not much to say today. It will be replaced with not much to talk about. First, let's clear the file so there is no content from before. I'm going to save this one, and let's run the program and let's see what it does. So this time I'm not outputting anything on the screen, so there's nothing here, but I'm going to look into the file and it should say not much to say today, and then it would have been replaced by not much to talk about. So the final outcome is not much to talk about. And here it is. To wrap things up, we looked at dynamic files, we looked at sequential files, random access, which gives us a lot of flexibility. There is not one situation better than the other. There's not one tool better than the other. You now have several tools that allows you to write content to a file either sequentially or through random access. You can read it, you can use file to save data, and so on. In this video, we are going to summarize some of the things we discussed so far and bringing them together in a read-write combined application of a realistic situation. Whenever you want to open a file, you have to ask yourself, what is the main action you want to do with that file? If all you want is to read and want to prevent inadvertent overwriting of the material, use the directive R. If, on the other hand, you don't have a need to read anything, or you just want to create a new document that didn't exist prior to that, you can open a file for writing, and the fopen command with a W directive will create the file if it doesn't exist. Sometimes you would like to write a log. In this case, you want to make sure you're not overwriting existing content, and you are forcing it to be appended at the end of the file. A+ opens a file for reading and writing in append mode. So you can read, but the writing is only in the append. R+ open the files for both reading and writing for maximum flexibility. Let's look at an application in code where all of this will be used in the same place. In this example, we are going to create a copy of an existing file. We have a little text file here called source file that has 2 lines of content. As you can see, this is the first line of the file. The second line does not add much. Let's close it. Then I'm going to do two things. I created a function called copy from source to destination, and the second one, append copyright notice. I will keep only the copy from source to destination open so that we can verify the interim content of the file before we perform the second one. Let's take a look at the copy from source to destination. It's a very simple loop like the ones you've seen before. However, in this case, we are using the fopen command twice. One is to open the source file for reading in line 30. The other is to open the destination file for writing in line 31. Notice that the destination file does not exist. It will be automatically created. Once we open the file, we are starting a reading loop until the end of file in line 33. As we are reading a character, we are immediately copying that character onto the destination file in line 34 until we reach the end of the first file. When we are done, we are closing both files, 37 and 38. Notice that obviously for this to work, in line 29, we needed to declare two pointers to files. Let's run this and see what happens. The program terminated, and I didn't ask it to produce any output. We don't see any destination file here, so we will have to refresh. The destination file has appeared. Let's open the source, and let's open the destination, and as we can see, they are absolutely identical. I'm going to close both files again, go back to the code, and enable the append copyright notice and disable the copy from source to destination. We're going to run the code again, and this was done very quickly. Again, I didn't ask for any message to be printed. Let's look at the destination file, and now we see the copyright notice has been added. How did this happen? Is because we ran that function append copyright notice, which is simply opening the file in append mode and is adding two blank lines in line 45, followed by the copyright notice and closing the file. This concludes our discussion of files in which you learn how to read, how to write into random access mode, how to read and write sequential files. In the next few sections, we will talk about user-defined functions. We have used functions so far in many examples throughout this course. However, now it's a good time to reflect and think about some of the specifics involved in user-defined functions. Let's recap what is a function. It's simply a group of statements that perform a specific task. Now that you have some experience writing statements in C and planning and implementing shorter or longer programs, let's focus on what that task is. Before writing your code, have you clearly identified the purpose and scope? Do you know what this program is about to do? What is the intent? And what was the main criteria that led you to define certain functions? Each task is defined to implement a step towards providing a solution to a bigger problem. You cannot define a program that solves one problem in its entirety. You have to chop the problem into smaller components and tackle each one of those individually. Let's see in an example of a C program, what does it mean? This code is not producing any output. In fact, it's just a skeleton. It's a great way to explain the concept of dividing a task into smaller tasks. Just look at this line 16 through 23. Even without knowing what the problem is or what the purpose of this code is, you read data, validate data, process data, analyze results, generate report, write formatted report, archive data, disseminate results. Regardless of what the problem at hand is, it is always possible to break it down along these lines. This is not a recipe. It's not a concrete example. It's a generic approach to solving problem. If we scroll further down to function definition, we see how the skeleton is ready for us to simply pour in the content. If you think like this, you are more likely to come up with solutions that make sense, solutions that can be better maintained in terms of code readability, code usability, debugging, and so on. Over the next several video segments, we will discuss even more details about the entire approach to user-defined functions so that they are the best they can be in terms of efficiency, readability, reusability, and so on. Now that we discussed what functions are, we can proceed with our topic of functional programming. Functional programming is essentially writing a program that, well, consists of functions, which are tasks and subtasks. So let's refine the thought. A top-down design approach breaks down a program into smaller functions, meaning you first take the big problem at hand, you break it into smaller problems, and you tackle each one of them individually. This way, a big project becomes much more manageable. This is true not just for computer programming or computer science, but especially true for computer programming. Smaller pieces of code, smaller functions, partial code, loops, and other constructs are easier to decode and debug if they can be isolated and tested. The code becomes easier to maintain, easier to make changes, not just by you, but other members of your team. Let's continue with our previous example and refine this a little bit further. As you can see, when we look at a code, we should see a clear description of every section. For example, we have global variables in which I define some dummy array that doesn't do anything. It's just an example that this is where I would define a global variable. Then we have our function prototypes. Then the same main where all the functions that represent steps toward the solutions are being called. And I give an example here. This function is working, except I did not include a data file with it. I just show an example in Live 48, which you saw in other videos, how we can read data from a file. And this is an example of what a read data function should do. It's simply a loop that gets the data and sets it up into a variable for later processing. So in a second refinement step, after we set up the skeleton, we can now write for every function a little bit of a text. What do we think this function should do? So example, if you want to validate the data, you could check things like, are the numbers within a plausible range? So you look at the data that your code generates and you ask yourself, is this plausible? Does it make sense? Is this the same data that someone that was a professional in the field or a professional in your company or a manager or anybody that's experienced in the field we think, yes, this is consistent with finding over a period of time. You can also check your structural integrity of your code. For example, have you missed any array elements? You could run some print functions that will give you the content of arrays, of variable, of struct fields, and so on. Are there any variables that haven't been initialized, and so on? We'll proceed then with process data, in which you would identify formulas, formats, and standards that are compatible with the problem you're trying to address. Analyze results. What type of graph, tables, or lists do you need? Whatever else that's customary to your organization was required by your program to produce. When you look at the data and analyze the results, especially through a statistical analysis lens, is there anything that stands out as being out of the ordinary? Out of the ordinary could be, yes, that's great, we have low sales, now I find some evidence of great sales, but it could also indicate some errors. Finally, you might have to generate a report. You should know what type of reports are expected from you. Anything that is compliance related. Formatting, archiving. Does your program store data in more than one location so you can refer to it later? Maybe due to regulatory issues, or maybe just because you need to have a backup. How about sharing your results with others? Does your program include a mechanism for storing data onto a shared folder, onto a network? Is it secure? Every project has its own requirements and issues. And this is just an example. It doesn't mean that every program you would write will have validate and test and generate reports and analysis, but this is a good example of how it might look like if it should. Still under the topic of function, let's examine a little bit in further detail the components of a function. First of all, there's a declaration of a function where you define the header, the name, and so on. Then you think of, does the function return a type? Maybe it doesn't. If it does, what type of value should it return? What is the most appropriate name for this function? Should we just call it function, function1, or shall we call it average of two numbers? Parameters. Does the function require any external input? Does it require parameters that are numbers, that are text? You have to be aligned with what exactly is expected from the problem that this function is trying to solve. Finally, the body of the function, the statements that make up the function. Obviously, the function has to do something. So before you write the function, just ask yourself, do you have an idea of how you're going to go about this function? I have said that many times throughout this course. Think and plan and never rush into just writing code. A simple function is a great way to examine some of the things in detail because even in simpler functions, sometimes there are things that are worth noticing and sometimes they can get lost. For example, this function is meant to compare two numbers and return the smallest of the two. Obviously, because of that, it requires external data to be passed as arguments to its two int parameters x and y. At the heart of the function, the main idea was we are going to compare those two values and we will find whichever is the smallest, and this will be the return value. So this function receives two inputs and returns one, which is one of those two inputs. It makes a selection. Therefore, after we decided that the core of the function is this, things like the second line of the function int minval, this is just a side effect of us deciding that the function would first compare those two numbers. So this is the heart of the function. That's the main idea. How are we going to about implementing it? That's tactics. Sometimes you need one or two or three variables. They call helper variables or temporary variables, and so on. This is not necessarily supposed to be the best, most efficient, the most awesomest function for comparing two numbers. But it works, as we'll see shortly in a C program. So here's the function, just like as we saw, and we are now going to compare two values, int x and y. Now, notice that the values that I'm passing to the function are not numbers. They are two characters. Let's run the code and let's see if there's a problem, and then we'll focus on some of the issues. But I want to run the code first so we'll have something at hand to talk about. Okay, we see n equals 97. What could possibly 97 come from? The function was called in line 18, smallest, r, and a. So naturally, one would expect to receive an answer. Which one is smaller, the letter r or the letter a? What does it mean? If you examine the function, there is nothing here to suggest that the function is capable of comparing two letters, unless you know that the function might be able to translate a character into its ASCII code, because after all, the language C can do stuff like that. So let's examine this a little further. These are some of the questions we have to ask ourselves before we implement the function, so that we don't come up across a situation where we are puzzled. We see that line 18, we're calling the function with two characters, yet the function returns a number. I have no idea what to do with this result. So let's look at line 26, where I put the comments deliberately here and not outside this document, because it's very important when you think about a function, when you think about coding, to have those tips and questions in front of you. Is the return type the same as the function data type? For example, if the function returns minval, which is int, has it been set so that the data type is also an int? In this case, yes. Is the function name appropriate for what it does? Smallest. I'm not sure yet what the function does, but that's one of the questions we have to ask. Are the parameters correctly typed? Does this function work on integers? Is it supposed to work on integers? Is the input that this function is supposed to process integer? Line 29, is the number of parameters in agreement with what the function input is supposed to be? Was I supposed to design a function that receives 2 external values, maybe 3, maybe 5, maybe an arbitrary number? Is the function working properly on all inputs? Does it work with negative numbers? Does it work with identical number? What if the input is not an int? Is typecasting an option? Typecasting means we are changing the type of a variable for a specific operation so that the operation can be carried on between compatible types. If you can run the function with 2 float arguments, what does this mean? You can run the function with 2 character arguments. What does that mean? Obviously, if I'm going to change the function, instead of R and A, I'm going to choose 5 and 12, and I'm going to save and run the function. The smallest between 5 and 12 is 5, so I know that the function works correctly on integer numbers. What about floating point numbers? Will it still work? Let's see. It still works. However, the result is an integer. What if I had something like this? And 11.99. Would the function still work in this case? I still get the result 5. What if it was 11.98 against 11.99? Will the function still work? The answer is 11, inconclusive. So this is an example of a thorough testing you have to perform even when we are discussing a very small, very seemingly deceivingly simple function. Imagine the length of testing you will have to go through for much complex programs. Another aspect of user-defined functions is the scope of a variable. We will specifically distinguish between local and global variables. What is the scope? The scope is the area in which a variable is known to the code. In other words, global variables are recognized throughout the entire code, the entire program. So they span an area that's identical with every single function and every single piece of code in that program. That's why they're called global. Local variables are recognized only within the containing function. You could declare 2 variables by the same name in 2 different functions, and although they have the same name, they would be 2 different variables. They will only be recognized by their respective owning functions. Finally, if a local variable has the same name as the global one, the local variable supersedes the global one. So the closer you are to the use of the variable, the more precedence it takes in terms of conflict resolution if the names are identical. Let's take a look at the code and see how those things would affect how we code. In this exercise, we are going to look at several global variables which may or may not have been assigned a value in the main or inside one or more functions. We are going to track the changes in the values of those variables to further explore the issue of scope and make sure that we all understand the implication of naming, changing values in a function, outside a function. Let's examine first the 2 functions we have in this code. They're very simple. One changes a number, the other one is changing it differently. The first function, change number, has one parameter, a. Inside the function, a is being assigned the value 5. The second function, change number differently, it's also an int a. However, it sets values to other variables, b and c. Where are those b and c coming from since they are not defined in the function? Notice that a is the parameter, B is coming from here. So in fact, A, B, and C are all global variables. So in function change number, we have a variable A, and the question is A the same as the parameter of the function, or it is the same as the global variable A? In this case, we follow the rule that the closer to where the variable is being used supersedes the other definition. So in this case, int A is an internal variable known to that function. Therefore, in line 37, A refers to the parameter A. B has not been defined in this function. Therefore, there's no conflict. Therefore, B is the global variable. So is C. However, that's only at first look. Notice the int C, which means there's a new declaration of C, which means that this particular C is not the same as the global variable C. So we have an A that's not the same as the global A because it is a parameter. We have a C that's not the same as the global C because it's defined inside the function, and only B is the one that's left. So I'm going to run this program and then follow line by line in the code and see what happened. First of all, in main, we have A equals 0 because it has been initialized a declaration. Then we call change number A. Change number A, assign the value 5 to A. So inside change number, A now becomes 5. And we are printing the value again as soon as change number finished. So obviously, since A equals 5, it's an internal statement of the function, and A is the parameter known only to the function. Even though they call A, it's not the same A. So outside the function, that A is still 0. Now we're going to call the function change number differently with the same A, which is 0. So in main, it is 0. And now inside the function, we are assigning A to be -1, B to be equal 3, C to be equals -1. We run in the function. Let's see what happened. A is still 0 because it hasn't been changed by a function. The only thing those functions did is they made a change internally to their own parameter. B is now equal 3 because it is a true global variable unaffected by anything else. And C has also been unaffected outside because the variable C inside change number, it's a local variable. So we had multiple instances, variables with the same name, not being changed and being very confusing. The main lesson from here is to, first of all, name your variable in a very meaningful manner so that you avoid any kind of confusion by looking at an output, seeing variables with same name with multiple values. And second, be very careful what you define and where and what values you assign. Continuing our discussion of functions is the topic of passing variables. Parameters of a function are essentially the same as local variables, but are assigned values outside the function, and their value is carried inside the function. There are two ways to pass variables to a function. One, it's called by value. Argument values are copied onto the function parameters. So the variables themselves do not participate into any computation or any statement outside the functions. They are just receivers of values from the outside. By reference, the argument addresses are copied into the function parameters. So the distinction here is that we are not passing a value, but we are passing the address of where that value is being stored. That's a very, very important distinction because now the function is capable of modifying an address. So there is no longer a distinction between local or global. It is the physical location. Let's see how this works in code. I wrote two functions. First of all, let's look at their declaration. Notice line 15, void sum function receives two integers, a's and b's. On line 16, the function some other function also receives two parameters, but they are pointers, meaning they are linked to a specific address that stores an int. What I will do now is I will initialize x and y to 0. I'm going to call the function that receives the parameters by value. I will check the values of x and y before and after the call of the function, and then I will repeat those steps by reference. This way we'll be able to see what is the difference between passing a variable to a function by value or by reference. I'm going to run the code and we will look at the output line by line to see where it's coming from. First, notice in line 25, x equals 0, y equals 0, and indeed, before the function call, there are 0. Now we are calling some function. Inside the function, the variables have been renamed a and b. It's not that the x and y have changed, but a and b are the parameters of the function. The function internally knows them as a's and b's, so the values of 0 have been copied onto a and b. That's why on line 50, we're printing a 0 and b 0. Inside the function, we are now modifying a's and b to be 111 and 222 respectively. Hence, the note modified inside the function, here are the values. The function now ends, and the execution returns to the line after the function call. And after the function call, x and y are still 0. Because we passed values onto the function, those values were used inside the function for whatever calculation the function needed, but they had absolutely no effect on the x and y outside the function. Let's see what happens when we do this by reference. When the argument that's transferred to the function, it's actually the address of a variable and not the value. Before the function call, they're both 0, and inside the function, something different will happen. First of all, I'm calling this function with the address of x and y because this is the way we treat two parameters that are defined, if you recall, as pointers. And if you're not, you can simply hover and they will tell you. Eclipse is very good at giving you information about your code. You can hover over a function and see its entire definition without needing to scroll up and down. So inside that function, we have two pointers a and b that are being assigned the value 111 and 222, which means those pointers now have a link to the address where those numbers are being stored. Therefore, as you can see, in the function, a was modified and x and y were modified because those pointers that happen to be parameters of a function, they point to the same exact address as the variable x and y. We refer to them by different labels, but they are the same exact address. This is why the address has been modified inside the function and the change is persistent. So whatever label we choose for that address, it is still the same address outside the function and inside the function. Let's discuss in this segment passing an array to a function. An array is not a regular variable, obviously. It's a sequence of data that's being stored in one sequential location. So let's see what is different about passing an array from passing a regular variable. First of all, passing an array, it's not really passing a variable, but a pointer. When we have an array, we cannot send the entire data set. We are doing it in a more efficient way. We are sending it the beginning location of the data set, and the compiler will handle the rest. Here's an interesting observation. Function parameters are synonymous to pointers. We will see that shortly in code, but first let's take a look here. Let's say we have two functions, func1 and func2. Notice the difference in the way they define their one parameter. The first one has an array of int. The second one, func2, it's a pointer to an int. Apparently, those are very different things. Line 3. Let's initialize an array list with 5 elements with the numbers 1, 2, 3, 4, and 5. we are now going to pass the same array list to both functions and see if there's a difference. Notice that I am not passing the numbers. I am not passing list 5 or list brackets. I am just passing list. All I need to tell the function is the name that represents a label of that set of elements that we call an array. That's exactly the same thing we're doing in code. I just have different numbers. So here I initialize an array list 5 with the numbers 5, 7, 9, 23, and 15. I'm passing it to the two functions that were defined. And just as a test, I am printing in line 28 and line 32 the third element of the array. And I'm curious what happened when those functions receive the array in different ways and they try to print the same element. What does it look like? Is it the same or is there a difference? Let's run this code and we'll see. First of all, there is no difference. So position 3 in the array, which is element 4, because this is 0, 1, 2, and 3, it's 23. So first of all, the answer is correct. So the question is, how come those two functions whose parameters were defined differently, one was an array of int, the other's a pointer to an int, did exactly the same thing? Even the printf statement is the same. There's absolutely no difference in what the functions do other than the definition of their parameter. The only explanation is that int array in line 27 and int pointer are the same and exact thing. And this confirms our earlier statement that parameters of functions are nothing but pointers. Now that we discuss how data gets passed onto a function, let's look at how values or results are being returned from it. We have several options. Option number 1 is very explicitly, we tell the function to return a value, even if that function does not receive any arguments from the outside. In fact, this function doesn't even have parameters to receive anything. So it simply returns a value. Very simple. Option number 2 is modifying the value of a global variable. For example, we would have a temperature variable defined in the global section. That variable is then modified inside the function. And since there are no other local variables with the same name, it is fair to assume that this is the same variable temperature that lives outside the function. Finally, the third option is passing arguments by reference. We have, for example, in this case, two integers a and b that are going to be mapped onto two pointers that represent the function parameters. Those pointers then modify I and j. They modify the address in which those two outside numbers exist. And by calling func with the ampersand a and b, we are passing that address. So we're not really modifying a variable, but we're modifying the address. Remember that the variable is just a label of an address. The pointer gives us the mechanism in the language C to access that address. Let's see how this actually works. So here's our global variable, temperature. And here are three functions. A func named func that simply returns a value, 12. The second one, it's a function measure that modifies a global variable. And the third is the function that receives two values passed by reference. Please recall that our topic of discussion is functions that return values, which means passing parameters by reference are not part of this discussion. We're only talking about functions that are doing something that affects a variable outside their scope. So let's look into main and see what this program does. Actually, it's even better if we run it so we can follow step by step. So first, I am declaring a variable n, which receives the return value from a function. If you look at the function definition, This is simply an int value inside the function that's being returned. So the function communicates to the outside world explicitly the value of an internal variable. So it's not surprising that after the call to func, n equals 12. Next, measure is, as we saw, affecting a global variable. If you look at the definition of measure, indeed, it doesn't declare anything internally, and we already know that temperature has been declared as a global variable, so there is no surprise that temperature is now 50.2, as is the value set to it inside a function. Finally, line 30, I'm declaring two variables a and b, which, as you can see, are deliberately not initialized. I am now calling the func_by_ref function with the addresses of those variables. That's very important. I'm not sending to the function a and b, but the variables that represent the address of a and b. Let's hover over the func and see what it does. There are two pointers, which also happen to be the two parameters of the functions. They are the ones that are being modified. So the function has received two addresses, a and b. Inside the functions, those addresses are being pointed at by two pointers, I and j. So when I becomes 5 and j becomes 7, this means that the address that this pointer I and j is pointing to has received the values 5 and 7 respectively. Since this address is the same as the address labeled outside the function as a and b, it follows that a and b have now been modified outside the function. You can use this approach to create a function that initializes data. In fact, this is what this function did. We can create a set of variables that are not initialized anywhere and then call a function by reference. That function can be either stored in an external library that's being loaded, and in a very safe way, we are very explicitly initialize every single variable that require initialization in our code. We have been using, in most of our examples, prototypes of a function. So now it's a good time to pause and discuss this for a few more minutes. So what is a prototype? As a reminder, it allows for a function to be used before it is defined, especially when we have multiple functions and we don't know exactly in advance which one may be needed before another. So in order to avoid any problems with errors, we are simply declaring before the main a prototype. A prototype literally means I am advance declaring the function, but here's a little bit of a difference. The function itself, if you look at the bottom, it says double func, double x, and double y. The prototype doesn't have to include the variable names, just their types. In a way, you can refer to it as a template. So we are now creating a template of a function that returns a double and requires two double arguments. In main, we are going to declare yet another double result, which will capture whatever that function is supposed to do once it receives those two values, 10 and 20, and it returns, in this case, the product. Notice it's a minutia here that even though the function requires two doubles, in this example, we are sending two integers, we already know that C is not very picky when it comes to this. As a reminder, as I said in other videos, C assumes you know what you're doing. It will not always alert you. This is why we will see shortly in another portion of this course, how do we ensure that we don't make such inadvertent mistakes. For now, let's go to the code. And here's our function, the prototype, double func, double double. And the request for a result from two variables, x and y, that are being multiplied inside the function. So let's see what happens. All we have left to do is click run, and the result is 200 because 10 times 20 is 200. And what the function did, it took those 10 and 20, converted them to double, multiplied them, send the result back as double. So it is now 200.00000. The key point in here that I wanted to show is the fact that you declare a prototype of the function as a template that doesn't require anything except the type of the data that the function returns and the type of parameters, if any. We're going to wrap up the discussion of functions with the topic of recursion. We have seen the topic before, and now it's a good time to revisit it. We call a recursive process those processes in which a function calls itself. We are going to stay true to tradition in programming and computer science classes, and we are going to look at the Fibonacci series as an example of a recursive computation. The Fibonacci series, it's a great example because it is powerful, it is simple, and it has a lot of information that we need to talk about. So the Fibonacci series, in a nutshell, is a series such that one element in the series equals to the sum of the preceding two. That's it. The only way that are different are the first two, because the first and the second don't have two preceding ones. So we need to treat them specially. So the Fibonacci series receives an index, n, and based on that index, computes the series. If n is 0, which is the first element in the series, the function will return 0 because there's nothing else to compute. So by definition, we define that the 0th element in a Fibonacci series is 0, and the first element, so number 1, is 1. Other than that, we can now use the formula that's listed in the return statement. We are going to return the sum of the previous two. So in this case would be 1 and 0. If you look at the recursive process, it occurs when you see the name of the function being referred to inside the function definition. So what happens here is that when I say return Fibonacci n minus 1, the function doesn't even go to the Fibonacci n minus 2. It goes back to the top, and instead of n, it now uses n minus 1. So obviously n is coming from somewhere else. If you look further down under main, the command printf, it prints the result of computing the Fibonacci, in this case for number 10. So if 10 is being passed on to the Fibonacci header function, then it is not 0, it is not 1. Therefore, Fibonacci n minus 1, which is 9, it's now being sent to the function. 9, it's not 0, and it's not 1, and it becomes 8, and it becomes 7, it becomes 6, 5, 4, 3, 2. Now it becomes 1. If it's 1, the function quits, and now it goes to the other Fibonacci n minus 2. So we have this sort of a yo-yo movement where we start with Fibonacci n minus 1, and there's a loop that happens between those Fibonacci n minus 1 and the header of the function. When that loop can no longer work, it switches for one cycle to Fibonacci n minus 2, but then immediately switches back to Fibonacci header and Fibonacci n minus 1. So that back and forth until everything is exhausted. Let's take a look at the code and see how this works. Notice, first of all, that there is no main yet. It is all the way at the bottom. I just did that to show you that it really doesn't matter where you put main. It's more of a convention, habit, whichever you want to call it. It is a function. Main is just a function like any other function. The only thing that's special about it is when the compiler creates executable code, it is expected for one function to exist that is called main. And this is the function where execution starts. Other than that, it can be anywhere. Now, what we did with that, notice there's no prototypes here because the two functions, Fibonacci and the one that calls the series, are being defined in the order that they're being used. So there is no problem of us needing to use a function before it has been defined. Let's go to main and see how it all starts. So I have a function called generate Fibonacci, which I would like to use to generate the first 25 numbers in the Fibonacci series. Line 32 is the header of that function, so I'm receiving the 25, and now I am starting a loop. So numbers, which is the parameter of the function, is now 25 because it was passed on from line 48. We start the loop from 0 to 24, and inside that loop, I have another counter. If you notice, the n starts at 0 outside the loop, and at every cycle of the for loop, I am increasing n by 1. So n now equals 0. I'm running Fibonacci with 0, but I'm doing this 24 times. So for each n, I'm running the Fibonacci loop 24 times. And whenever I say in line 30 that I'm calling Fibonacci, I'm actually going to a recursive function Fibonacci. So I have a loop. Inside that loop, I have a call to a recursive function. So that recursion is in itself a loop. We haven't mentioned that the first time we discussed recursion because at that point, we haven't learned about loops yet. But now it's a good time to see that all recursion is, it's a loop without saying it is. So this function computes the Fibonacci series. And there's another interesting line there that I commented out, which is line 22. If you want to follow everything that this function does, I encourage you to print those values. So uncomment line 22. Let's run and see what the Fibonacci sequence looks like. And just to make the output a little bit more readable, I put the brackets and I formatted it. So here are the first 25 numbers from 0 to 24. So we start at 0, 24. It goes from 0, and the 24th cycle, which is actually number 25 in Fibonacci, is 46,368. If I was to uncomment that line and run this program, as you can see, now you can follow all the evolution inside each cycle. So each time you see a number in brackets, this is the next Fibonacci. This is the recursion at work. So all of this happens until there's some number in brackets. In this video, we will discuss the definition and usage of macros, which are an interesting feature that allows our programming to become easier and gives us a few powerful tools, as we can see. There are two types of macros. First, let's define formally what a macro is. Very simple definition. It's a code fragment that has a label or a name. We distinguish between two main types of macros. One is the one that looks like an object. For example, numbers, defined as 1, 2, 3. So it's a sequence of numbers, which then can be used to assign values when we initialize an array. So it is an encapsulated object that has 3 integers, which are now being used to initialize an array. That's an object macro. Another type of macro is one that looks like a function. So notice the first line where it says define max xy, meaning a function that finds the higher of x and y, or the larger of x and y, depends on your frame of reference. If you look at that line, this is essentially an if-else notation in a shortcut. Other languages also introduced this notation, but it was originated in C. What this line says is, compare x and y. If x is bigger than y, that's the question mark, then x, else y. So if x is bigger than y, return x. Otherwise, return y. And we define that as max xy. We can then use it in multiple ways in which we need to compare two values. For example, max of p and q. Just like with a function, I am using p and q as arguments. They're being mapped onto x and y. And I am now comparing p and q. The value from max pq's comparison is being returned in a variable lowercase x, which is not to be confused with uppercase x in the definition. The second, we are comparing two values, 12, and 5. Those two values now are being mapped onto x and y, and the macro compares 12 versus 5, so obviously the result will be 12. Finally, we are comparing n plus 5, presumably n has been assigned the values prior to that, against a pointer p that also points to an address that contains an integer. So presumably, p has been initialized somewhere, and now we have two values that are integers to compare. Notice that the macro doesn't care about the type of those items. Let's go to the code and see how this works. The same exact macros are being defined. The object, numbers 1 to 3. The list is not really that interesting, so we are not going to talk about it. It's simply an array of 3 numbers. What is interesting is the other macro. So let's see what we did for it. First, we need to prepare all the variables that we are going to use. Line 23, we defined 2 pointers, p and q, and a value n, then 2 ints, val1, which is 5, val2, which is 12. And then we have assigned to those 2 pointers, p and q, the address of val1 and val2. So now those 2 pointers point to 5 and 12, respectively. We also initialize the integer n to 1. So let's start our first comparison, just like in the previous screen. We are going to compare p and q, which are pointers. Comparing 2 pointers, let's see when we run, what does this mean in terms of results. So as you can see, the pointers p and q are actually addresses in memory. So we are comparing 2 addresses, not what is being stored at that address. So if you look at the hex values, the one that the macro chose to be the larger is 529, C6, C60, since if you look at what is the end of those numbers, they're both identical except the last 2 digits, 60 and 5C. 60, it's not actually 60, it's 60 in hex. So in that notation, 60 is still bigger than 5C, and therefore. So regardless of what the content that this pointer point to, this address, so the label of the address itself, which is also a number, is being compared. The second one, y, it's obvious. 12 is bigger than 5, so the result is 12. And z is 6. Now, where did the 6 come from? Notice in line 27 that n is 1. Therefore, in line 31, n plus 5 is 6. So this is one value that we're comparing. The other one is the pointer p. If you look at line 24, value 1 is 5. Line 25, p points to the address of value 1, which means p points to 5. Therefore, p with a star is 5. P without a star, if you look at the output, the 2 line above, it's 529, C6, C60. So the last comparison compares the number 6 with the number 5. The number 6 is bigger, therefore z equals 6. In these videos, we will discover, again, a few more things about headers, even though we mentioned headers already before and we used it more than one time. We are going to take a little bit deeper look into what headers are and what are some of the uses they can have in practical terms. So first of all, we know that enable the use of functions defined in external files. For example, include mylibrary.h. Mylibrary.h, the .h file, is one of a pair of files that makes an external header. The files themselves are actually implemented in a C file, mylibrary.c. The headers include the prototype of the functions and any constant that would require define, for example. I created 3 headers for us to include that not only show that you can include a file, but the name also hints on something useful that those files contain. If you look at lines 13, 14, and 15, we see my library, my constants, and my macros. The number 1502 simply means that this file is associated with video 15_02. There's nothing special about it. Let's take a look at what these headers are, and then we'll see how they are utilized. My constant is simply a list of define statements. I'm defining something called max room, max price, true, false, epsilon. Those are randomly selected values. They don't mean to implement anything in the code. I'm just showing some conceptual reasons why you would want to have a list of constants in a program. The second one, my library, actually has two files. One, it's my library.h and my library.c. The .c library implements two mathematical functions. One in line 9, the area of a trapezoid, which is the sum of the two bases times the height divided by 2. And on line 13, the volume of a sphere, given the radius, 4/3 times pi times r square. Notice the notation in line 14. m underscore pi is predefined in the library math.h, which is included in line 7. The function pow, short for power, is also part of math.h, and it has two arguments, r and 2, which mean r to the power of 2. My library.h simply has the prototypes of those functions, and you recall by now that all we need for a prototype is the number of parameters and their type. Everything happens to be double here. Area trapezoid has 3 double parameters that it needs: the first base, the second base, and the height, and the sphere just needs the radius. Let's look at our main code, and nothing really happens here except we are calling volume sphere, which happens to be in one of the libraries, and then we have another call to numbers. It's right here, my macros. My macros has numbers defined as a sequence of numbers, and max, the same one as we saw before. Note here, I deliberately inserted another comma to show you that it really doesn't matter. There are tiny inadvertent things that C will let you get away with. C, in many instances, assumes you know what you're doing. Let's run this and see what happens. Volume of sphere with radius 5 is 4/3 times pi times 25. It's apparently 104 and change. And the fourth element in list is 7. We can confirm that easily. We have to look at the macro. That's 0, 1, 2, 3. So the fourth element, which is at position 3, is the number 7. We can confirm that in the code that we referred to list 3, which is the fourth element. In this video, we are continuing our discussion of preprocessors commands or directive, namely with the conditional directives. Let's see what they are. We saw already that we can define macro as a preprocessor command. In this particular case, it's a macro that also includes an if statement, which basically says the macro is defined. So if there is such a definition for some random macro called macro, then we are displaying some text. Another example of a conditional directive is if followed by an expression. So if something equals something or something is bigger than something, then we also display some text. And if. Let's look at 2 more directives. This is a 2-part directive, which is encapsulated in an if, else, and if structure. If expression, then we print the text if that expression is true. Else, meaning that expression is false, we are displaying another text. And that's it. Everything that starts with a pound sign is a preprocessor directive. It goes for includes, undefined, and so on. Let's switch to the code and see some of those things in action. So in this example, we'll start with something a little bit different than before. Undef max price. Let's look at headers. In headers, on line 12, I have defined a max price to be equal 45. This header file might be included in multiple files, and somebody thought that this is of useful enough value that it should be defined in a header. However, that could be one instance in which that max price is not applicable. Therefore, line 15 says undef, undefined max price, and now that it no longer has a value, you can define it again as 100. And it is only valid in this file. It doesn't affect the myheaders.h file. A second conditional directive is in line 18. The word in line 18 is shortcut for if not define threshold. If we do not have a macro or a constant labeled threshold, then we define it as threshold with value 23.751. Let's take a quick peek at my headers. There is no threshold defined, so this if holds. Therefore, now we do have a threshold, 23.751. Finally, another interesting definition of a macro is line 22. I'm defining a function, which we call greet, which receives one parameter, name. Printf, thank you for shopping here, and then the value of that parameter. So what this greet does, it greets, so it produces a message that says thank you for shopping here, and then the parameter. Let's put this to test. First, we're going to run it, and it says that max price is 100 because we undefined whatever was there. Threshold is 23.751. because we're printing this as a float. And then the greet says, thank you for shopping here. Now, where did Isaac come from? It came from calling greet with the word Isaac. Notice that even though this is string, it does not require double quotes. And this is special to macros. It just takes it the way it is. Then we have an interesting set of outputs, file, date, time, line, and ANSI. If you look at those lines, 33 through 37, those are predefined macros in C. So the file knows its own name. That's line 33, which is printed, file, and the full path to it. Second, the date, May 9, 2014, which is the date that this movie was recorded. Then the time, 20:46:51. This is the time at which it was recorded. That particular line, printf at line 36, can display its own line. So wherever you put that printf with the predefined macro line, it will tell you which line it is. And then finally, ANSI, that's the body of standards that govern, among other things, the definition of the C language, tells you that the value of its current standard is 1. And that pretty much wraps us our high-level overview of macros, includes preprocessor directives, and all related topics. We are going to start a series of videos that discuss the topic of good programming practices. The first one is about defining and using meaningful naming conventions. And let's see what we mean by that. Naming conventions refer to names, labels you choose for functions and variable in your code. There could be good and bad notations. However, this is subjective. It is very hard to say that something or some notation convention is universally good or universally bad. Most likely, it is an evolution based on different criteria, personal preferences, regulations, style of management, requirements for documentation, experience of the programmers, and so on. All we can do at this point is to give you some tools that will help you assess on your own whether a particular naming convention that you chose, if it's a convention at all, is appropriate or did it require some improvement. First of all, does it make sense to you? When you look at a variable name X or height or max price, does that name resonate with you? Do you feel like when you look at the code, yeah, it's obvious that somebody would use this name for a variable? When you show this code to someone else, does it make sense to them? Will they look at it and be completely clueless about what the program does in spite of the fact that they are very experienced programmers? Does it help making the code more readable? If you had to debate between labeling something X or labeling something X1 or A or a very long name, when you made that decision, did you ask yourself whether this decision makes the code more readable? Ultimately, the code is not just about running well, saving time, being resourceful. If the code is not very readable, it may be difficult for somebody to improve it, which means longer revision cycles, and the company might actually lose money because it cannot improve its own code for lack of readability. Whatever you think you are saving because you made your code more efficient, you may lose in the long term because nobody can improve it. Finally, if you look at your naming conventions, is there any aspect of your naming choices that made the code better in any way, whether it's readability, maintenance, makes sense to you, makes sense to other, whatever is there that you can point to? Let's see what this means in the code. And this is not entirely running code, but it's mostly an illustration because it helps seeing these things in the context of a program rather than outside in a PowerPoint. I listed here a comparison between what I personally considered good and bad choices. You might have another opinion. The most important thing that you are able to critically think, evaluate your requirements and criteria, and make the best decision out of all the options that are available to you. Let's look at line 17. Room numbers is the name for an array. It's very descriptive as opposed to RM, which would be short for rooms after the fact if somebody explained to me. So in this case, I choose room numbers. Line 18, first num in series versus first num in series. I know it says first num in series in both places, but did you when you first looked at it? The main difference, obviously, is the camelback notation on the good column, which definitely makes those words stand out. Line 19, I have a double, twice the risk. It's unrelated to anything. And on the right, double, doubler. So I try to show a common core in terms of the meaning. One starts with the word twice, the other with the one double. And I made this confusing to illustrate that you really don't want to name a variable the same word almost that you use for a type. So double, doubler, great opportunity for confusion. Line 20 through 22, there are conventions for writing about miles per gallon. Typically, if you would go to a car dealership and they will show you the Carfax or any other sticker information, you will see the notation MPG, lowercase or uppercase. Rarely you would see one word called miles per gallon, even though it makes more sense with the camelback notation and so on. So I really do not have an alternative to the MPG on the bad side, but I do have a bad alternative to miles per gallon. Obviously, it's the one without the camel notation. Finally, line 24, 5, and 6. I initialize three variables, x, y, and z to 0 versus putting them all in one line. It's really hard to say whether one is better than the other. It's a matter of style. That's why I said, even though I think it's a bad habit, it is often acceptable. If we continue to look at some rules that I put here, again, nothing runs. It's not meant to run in this code, but I wanted to put those recommendations in the context of code. So rule of thumb, Ask yourself whether the name of a variable, a function, a macro makes sense to you. When you look at your code, try to extrapolate and port yourself into the future and maybe a week from now and say, are you going to remember next week or next month or in a year what you meant when you said x equals 12? If your project needs to be transferred to somewhere else so you can get a promotion, will they be able to understand your code, or perhaps you will stay stuck in your low-level position because you are the prisoner of your code? There are multiple reasons why you want your code not only to be fast, elegant, well-documented, good naming convention, good structure. You never know when somebody will come to you and say, you did such a great job, I want you to now become the manager of their team. And you don't want to tell them, look, I would love to, but frankly, if I leave, nobody else will be able to deal with this code. Or the manager might tell you this, I would really love to promote you, but unfortunately, your code, it's such a genius. Only you can handle it. So word of caution, and be careful and trust your senses, trust your common sense, and in time, those things would become second nature to you. Code correctness is often an overlooked item, and now that you have some experience writing code, it's a very good time to talk about it. So let's see first what we mean by that. There are several measures that you can take to ensure that your code is written correctly, namely that it does exactly what it's supposed to do. First of all, you should look at your initialization. When you declare a variable, is it obvious that the value that that variable has by default is the one that you need? Or is there any danger that an initialization may cause a variable to have an unknown value? This applies to arrays, variables, and constants. Another type of measures are qualitative. For example, has the problem been appropriately defined? Are you sure that are you addressing the right problem? Planning. Did you take time to think about your solution, to come up with the right idea for implementation? Do you have all the resources? Do you have enough knowledge of the programming language or of the algorithm or of the problem space that will allow you to even start thinking about the problem, let alone planning a solution? Pre-coding. Never just start coding. The more you plan, the more you think, the more you run ideas in your head, the better your code will be. It is very hard psychologically, once you start writing the code, to stop and go back to paper, because you have that illusion that you already invested so much in it and it's a shame to let go. Do not let yourself to get to that point. Plan well before. And even if you feel at some point that you prematurely started to code, it's perfectly fine to drop everything, go back to the drawing board and start over. Second is your style or programming. Are you documenting? Are you using variable names correctly? Are you indenting your code so it's easy to read, and so on? The other one is verification. You can place measures in place in your code that will give you a lot of feedback, and we'll see that shortly. This program example in part shows a few things when we run it, and the others are again in the same category of tips, advice. Let's look at the quantitative measures. The quantitative measures are simple at the level we are discussing here and refers to primarily to initialization. Let's look at lines 18 through 21, where I am declaring 4 variables: an int array numbers, length 100, an array of char, also length 100, float distance and log distance, and none of them is initialized. As a test, let's print the values, for example, on line 26, numbers 28, word 28, distance and log distance. Let's see what does C decide to place as a value into a variable if the programmer has not explicitly assigned a value. The best way to do that is simply run the code. 58 has the value of 0, even though I haven't put anything in there. Word 58 has nothing. So apparently C thinks that nothing for characters is the equivalent to 0 for numbers. Distance and long distance are 0. So you can see a pattern here that whenever you declare a variable and you have not initialized it to a particular value, its default value is 0. If at some point in your code you are dividing by that variable and you forgot to initialize it, you might crash your code because you're dividing by 0. It doesn't mean you have to initialize it to 1 or something else. Only initialize it to something that makes sense. Let's look at some of the qualitative measures that I am suggesting. Again, those are not recipes or prescriptions. Those are points for you to think about, contemplate, and ultimately decide for you what makes sense for you and in your program. For example, is the problem you are trying to solve in code being clearly stated and defined? How do you know? Have you checked with other similar projects? Maybe somebody has already tried to solve the same thing and they reached the conclusion that the problem is unsolvable, or the approach they took and you are repeating, it's not very efficient. 2, think, have a plan, develop an algorithm, draw a flowchart. Only then start writing code. Make code writing your last priority. Debug algorithms on paper. What does it mean? Maybe you want to create a table of numbers and you pretend that you are the computer, plug in the numbers in loops, in variables, and see if you can track what the program would do if it ran for real. Then think without testing, but just try to imagine and find potential loophole in your code. Let's say you wrote an array that can process 1,000 numbers and your program is built on the assumption that at any given time there will be about 1,000 numbers. What happens if all of a sudden that number is 1,000,000? Is your code going to run as efficient for 1,000 numbers as for 1,000,000 numbers? Should you even worry? Maybe this is such an esoteric hypothetical situation that it's completely not applicable to your situation, but you should at least ask yourself this question. What if you get a very small data set? What if it's only 2 numbers and you expect 1,000? Is your arrays and everything you define, are they overkill? What if there's no data? The program starts to run and nothing happens. It's expecting to read some data from a file, but the file is empty. Will it crash? Will it give you a message, or will it hang? Will it just get into an infinite loop until some data is available? What if you give it very large numbers? So your program is programmed to deal with numbers, let's say between -1,000 and +1,000, and all of a sudden you give it 1,000,000,000. Will it be able, if your number is going to start a loop, and you know that the number is typically going to be 30, 40, 50, all of a sudden you give it 10,000. You might think the program doesn't work because everything is so slow, it has to finish the loop. What if you give the number that are very small? What about 0.0000001? Will something like this be rounded to 0 and crash the program if you divide by it? So all these issues you have to think about, at least on paper, and then start to experiment with writing the code. Simpler is better than smart. Simple means easy to debug, easy to improve, easy to explain, easy to give to someone else. Do not always attempt to show how smart you are and how efficient your code is and how you're better than anybody else and your code does tricks that nobody understands, only you. It's going to come back to haunt you, if not bite you. Keep it simple, keep it easy, and you'll be happy, and your manager will be happy, and everybody in your team will be happy. And verify the code as you go. Do not write the whole thing and then test. You wrote a function, run it right away. You wrote another function, maybe the functions are connected, run them together. Organize the code into very small functions so you never have a very, very long function to test. Again, those are just some tips. Maybe you have a function, again, initialize values. We saw a couple of videos ago, you can initialize by passing pointers by reference. So you have a lot of options at this point. I cannot stress this too much. Think, then code. Let's look in this video at some debugging techniques. Now that you learn to code, you learn some advanced features, you have some experience, it is time to also pause and see how can you find out if there's errors in your code, and if you know there's errors, how can you isolate them? There are several techniques that you will have to interpret and adapt to the way your program style is, your problem-solving style is, other criterias and other tools and experience. A simple thing to look at is always verify values. If you know that a value is being passed on to a function, before you do anything inside the function, tell the function to print the value so you know for sure that the values that are being received are the correct ones. This goes true for initialized variables, function parameters, and array boundaries. When you are trying to access an element in the array and using an index, make sure that index is not less than the lower boundary of the array, and it's not higher than the upper boundary of the array. Other techniques for debugging are set some smart mechanisms. I will show you shortly how to do something like that. Activate on demand so that you can set things in place that works when you need them and don't do anything when you don't. Some modern integrated development environments include debugging tools. However, as a beginning programmer, I advise that you build your own, even primitive, debugging techniques because it will make you explore the code. You will understand not just how code should be written and what it does, but you will understand yourself and you'll be able to improve yourself. Finally, some trade-off between manual or system tools. Manual tools are more tedious because you have to do everything from scratch. System tools are not necessarily as efficient and they don't necessarily do exactly what you want them to do, but they're ready-made and you don't have to spend time developing them. Let's look in the code and see a system that I implemented for you, and you can look at it as just a suggestion. Before I'm going to show you, I just want to run the code so you can see what it does. It does nothing. I created some functions. They simply say it's working, it's not working. So you can see we have a function 1, a function 2, and a function 3. So some function 1 says it's executing, still doing something, keeps going. Function 2 is just executing, 3 is executing, busy looping, still doing something, and so on. Let's say I want to know more than that. If you look at some function 1, lines 41 through 43 is where those messages are coming from. Some function 1 is executed and so on. So basically what these functions do, they just print some text. I created a set of functions here that do nothing except they help me illustrate to you the concept of debugging. Let's focus for now on line 38 and 39. First, line 39. Printf something in some function 1 received a equals an integer, b equals an integer, and those are a's and b's, the values that have been received by some function. So what I'm doing here in line 39, I am printing the values of the two parameters a's and b's. Notice line 38. If debug flag, in other words, if debug flag equals true, only then you printf this. And notice another thing on line 39, something called debug alert. Now it's time to look at our macro. Let's look at a few things here. First, I have 3 constants, debug on, which is 1, and debug off, which is 0. I could have used 1 and 0, but the text is so much more readable when I use those terms. The other one, it's a debug alert. I will show you how I can insert that alert as needed. And finally, I have a debug flag, which is now set to off, meaning 0. I could have said set debug flag equals 0 or set it equals 1. This is more elegant and more informative to somebody that looks at this code for the first time. Here's my prototype functions. The one receives 2 ints, the other's 2 floats, the other an int and a float, and this is really not important. What's important is what we do with this debugging tool. So here's the little trick. So notice right now, the functions just print whatever they do, but I want to verify what they do. I'm going to set this debug of flag to on. All I'm saying is now debug flag equals to 1 instead of 0. Let's run the code and see what happens, and then I'll tell you how I did it. First, you can see there's considerably more input into the function and some additional text outputted back. There's an arrow that says in some function received A3 and B5. And now in some function 2, we received A equals 2.000. Apparently it's a float. Some function 2 is executed. Then we have another message that says it's again in some function 2 with M equals 4 at line 57 now. I'm also printing on which line, 53 and so on. So I have enabled that through a simple variable. I can put this back to off and run the code, and there's no debug information. So let's see how this works. I set debug flag to off right now. In each one of those functions, before I just print the feedback of what's happening inside the function, I put an if for debug flag. If debug flag is turned to on, then I'm printing whatever this line 39 says to print. If not, I'm just ignoring it. In addition to that, I have some functionality that's being placed in what the function does. I'm computing some things. I am working on some formulas. But here's another interesting thing, is that debug alert and line. So if I hover over, notice that is that arrow. So I essentially created a value, debug alert, that stores that little arrow. So whenever I want to display it and draw attention to the debugger, here's the arrow. The other one, which we saw earlier 2 videos ago, is line. Line is a known processor directive that says print the line that you are currently at. Very handy if you want to print and find information that's deep inside the computer and you don't know even where the file is. That's a perfect usage of that line. And this is pretty much it. Every function does something extra to its core, but other than that, it's pretty much straightforward. Turning a flag on, off. If it's on, you print a text message, otherwise you don't. Another good programming practice we will talk about in this video is the need for simple things, simple solutions that are clear. So let's start with simplicity. What do we mean by a simplicity concept in the context of programming? First of all, we don't like complex code that's so hard to read and so convoluted, even though there's some trickery there that's the envy of the world. Even though complex code might be more efficient and harder to steal, simpler code, it's easier to read, easier to maintain, easier to debug, potentially less efficient, but it's still worth considering once you have all the information necessary. Let's look at a little program and try to come up with some advice. That's all the program does, other than printing something. And if you haven't noticed yet, it calculates the square root equation. So we have the values of a, b, and c, which means we have formula ax squared plus bx plus c equals 0. That's the formula we're solving. And we know that the solution to that formula is minus b plus square root of b squared minus 4ac, all of that in square root divided by 2a. So minus b minus square root of b squared minus 4ac divided by 2a, and so on. What I would like to do here is to show 2 alternative ways to write those calculations. Look at line 18 and 19. The formula looks very cluttered. It's not clear with all those parentheses where they open and where they close. On the other hand, line 24, we are calculating separately the discriminant, taking b squared minus 4ac. If the discriminant is bigger than 0, only then I can perform any kind of calculation about it. So if it's bigger than 0, and I have another qualifier, 4ac if that a is also not equal 0, then I can proceed, because recall the quadratic equation is b squared minus 4ac square root of all that. Then we add either the negative of it or the positive of it and divide everything by 2a. If a is 0, it will imply that we are dividing by 0, and we have to handle that separately. So what we're doing is, before we calculating anything, so we don't just calculate for no reason, I'm asking, is the discriminant bigger than 0? And is a not equal 0? If that's the case, then we can now proceed and do it in a slightly different way. We have the discriminant already computed separately. And now I have numerator 1 and numerator 2. So the numerator is minus b plus the square root of the discriminant, or minus b minus the square root of the experiment. One other reason to break those into those chunks is that I have an opportunity now to test those values separately. I can test the value of numerator 1, I can do numerator 1 divided by 2a, and so on. So I'm not that dependent on an external source. And that's all there is about this video. All we need to do now is actually print the results. And here they are. In both instances where we print root 1 and root 2, we get the same exact result. So root 1 is minus 0.450807, and negative 2 minus 3.549.193. The last video in this course will discuss the development of portable code. So first, let's see what do we mean by that. Portability is a great issue with programming because portable code can run on more machines than non-portable code, is less dependent on one operating system or another, less dependent on a style of programming, less dependent on alphabets. Does code in the US run the same as code in Russia or the same in China, and there's character sets and so on. So let's look at some of the issues. First is the size of data types. In some languages and in some computers, same data types have different sizes. So we have to know that 8-bit on a Mac is the same as 8-bit on Linux or Windows and so on. The other one is increment versus decrement variables. Because we can assign a value to x and then at the same time increment x with a plus plus sign by 1, are we using the right x in the next iteration? What about sign versus unsigned variables? And we'll see something very interesting related to that when we are performing right shift on sign values. The other one is byte order. So when you define a struct with several fields, it is not guaranteed that those fields will form a contiguous array of memory locations. So it is our opportunity to detect that and do something about it. Finally, there's the byte order, because, well, again, when you define struct, it is not clear whether, let's say you have two vectors or two data points x and y, it is not clear whether x is stored before y or after. Let's see some of the things we can discuss about this in code. So first, we're going to define a constant max character to be equal 10, and I will show you immediately what is this for. So let's look at some declarations here. First, I would like to print the size of the types long, int, and float. This is not a random thing. When I showed you the previous window, I said that one of the issues that we need to discuss is the size of the various data types and ensure that they are the same across multiple operating systems and types of computer. So we are printing size of long, size of int, and size of float. Printing a line, and we're moving on. Now we have two arrays. One has the letters A, B, C, D, E. The other is the numbers 1, 2, 3, 4, 5. We know that if we assign letters n the value at symbols n, it should be the same. However, in addition to that, I am incrementing n before I'm using it, and then I'm printing the values. I'm repeating the process, line 32. Now I'm doing the same thing with letters and symbols, but a reverse addition. So in line 29, I had plus plus n. Line 35, I had n plus plus. And I again print the contents of letters without the 1. We have to be careful with signed and unsigned code. Let's run for now what we have, and then we'll draw some conclusions. So first, you recall we started with the sizes. So we have the size of long is 8, size of int is 4, size of float is also 4, and we can move on. Now let's look at the letters. So N1, because it used to be 0, now there's some relationship between 1 and N. It's not obvious where it's coming from. I'm sure the debugging process we discussed earlier will come in handy. The other one is letters location 0. And the third one is shifting, and this I expect not to have problems at all. Let's focus on the shifting, where we have 5 is shifted 1 bit to the left, and it equals 2 now. And minus 5, it's also shifted the same amount, and it's now equals minus 3. So it's a big difference between 2 and minus 3, so let's see what this might be attributed to. Notice in both cases I'm shifting the number 5, except in the second case I am shifting the opposite of the number. If this is consistent, then we can live with that, but apparently it isn't. Other things you can do in your code is to notice different structs of memory layout. So it is known that bytes and chars and so on takes a certain amount of space. It's not clear whether the price and title below in the struct book, they always take the same price, so the struct book would always have the same price. Second, you should look at portability across operating systems. For example, the end of line in text file is \n. However, on Windows, it could be \n, but it could be \r. ASCII is only used in English-speaking countries. What about Chinese, Japanese, where they use a different notation, and a char type is 16 bits. So you can see we have quite a few things to think about. We have some solution to them, some food for thought, but the more mindful we are of those things, even if we don't have a solution right away, the better collectively the programming community will be.